All right, people. I believe everybody is doing great, nice, and absolutely fine. So, welcome to Unacademy NEET English. My name is Yawar Manzoor, and I am a physics educator in the NEET UG category. I would want you guys to tell me in the chats if I'm perfectly audible, visible to each and every single student. Okay? And guys, before starting the session, I would want you guys to smash the like button, mark your attendance, whosoever is watching this particular session, because marking the attendance is extremely mandatory, extremely important. Okay? And then I'll be telling you what are we going to do in this particular mega marathon. Okay, what are the chapters we are going to complete in this mega marathon? Each and every single thing I'll be telling you in detail today. Okay, and if there are students in this marathon who are watching this for the first time, who are studying these chapters for the first time, no need to worry about anything. You would be able to understand each and every single thing, provided if you give me your 100% attention. I'll be showing you each and every single thing, and I'll be telling you if you get the confusion at any point, what you are supposed to do. Now, guys, let me know in the chats if I am perfectly audible, visible to each and every single student. Guys, light up the chats with the fire emojis. I can't see the fire. I can't see the hearts. Everyone means everyone. Everyone means everyone. Okay? And if you have not liked the session yet, I would want you guys to like it as soon as possible. Smash the like button. Everyone means everyone. Everyone means everyone. That's great. That's great. Okay. Yes, JEE students can also watch this particular session because we'll be targeting all the topics, whatever you have in these chapters, okay? And all the problem patterns, whatever has the probability to come in your NEET and JEE examination. Now, guys, before this, I would want you guys to see this one. This is the mega marathon, complete physics mega marathon that I have taken last year for the NEET 2024 students. Already a lot of students have watched it, 2.1 lakh views. So I have tried to make this year better than the previous year. Okay. So my dear friends, I have added some more questions. Okay. I have added some more problem patterns. Okay. Rest. Everything when it comes to the chapters, these are the chapters that we will be targeting. We have the electrostatics, we have the capacitors, we have the current electricity, magnetic effects of current, magnetism and matter, you have electromagnetic induction, you have AC. Total of 7 chapters, and these are the big chapters when it comes to the 12th portion. All of these chapters will be discussed in detail from the scratch, from the basics. Now, let's suppose if there are students who are watching this for the first time, they are getting some confusion at any point, okay? Now, my dear friends, at that point of time, let's suppose we are studying a particular topic. You are getting confusion at in that particular topic. What you are supposed to do, you have to mark it over there, okay? And then you have to continue your journey with me. But later on, what you are supposed to do is, you have to open this channel, that is Unacademy NEET English. And over there is a playlist that is Game of NEET 2.0 that is completely for physics, okay? For physics playlist only. All these chapters I have taught in complete detail. So if you get any sort of confusion in any chapter at any point, you can go and watch that particular topic from this particular session. Like if you're getting confusion in electrostatics in a topic, like in Coulomb's law, you open this electrostatics Coulomb's law and you watch it in detail, you'll get confusion out. But when it comes to this particular session that we have over here, I'll be telling you, see, the amount of content or the amount of, we say, problems, the amount of theory that you need, that will be limited over here, okay? But I'm giving you the guarantee and assurity in your NEET examination, all the problem patterns you would be able to solve, the amount of content that I'll provide you over here. That is for sure, okay? So guys, if I say at some point, remember this, just keep that thing in your mind, you have to remember it. You don't have to ask me the question, sir, why not? Because that we have already discussed in the marathons of every single chapter. Now, my dear friends, not wasting the further time, let's get started with this mega marathon The first chapter of the mega marathon that we will be starting is the electrostatics. Extremely important. And when it comes to the electrostatics, my dear friends, I would want you guys to focus over here. You can expect 4 to 5 questions from the electrostatics portion. That means 20 marks. Extremely high weightage chapter. Okay. And my dear friends, when it comes to this chapter, it is extremely easy, formula based. You have to remember the formulas and just apply those formulas in the questions. You would be able to understand each and every single thing. Now guys, listen to me very, very, very carefully. So I am starting the chapter. Make sure you have already subscribed to the channel and you have liked the session, okay? Because liking the session is mandatory. Now, my dear friends, let's start with the topic that is what we call the charge. In electrostatics, the very first topic that we need to understand is charge. What this charge is all about. See. Let me give you the basic example that I keep on giving every single time whenever I teach this particular chapter. Let's suppose I have got a comb over here. I'm taking a comb. Okay, I'm taking a comb. Guys, this is the comb that I have. Okay, with which we make the hairstyle or something like that. And I'm taking this comb, I'm rubbing this comb with my hair. Okay, I'm rubbing this comb with my hair. Then, my dear friends, I'll take the small piece of papers. And I'll place it over here. These are the small piece of papers and I'll place these piece of papers over here. When I rub this comb with my hair, can I take this comb near to the piece of papers? Could you please tell me what is going to happen? Maximum number of students might have done this experiment in their childhood. So we say these piece of papers will be attracted towards the comb. Okay, these are the piece of papers. Small piece of papers. These will be attracted towards the comb. So why this attraction took place? Let me just write over here. We say these will be attracted. Okay. Why this attraction took place? So it is because when you rub this comb with your hair, something gets occupied onto this comb, and that something, because of that something, these piece of papers are attracted towards the comb. You are rubbing the comb with your hair. Something gets occupied onto this comb. Because of that something, these piece of papers are attracted. These piece of papers stick to the comb. That something is what we call the charge. This is what we call the charge. Okay. So can I say when it comes to the charge is something. Charge is something. It is something. It is something due to which a body shows electrical and magnetic effect. So charge is something due to which a body shows electrical and magnetic effects. Like over here, the comb is showing the magnetic effects. It is attracting the piece of papers. Okay, that's it. When it comes to the symbol of charge, my dear friends, simply, when it comes to the symbol, we say symbol of charge is Q. Simply, we say symbol of charge is Q. We say, sir, Q is equal to 2 Coulomb charge, 3 Coulomb charge. Like you have symbol of mass as M. Similarly, you have symbol of charge as Q. And when it comes to the SI unit, SI unit of charge is Coulomb. Like my dear friends, you say, sir, mass of this ball is 2 kgs. What is this kg? This is a unit. Similarly, you say charge on this comb is 2 Coulomb, 3 Coulomb, 4 Coulomb, something like that. You do not say charge is 4 kg. Okay. Yes. Now, one more thing I just want to add over here. What is that? That is, when it comes to the charge, there are 2 types of charge. Sir, first one is positive charge and second one is negative charge. Okay. We say positive charge and negative charge. All of you must remember from now onwards, if you have a positive charge on a body, let's suppose this is a rod On this rod, you have positive charge. On the another rod, you have negative charge. Always remember, my dear friends, they will attract each other. They will attract each other. Because positive and negative, unlike charges, attract each other. Okay. Now, my dear friends, if you have a positive charge over here, if you have a positive charge over here also on another rod, we say they will repel each other. Because like charges repel. Keep that thing in your mind. Like charges always repel each other. Now, my dear friends, when it comes to if you have a negative charge over here, you have a rod on which negative charge is placed, and you have a rod, another rod on which also negative charge is present, we say they will also repel each other. They will also repel each other. So positive charges attract, two negative charges also, positive and positive repel, positive and negative attract, negative and negative repel. So this is the sufficient amount of information regarding the charge. What is charge? Charge is something due to which a body shows electrical and magnetic effects. Okay. And my dear friends, like I told you here, because of the charge, comb is attracting the piece of papers. Then we have two types of charge, positive and negative. And my dear friends, symbol of charge is Q, SI unit is Coulomb. Please give me the thumbs up and send the fire emoji in the chats if everything is crystalline clear. I would want you guys to do it as soon as possible. I would want you guys to do it as soon as possible, guys. If everything is crystalline clear, let me know in the chats. If everything is crystalline clear, let me know in the chats. Okay. And if you have not liked the session, I would want you guys to smash the like button. Okay. Great. Great. Now, guys, let's move on to properties of charge. Let's move on to properties of charge. Properties of charge. Guys, understand very carefully. When it comes to the properties of charge, the very first property is charge is a scalar quantity. Okay. It has only magnitude. We say, sir, charge on this rod is 2 Coulomb only. You do not say charge on this rod is 2 Coulomb in that direction. Charge on this rod is 4 Coulomb in that direction. No, it has got magnitude only. So it's a scalar quantity. Okay. Second point we say, my dear friends, take a look over here. We say charge is conserved. Charge is conserved. Charge remains conserved. Conservation of charge. Guys, see, let's suppose you have a box over here. You have a box over here. And inside this box, you have this ball, you have this ball, you have this ball, or sphere. And on this ball, you have got 2 Coulomb charge. On this ball, 3 Coulomb charge is placed. On this ball, 4 Coulomb charge is placed. What is the net charge inside this box? You say, sir, 4 plus 3 plus 2, that is 9 Coulomb. Now I want you guys to take this box and shake it. Okay, take it to the another place, throw it over there. Okay, so then place it over here. And when you open this box over here, you saw that on the first ball, charge is 1 Coulomb. Previously, it was 2 Coulomb. On the second ball, charge is 4 Coulomb. Previously, it was 3 Coulomb. And on the third ball, charge is 4 Coulomb. Previously, it was 4 Coulomb also. Okay, it is same. Now, guys, what is the net charge finally inside the box? You say net charge finally inside the box is 9 Coulomb. Net charge finally is 9 Coulomb. Okay. Now, my dear friends, I would want you guys to tell me one thing. What is that? What is that? Guys, see. Sir, whatever is the charge initially, same is the charge finally. Can I say charge remains conserved? Yes. But my dear friends, when it comes to inside the box, the balls definitely have transferred the charge between each other. They have shared the charge between each other. But net charge of the system remains conserved. That's what we call the conservation of charge. transfer of charge is possible, but when it comes to the net charge of the system, that always remains conserved. This is called the conservation of charge. Next, my dear friends, we have over here, that is charge is quantized. This is the third property, I would say. What does quantization of charge exactly mean? What does quantization of charge exactly mean? Guys, see. I am saying you go to the shop, okay? You go to the shop. If the shopkeeper is selling the pens, okay, these are the pens. Can you ask the shopkeeper to give me half of the pen? No, it is not possible to buy half of the pen. You can buy 1 pen, 2 pen, 3 pens, 4 pens. So I say these pens are available in fixed amounts. Okay, these pens are available in fixed amounts, not like rice. If you go to the market, if you go to the shopkeeper, you ask the shopkeeper, give me 2 kg rice, 2.5 kg rice, 50 grams of rice. He can give you any amount. So rice is available in random amounts. But when it comes to the pens are available in the fixed amounts. 1, 2, 3, 4. Okay, 2.5 pens are not possible. 3.5 pens are not available. So I can say pens are quantized. Now, my dear friends, same is the case over here. If I am writing charge is quantized, what does that mean? That means charge is available in fixed amounts. You cannot get the charge in random amounts. You can get the charge in fixed amounts. Like, what is the smallest quantity that you can bring over here? 1 pen. Okay. What is the smallest charge that is present on the face of the earth? On the face of the earth. You say, sir, smallest charge is charge on 1 electron. If somebody asks you, sir, how much is the charge on 1 electron? You say charge on 1 electron is 1.6 into 10 raised power minus 19 Coulomb. Sir, can you get the charge of E by 2? No, not possible. Because charge on 1 electron, 1 E means charge on 1 electron. It is the smallest charge available on the face of earth. Like here, smallest quantity is 1 pen. You cannot get half of the pen. Similarly, smallest charge is 1 electron. You cannot get half of the electron. Not possible. So charge on 1 electron is smallest charge. Similarly, my dear friends, E by 2 is not possible. 3.5 electron is not possible. But 3 electrons are possible. 1 electron, 2 electron, 3 electrons. So that's what I'm trying to say. Charge is available in fixed amounts. So possible charges can be. What are the charges which we can get? What are the charges which we can bring? So I can say that charge is, sir, 1 electron is possible, 2 electrons are possible, 3 electron possible, 4 electron possible, and similarly n electrons are possible. Ne. N can be 1, 2, 3, 4 and so on. Sir, is 2.5 electrons possible? We say no, not possible. Is 3.5 electrons possible? No, not possible. So what are the possible charges? What are the charges which is available? That is 1 electron, 2, 3 and n times of E. So basically, we can write over here Q is equal to plus minus. Charge can be positive, it can be negative, n times of. This is called the quantization of charge. So quantization of charge tells you charge is quantized. Charge is available in this world in fixed amounts, not in random amounts. You can store 1 electron, 2 electron, 3 electron, 4 electron. 2.5 electron is not possible because 1 electron is the smallest charge possible. So 0.5 is not possible. Please give me the thumbs ups in the chat if everything is crystalline clear to each and every single student. Guys, let me know in the chats with the fire emojis. Everyone means everyone. And if you have not liked this session, I would want you guys to smash the like button as soon as possible. And one more thing, my dear friends. This is my Telegram channel where I will be sharing the notes and where I put up every single information, whatever is needed for the NEET students and JEE students. Okay. So this is t.me/YAWARMANZOOR. Join this Telegram channel. That's Yawar Manzoor Physics. Okay. You can search it on Google and then click over there and you'll reach on to this channel. So join this channel. I'll be sharing the notes on this channel. Okay. That's great. That's great. So we are done with the properties of charge. We are done with the properties of charge. Now, guys, let's move on to Coulomb's law. Let's move on to the Coulomb's law. I would want you guys to focus exactly over here. Give me your 100% attention. Guys, when it comes to the Coulomb's law, since let's suppose we have got a charge Q1 over here, and this is Q1 charge, that is positive charge. We have got another Q2 charge over here. This is also positive charge. Okay. Since this charge and this charge, they repel each other. Yes. So they apply the force on each other. They apply the force on each other. If I'm saying I'm repelling that person, what does that mean? That means I'm applying the force on that person, repulsive force on that person. That's what I'm trying to say. This charge is repelling this charge. So this charge is repelling this charge with a force F. This charge is also repelling this charge with a force F. Okay. So the two charges are repelling here with a force F, such that the distance between them is R. If somebody asks you, how much is the force between the two charges? What is the force they are applying on each other? I can say force between the two charges. If somebody asks you, what is the force between the two charges? You'll say, sir, simply, this force is equal to, that is K. K is the Coulomb's constant. Okay. Then we say Q1. Sir, this charge. Then we say Q2, this charge, divided by, we say, R square. So this is the force between the two charges. And clearly say, sir, force is directly proportional to Q1 and Q2. If the magnitude of the two charges is large, if there are bigger charges, they apply more force on each other. If there are smaller charges, they apply less force on each other. They apply less force on each other. Okay. Now, my dear friends, so from now onwards, if somebody asks you, we have a charge, we have another charge. Tell me how much force they are applying on each other. F is equal to K Q1 Q2 by R square. So you mention over here where K is Coulomb's constant. Where K is Coulomb's constant. And my dear friends, value of this K we say 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Okay. And this epsilon naught, this is what we call permittivity. Permittivity of free space. It is called permittivity of free space. Okay. So this epsilon naught, I'll tell you each and every single thing, what this epsilon naught is all about. So this epsilon naught is simply permittivity of free space. And my dear friends, if somebody asks you, what is the value of this epsilon naught? You simply say this epsilon naught is 8.85 into 10 raised power minus 12. Then we say Coulomb square upon Newton meter square. This is the value of this epsilon naught. Now, I would want you guys to put the value of epsilon naught over here. Then 1 by 4 pi, pi is 3.14 into value of epsilon naught. If you solve this, value of K will come out to be 9 into 10 raised power 9 Newton meter square upon Coulomb square. This is the value of K. I hope everything is crystalline clear till over here. You have got the two charges. The two charges apply the force on each other. That force is equal to F is equal to K Q1 Q2 by R square. K is 1 by 4 pi epsilon naught. Value of epsilon naught is 8.85 into 10 raised power minus 12. If you put this epsilon naught here, value of K will come out to be 9 into 10 raised power 9. Is this crystalline clear to each and every single student? Is this crystalline clear to each and every single student? Is this crystalline clear to each and every single student? Tell me guys, fire in the chats. Everyone means everyone. I would want you guys to tell me if this is crystalline clear to each and every single student, and smash the like button. Smash the like button if you have not liked the session yet. Marking the attendance is very much mandatory. That's great. Okay. Now guys, take a look over here. I would want you guys to listen to me very carefully. Listen to me very carefully. Guys, let's suppose I have got a box over here. This is the basics from vectors, okay? Because this is needed over here. I have got a box over here. Okay, this is a box. On this box, I am applying the force from this side, that is F. And I am applying the force from this side, this is also F. Now, what is the angle between the two forces? That is 180 degrees. Okay, that is 180 degrees. Angle between this and this is 180 degrees. In this particular case, guys, if somebody asks you, what is the net force on the box? You say 0. Provided this force and this force is same. If the two forces are acting in the opposite direction, net force will be 0. If the two forces are same in magnitude. Okay, cool, yes. Now, guys, one more thing. Let's suppose if you have a box. On this box, one force is acting in this direction, another force is acting in the same direction. What is the angle over here? Angle is 0 degrees. The angle between the two forces here, two vectors, is 0 degrees. If somebody asks you, what is the net force between these two? You say F plus F, that will be simply 2F. Directly remember, sir, where does this come from? Don't ask me that, okay? We have studied that previously in the marathons of every chapter. Okay, under root of F1 square plus F2 square plus twice F1 F2 cos of theta. By using that formula, you get this, you get this. Okay, next, my dear friends, if angle between the two forces, this is one vector, this is another vector, F is 90 degrees, if theta is 90 degrees. Guys, always remember, in that case, net force is under root of 2F. If you have F, resultant of this F and F at 90 degrees, root 2F. Directly remember. Then, if theta is equal to 60 degrees between the two forces, in that case, we say net force is under root of 3F. Done. If net force, if theta between the two forces, this is one force, this is one vector, this is another vector, okay, this is F and this is also F. In this case, angle, if it is 120 degrees, always remember, my dear friends, net force in this case will remain F only. So this force will be also F. Net will be also F. Keep that thing in your mind. Okay, now guys, let's suppose I have got the first question over here. Okay, before this, I would want you guys to answer this. Guys. If you have a symmetrical figure, this is a square, this is a triangle, okay? This is a triangle. This is a triangle. What else do you have? Okay, let's suppose I'll make over here hexagon. This is a hexagon, okay? And let's suppose I'll make the pentagon also. Pentagon means 5 sides, in which you have 5 sides. Guys, if you have the symmetrical figures, please remember from now onwards. And if similar charges are present at every single corner, plus Q, plus Q, plus Q, plus Q. Here also, you say plus Q, you say plus Q, you say plus Q. Here also, plus Q, plus Q, plus Q, plus Q, plus Q, plus Q. At every single corner, charge is present. At every single corner. Guys, listen very carefully. In case of these symmetrical figures, if you have the charge present at every single corner and similar charges are present, it's not like plus Q and here it is 2Q. No, similar charges are present. Here also it is plus Q. Here also it is plus Q. It is plus Q. It is plus Q. It is plus Q. Then, if a person comes and asks you, I'll place the charge at the center, another charge. It can be anything, sir, minus Q. Let's place minus Q. Let's place 2Q. Let's place 4Q. We say, guys, please remember, in these particular cases, we say net force is equal to 0 on center charge. Net force is equal to 0 on the center charge in all the cases. What is the condition? If you have, write it down, guys. If you have a symmetrical figure and identical charges are present at every corner, then the net force on the center charge is 0. Sir, if the center charge is similar or unsimilar, it doesn't matter. So net force on the center charge will be 0. Net force on the center charge will be 0. Net force on the center charge will be 0. Directly remember. Directly remember. Is this clear? Is this clear? I hope the speed is okay. I hope I'm not going fast. I hope the speed is okay. Please let me know in the chats if the speed is okay or I'm going fast. Tell me, guys. Tell me, guys. I would want you guys to give me the signal in the chats. Tell me. Everyone means everyone. Okay. If there are students saying little bit slow, means it is fine for those students, but I should not go fast. Okay, perfect. Chill. Let me get those students, if there are students who are feeling sir is going a bit fast, let me get them on track, okay, in next 15 to 20 minutes. Then you will match my speed, then we'll go with the speed of light. Chill. The point is you have to understand every single concept. Okay, that is our goal. Chill. Now guys, next we have over here this one. Guys, you have minus Q, you have minus Q, you have plus Q, you have plus Q. You guys are supposed to tell me what is the net force on the center charge. Sir, will it be 0? See, identical charges are not present at the corners. It will not be 0. It will not be 0. Now guys, take a look in this case. See, this negative charge will attract this positive charge towards itself with a force, let's suppose F. This positive charge will repel this positive charge with the force F, okay, in this direction. This negative charge will attract this positive charge with a force F. This positive charge will attract this positive charge with a force F. Now I would want you guys to focus. Guys. This F and F, these two are in the same direction. Now tell me, if the two forces are in the same direction, what is the net force of those two? That is 2F. So I can say the resultant, guys, if I'm making this over here, this F and F, this is F and this is F. And here also this is F and this is F. This F and F. And this angle is 90. In case of square, this is 90. Could you please tell me, if the two forces are in the same direction, what will be the resultant force? F plus F is 2F. So I can say this will be 2F. Sir, this F plus F is also 2F. So this will be also 2F. Now angle is 90. Guys, if the angle between the two forces is 90 degrees, take a look over here. If the angle between the two forces is 90 degrees, resultant will be root 2F. See, if this is F, then resultant is root 2F. If If this is x, this is x. Resultant is root 2x. Now, if this is 2f, this is 2f. In that case, resultant will be root 2 of 2f. I hope this is not creating any sort of confusion. So in this case, net force, I can say that is under root of, we say 2f. Whatever is the force over here, you have to just put here. So this will be simply, that is 2 root 2f. That is 2 root 2f. And what is this f? Guys, f is the force between these two charges, these two charges, these two charges, these two charges. And guys, always remember, let's suppose if this is a square. Okay, this side is, let's suppose, a. What will be the value of the diagonal? This is a root 2. What will be the value of half of the diagonal? Always remember, this is a by root 2. Now, one charge is present at the center. Another charge is present at the corner. Another charge is present at the corner. This is plus q. This is minus q. Could you please tell me what is the force between this and this? You say, sir, it is simple. Sir, F will be equals to, that is K, Q1 is Q, this Q2 is also Q. Don't consider minus Q because we are finding the magnitude. Divided by R square. R is A by root 2 whole square. Now, can I say this will be A square divided by 2. So this will be, if you take 2 in numerator, 2K Q square divided by A square. Now guys, put this F over here. So this will be 2 root 2. Instead of F, I can say 2K Q square divided by A square. Now 2 into 2 is 4. So it will be 4 root 2 K Q square divided by A square. Is this clear? Is this clear? Is this clear? Please give me the signal in the chats. Is this clear? Is this clear, guys? Let me know in the chats if everything is crystalline clear till over here. We'll move on to the next one. Great. Let's take a look at this, guys. See, guys, if you have a square something like this, you have placed minus 2 Coulomb on this corner. Okay, you have placed minus 2 Coulomb on this corner. Okay, and you have placed plus 4 Coulomb, minus 2 Coulomb, plus 2 Coulomb. Okay, now guys, find the net force at 2 Coulomb charge. You are supposed to find out the net force at this 2 Coulomb charge. You are supposed to find out net force at this 2 Coulomb charge. Guys, see. I'll make you understand. When it comes to the net force on this 2 Coulomb charge, guys, see. This minus 2 Coulomb will attract this plus 2 Coulomb towards itself with a force. Let's call this as F1. Okay. If I have to write this force F1, you say F1 is equal to K. How do you write the force? We say Q1, Q2 divided by R square. And R is the distance this side, that is 2 meters. Guys, see. What is the value of K? K is K. What is the value of Q1? Q1 is 2. Q2 is also 2. It is 2. Q2 is also 2. Divided by, what is the distance between the two? 2 square. That is 4. R square, that is 4. 2 square is 4. So 2 into 2 is 4. 2 into 2 is 4. So it is coming out to be K. Okay. Now guys, this minus 2 Coulomb will attract this plus 2 Coulomb towards itself. So could you please tell me what is the force between these two? Sir, that is this F2. That is this F2. So I can say F2 is equal to K. Similarly, K, Q1, Q2 by R square. So K, value of Q1, 2, Q2 is also 2. That is 2 into 2. Divided by distance between them. That is 2 square. So this and this will cancel. So it will again come out to be K. Now guys, this 4 Coulomb and this 2 Coulomb. This 4 Coulomb will repel this 2 Coulomb in this direction. This 4 coulomb will repel this 2 coulomb in this direction because positive repels. Now, with what force? That is mentioned over here, F3 force, F3 force. And I can say F3 in this case will be, sir, K. What is the value of Q1? That is 2 coulomb. What is the value of Q2? That is 4 coulomb. Divided by, what is the distance between the two? That is 2 root 2. So that is 2 root 2, its whole square. Guys, 2 into 4 is 8. 2 root 2 whole square is also 8. So this 8 and this 8 will cancel. So F3 is also K. Now, take a look. Guys, this is F1, F2, F3. Let me make over here. This is F1 and value of it is K. This is F2. Value of this is also K. This is F3. Value of this is also K. Now tell me one thing. This K and this K, both are at 90 degrees. What is the resultant of this one and this one? If you have F and F at 90 degrees, resultant is root 2F. So resultant of K and K, it will be simply, my dear friends, that is root 2K. Resultant of this one and this one is root 2K. Now guys, in this case, you have this vector. In the upward direction, you have K. In the downward direction, you have root 2K. Could you please tell me, what is the resultant of this K and root 2K? Guys, sure, net force will be always, guys, bigger force minus smaller force. If the two vectors are in opposite direction, so we say bigger force minus smaller force. That is root 2K minus K. Now take this K out. K is common. So root 2 minus 1. Is this clear? So this is the net force on this 2 coulomb charge. This is the net force on this 2 coulomb charge. Please give me the signal in the chats if this question is crystal and clear to each and every single student. I would want you guys to tell me in the chats if this is crystal and clear to each and every single student. Great. One more question. 3-point charges plus Q and minus Q are placed at the corners of an equilateral triangle. Okay, let me make the equilateral triangle over here. Okay, cool. Now 3 charges. It says plus Q, it says plus Q, it says minus Q are placed at the corners of an equilateral triangle. Of side A. This side is A, this is A, this is A. Another charge plus Q is kept at the centroid. Another charge plus Q is kept at the centroid. This is plus Q, which is kept at the centroid. Force exerted on plus Q will be, you have to tell me, what is the force exerted on this plus Q? Guys, see. If this is side A, always remember this distance from corner to the center, this will be A by root 3. Always remember this distance will be A by root 3. Now, this plus Q will repel this plus Q. This plus Q will repel this plus Q in this direction with a force F. This plus Q will repel this plus Q in this direction with a force F. This minus Q will attract this plus Q towards itself with a force F. Now guys, you have got 3 forces over here. 1, 2 and 3. One force is in this direction F. Another force is in this direction F. Another force is in this direction, that is F. Tell me guys. Sir, angle between these 2 forces in case of a triangle, always remember this angle is 120 degrees. Because if you have an equilateral triangle, this angle is 120, 120, 120. Now, if between this force and this force, angle is 120, what is the resultant of the 2 forces which has angle 120 between them? So that is F only. that is F only. So I can say resultant of this one and this one, that will be something like this, and that will be F only. Resultant of this one and this one is F only. Now already along this there was one F. F plus F is 2F. Now you have, after this you have F, and this is F. Now tell me, this F and this F, what is the net force in this particular case? That will be 2F. That will be 2F. Net force on the center charge is 2F. Now if you have to find the exact value, guys, F is the force between this charge and center charge, or this charge and center charge, or this charge and center charge. So can I say, sir, this net force will be, this is 2. And how can we write this F? F is K Q1 Q2 by R square. You can say K Q1 Q2 Q1 Q2 by R square. What is the distance between the two? A by root 3. So it will be A by root 3 whole square, and this is also square. Now this square and root will cancel, so 3 into 2 becomes 6, so it will be 6. So it will be 6 KQQ divided by A square. Is this clear? I hope this is crystalline clear to each and every single student. I hope this is crystalline clear to each and every single student. Is this clear, guys? Let me know in the chats. Let me know in the chats with the fire emojis if this is crystalline clear to each and every single student. Whosoever is watching, I would want you guys to tell me in the chats if this is crystalline clear to each and every single student. Guys, if you have not liked the session yet, I would want you guys to smash the like button. Now guys, take a look over here. I would want you guys to take a look exactly over here. Everyone means everyone. See guys, we have got equilibrium position. We have got equilibrium position. What does equilibrium position mean? Simply, if you have a charge over here plus Q, if you have another charge over here n times of Q, if you have plus Q, if you have n times of Q. Sir, what is this n times of Q? I'll tell you. If you have, let's suppose, plus Q and you have plus 4Q, in that case, n is 4. If you have plus Q, you have 9Q, n is 9. So if you have two charges, cool. Sir, where should we place the third charge? Where am I supposed to place the third charge so that net force or field is 0 on it? Guys, let's suppose, I'll tell you. Let's suppose I'll place the third charge Q0 here. I have to check whether net force here will be 0 or not. Check. This positive charge will repel this positive charge in this direction. Let's call this F1. This positive charge also repels this positive charge in this direction. Let's call this F2. This F1 and F2 both are in the same direction. So net force cannot be 0. Let's place the charge from this side. Sir, Q0. You'll say, sir, this plus Q will repel this plus Q, something like this. This positive will also repel this positive charge, something like this. Here also, you will say net force is not equal to 0. Here also, at this point, you will say net force is not equal to 0. Let's do one thing. Let's place the charge inside over here. See guys, let's place the charge here. this positive charge will repel this positive charge with force F1. This positive charge will repel this positive charge with force F2. Now, if you place the charge at the center, not at center, inside between the two charges, here the two forces are in the opposite direction. So I say net force here will come out to be equal to 0. Now the question is, at what distance you are supposed to place this charge? At what distance you are supposed to place this charge? Sir, this distance is x from the smaller charge. And this x is equal to, we say, r upon under root of n plus 1. If somebody asks you, what should be the distance, at what distance we must place the third charge so that net force on it is 0, you say x is equal to r upon under root of n plus 1. As simple as that. As simple as that. Okay. Now guys, let's have a look at the question. You have the question over here. In this case, I am asking you, where should I place the third charge so that net force is equal to 0 on it? Guys, sir, I'll place it over here, Q0. At what distance? You'll say, sir, at x distance from this charge. Sir, what is the value of this x? X will be r upon under root of n plus 1. R upon under root of n plus 1. Now, guys, what is n? How do we find the n? Guys, always remember, you find this n, this bigger charge, that is 36q, divided by this smaller charge, that is 25q. Q and q will cancel, so it will be 36 divided by 25. Keep it as it is. Now guys, do one thing. This x will come out to be, sir, this is r upon under root of n, and when it comes to the r, when it comes to this r, you say this r is given as 11 meters. Sir, what is n? N is 36 by 25. N is 36 divided by 25. Then we say plus 1. So you can say in this particular case, 11 upon root 36 is, my dear friend, 6. Upon root 25 is, we say 5. Then we say plus 1. Now I can say x is equal to, you guys will say 11 upon, now guys, 5 into 1 is 5. 5 plus 6 is 11. 11 divided by 5. Okay. Now 11 will go. So it will come out to be exactly, that is 5. So at 5 meters, you are supposed to place this charge. Then only net force on it will come out to be 0. Is this clear? Is this clear? So simple concept is, guys, if any of the students get confusion at any single point, I request that student to just simply mark that point, and later on you watch my one shot of that chapter and clear that out. That's it. But right now you go with the flow. You go with me like I'm going. That's it. So equilibrium position is if you have two charges, okay, and you are supposed to place the third charge somewhere around over here, where you must place the third charge so that net force is equal to 0. X is equal to r upon root n minus 1, n plus 1. Now guys, if the charges are of opposite nature, I'll just say when charges are of opposite nature. If the charges are of opposite nature, like you have plus q minus n times of q. Previously guys, here it was plus q plus nq. Or it can be minus q minus nq. In that case also same formula. But if you have the charges opposite nature, plus q minus nq. In this case, where should you place the third charge so that net force is 0 on it? Sir, from outer side. Place it on the outer side. At what distance? X distance. When you have the similar charges, place the third charge in between. When you have the opposite charges, place this charge from the outside, near to the smaller charge. This is the smaller one. Formula will be x is equal to r upon under root of n minus 1, under root of n minus 1. In that case, n plus 1, here you have n minus 1. Okay? Okay? Is that clear? Is that clear? Similarly, you can put, like, let's suppose I am placing q over here, 9q over here. Then you can say r upon under root of 9 minus 1. Okay, if you say one charge is q, another charge is 9q, x in that case will be r upon under root of 9 minus 1. So root 9 is 3, 3 minus 1, so it will be r by 2. At r by 2 distance outside. Simple, 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 simple. Now, the third thing which I want you guys to understand. The third thing which I want you guys to understand. Guys, see. In this particular case, we say, what should be the value of Q naught if all the three charges are in the equilibrium? Guys, previously in the two cases, I was saying, where should I place the third charge Q naught? Where? What is the distance? Now, I am saying, what is the value of this third charge? How do we find what is the magnitude of the third charge? You say, value of this third charge can be calculated using this formula. That is minus n times of Q upon under root of n plus 1 whole square. Let me give you the example. This was asked in NEET 2013. See what does the question say over here. You have got a charge Q. Now here, I'll be taking the classes in the Phoenix batch, okay? Definitely from tomorrow or day after tomorrow. That's for sure, okay? Sorry, I was busy with something. That's why I couldn't take the class. I'll be taking the regular classes. Muhammad Hafiz, okay? Now, guys, so we say plus Q. And my dear friends, what should be the value of this third charge? How do we find the value of third charge? Guys, see. Q is equal to minus n times of Q upon under root of n plus 1 whole square. Under root of n plus 1 whole square. Under root of n plus 1 whole square. Guys, I can say this Q is equal to minus n. N is how much? Guys, how do we find n? N is this Q divided by that Q, that is 1. So n is over here 1. And this Q, so keep it Q, upon under root of, what is n over here? That is 1 plus 1 and its whole square. Now guys, tell me, 1 root 1 is 1, 1 plus 1 is 2, 2 square is 4. So it will come out to be minus Q by 4. Guys, the value of the third charge is minus Q by 4. Okay. Yes, this is the equilibrium distance from the smaller charge. This is the equilibrium distance from the smaller charge. If somebody asks you, what is the equilibrium distance from the bigger charge? What will you say? This distance plus this distance. R plus X. Simple. This distance plus this distance. As simple as that. Guys, is this clear till over here? Please give me the signal in the chats. I would want you guys to tell me in the chats if this is crystalline clear. Everyone means everyone. Everyone means everyone. Is this clear? And if you have not liked this session yet, I would want you guys to smash the like button. as soon as possible. Yes, equilibrium distance is from the smallest charge. Equilibrium of two suspended charges. Now guys, listen carefully, listen carefully, listen carefully. Let's suppose, my dear friends, here in this particular case, this is the another problem pattern that can be asked from the Coulomb's law. Let's suppose you have got over here a thread, and with this thread you have the charge connected, that is plus Q. Plus Q charge is connected with the thread. Okay, you have a thread connected, a sphere which has a plus Q charge. And you have another thread, that is another plus Q charge is connected to this thread. Tell me one thing. If you have a ceiling, you connect a thread and then attach a charge. You connect one more thread, then attach a charge. Don't you think that in this particular case, my dear friends, the two charges will repel each other. The two charges will repel each other and they'll go away from each other. The two charges will repel each other and goes away from each other. This charge and this charge will repel each other and goes away from each other. And at a particular distance, the two charges will stop. At a particular distance, the two charges will stop. I would want you guys to understand this thing. We say, if the two charges are in equilibrium, then find the value of x, that is distance between them. Guys, equilibrium means when the two charges repel, now they are staying over here. Okay, they're staying over here in equilibrium at rest. Then find the value of x at what distance they are in equilibrium. Find the value of charge q and find the value of theta, this theta. At what distance, at what position equilibrium? If the two charges are in equilibrium, find the value of theta. And also, if there is a string over here, there will be tension in the string. Find the value of tension also. So, my dear friends, this charge q and this x distance, this was asked in. We say J Mains 2021. Guys, if you ever get a question of this sort, what you are supposed to do in this particular type of question, guys, always remember, listen to me very carefully. Take any charge. If I say the two thread charges are in equilibrium, take any charge, draw the forces acting on it. What is the force acting on this charge in the downward direction? That is mg. Okay. And guys, this charge is applying the electrostatic force, positive repel. So on this charge in this direction, electrostatic forces, that is k q square divided by x square. K q1 q2 by x square. K q square by x square. And guys, one more thing. We say if this is tension in this direction, we say this will be, guys, this will be theta. If this is tension, this will be theta. This will be t cos theta. And this component of the tension will be, t sin theta. T cos theta and t sin theta. Now guys, tell me, if the charge is in equilibrium, means upward force is equal to downward force. Right side force is equal to the force which is acting on the left side. Now balance the forces. Balance the forces. Guys, can I say this t sin theta is equal to kq square by x square. This force is equal to this force. Okay. Now, can I say this t cos theta is equal to mg? I can say this t cos theta is equal to mg. Now, divide the two equations. If you divide these two equations, now t and t will cancel. Sin theta by cos theta will come out to be tan theta is equal to, and here it is k q square divided by, we say x square mg. This x square mg. So this is the value of theta. So theta you can say tan inverse of, theta you can say tan inverse of kq square upon x square into mg. So we got the value of theta. Let's find the value of x and q. I'll just write over here. Let's find the value of x. Let's find the value of x. Let's find the value of x. Let's see. Take this equation. Take this equation. Let's call this as equation first. So I'll just write from equation first. From equation first. Can I say tan theta is equal to kq square upon x square mg? You have to find the value of x. Take this x over here. You'll say, sir, x square is equal to kq square upon, we say tan theta, and then we say mg. Now guys, x will be equals to, that is under root of, that is kq square upon, we say tan theta, and then we say mg. Guys, because of the square, we have replaced it with the root. Now guys, tell me one thing. In this particular case, if the questioner asks you to find the value of x, then charge, theta, all the things will be given from their side only. Okay. Now let's find the value of, let's find q. Let's find the value of q. Guys, from this equation only, we can say tan theta is equal to kq square, or I'll directly write. Guys, if you want to find the value of q, multiply this with this. So I can say this will be tan theta x square mg is equal to, here it is kq square. Can I say this q square will come out to be, that is tan theta x square mg divided by q. Sorry, divided by k. Now, take the square over here. Q will come out to be under root of, we say tan theta x square mg divided by k. This is the value of q. This is the value of q. Now, we are done with q theta x. Now, my dear friends, let's find the value of tension. Guys. Let's find tension. Tell me one thing. Let's suppose I am saying there is a charge over here, this q charge. I'm saying this is the q charge. What are the forces acting on the charge? Guys, understand. In the downward direction, you have mg. From the right side, it is electrostatic force. And then you have this tension in this direction. No doubt you have resolved tension in two components. T cos theta, T sin theta. But in reality, this is the tension. I'm saying in the downward direction, you have mg. And in this direction, you have electrostatic force. And in this direction, you have actually tension. Now, you guys say that, sir, this charge is in equilibrium. Tell me, what is the resultant of this one and this one? Guys. Previously, I told you if this force is F, this is F, angle is 90. This will be root 2F. But if this is different, this is X, this is Y. What will be resultant in that case? In that case, resultant will be, remember directly, resultant will be under root of this square, X square, plus this square, that is Y square. Please remember it directly. So similarly, can I say in this particular case, guys, resultant of this and this is R. So I can say R will be equals to under root of, that is Fe square plus mg whole square. Now. Since you say that the charge is in equilibrium, can I say that this force will be equal to this force? This side force is equal to this side force. So tension is equal to R is equal to under root of Fe square plus mg whole square. Guys, I would want you guys to tell me in the chats if this is crystal and clear to each and every single student. Come on, guys, tell me if this is crystal and clear. Give me the signal in the chats if everything is crystal and clear. Derivation of this was required. That's why I have shown you over here. Okay. Next you have a relative permittivity. Next you have relative permittivity. Great. Guys, take a look. When it comes to the relative permittivity, guys, see. Let's suppose I am saying you have got two charges over here. This is Q1 and this is Q2. And distance between the two charges, let's suppose R. Distance between the two charges is, let's suppose, R. Okay. And the two charges are placed in air. Okay. Cool. Now, guys, I am saying force between the two charges, force in air between the two charges is F. F is the force between the two charges, or F naught. What you are doing is that you are placing the same two charges. You are placing the same two charges in any other medium. Let's suppose it is water. Okay. This is Q1 and this is Q2. And you are placing the two charges at the same distance, that is R. The two charges are placed at the same distance, that is R. Yes. Now, my dear friends, I am asking you, what is the force in water? What is the force in water? Guys, apart from air, whatever the medium will be, if you want to find the force in that medium, always remember, you will be able to find with the help of this formula. Force in a medium is equal to force in air, free space, divided by relative permittivity. So what is this relative permittivity? Relative permittivity helps us to find the force in a medium. Like, my dear friends, for every medium, relative permittivity, it has the value of relative permittivity. Like, we say for water, relative permittivity is 81. For some other medium, it will be 75. For some other medium, it will be 65. Now tell me, what is the force in water? You say, sir, force in air, that is F naught, divided by relative permittivity of water, that is 81. So means force in this medium has been decreased by 81 times. Force in this medium has been decreased by 81 times. So can I say, from now onwards, relative permittivity, ER, this ER, relative permittivity, helps us to find the force in a medium. So it is something which helps us to find the force in a medium. Like, let's suppose if you have got a medium, its relative permittivity is 25. Tell me what is the force here. Sir, force in this medium will be force in air divided by 25. Simply. So for every medium, relative permittivity will be given. One more thing. We say relative permittivity is EM by E naught. So from here you can say permittivity of the medium is equal to relative permittivity into E naught. Guys, see, if somebody asks you, you find the force in this medium, you can find it is very easy now. If somebody asks you, find the permittivity of this medium, like permittivity of air. Guys, you say permittivity of air, it is 8.85 into 10 raised power minus 12 Coulomb square upon Newton meter square. This is permittivity of free space, permittivity of air, vacuum. But if you want to find the permittivity of this medium, how can you find the permittivity of this medium? That will be EM is equal to relative permittivity of this water, that is 81 multiplied by E naught, value of E naught you know. So can I say relative permittivity also helps us to find the permittivity of a medium? Yes, sir. So relative permittivity also helps us to find the permittivity of any medium. It also helps us to find the force between the two charges in that medium. Is this clear? Is this clear? There was a question which was asked in NEET 2020 in the concept relative permittivity. When air is replaced by a dielectric medium of force constant K, when air is replaced by a dielectric medium of force constant K, means relative permittivity. We have got a medium over here, and relative permittivity of this medium is given as K. It is given as K. The maximum force of attraction between the two charges separated by a distance C. You have got two charges Q1, you have got two charges Q2, and distances R. Could you please tell me, what is the force between the two charges here? You say force in this medium will be simply force in air divided by relative permittivity there, that is K. So means, can I say force has been decreased by K times in this medium as compared to the force in air? Like force has been decreased by 81 times in water as compared to the force in air. Similarly here, force has been decreased by K times in this medium as compared to the force in air. So what is the correct answer? So decreases by K times. So in this medium, force decreases by K times. Is this clear, guys? Tell me in the chats. I would want you guys to tell me if this is crystalline clear. Everyone means everyone. Who sir is watching, I would want you guys to tell me. For relative, the another name of relative permittivity is force constant. This is also ER. Force constant, relative permittivity, it's one and the same thing. It's one and the same thing. Now guys, take a look. Let's move on to the electric field. I would want you guys to understand one thing. See. Guys, let's suppose you have got a charge over here. Okay. And before this, could you please tell me one thing? What is that? That is, guys. Let's suppose you have got a magnet over here. Okay, this is a magnet. Okay. And my dear friends, let's suppose you place a coin over here. This is a coin. What is going to happen to this coin? It will be attracted towards the magnet. Let's suppose if you place the coin over here, it will be here attracted to the magnet. If you place the coin here, it will be attracted towards the magnet. If you place the coin here, it will be attracted towards the magnet. Now, can I say in this case, this magnet is creating some sort of field around it. This magnet is creating some sort of field around it. in which if any other piece of iron is placed, in which this coin is placed, it will be attracted towards the magnet. This field is what we call the magnetic field. Now, let's come over here. My dear friends, similarly, you can use the same logic. If you have a charge over here, okay, if you place another charge at this point, Q0, test charge, what do you think is going to happen? This charge will apply force on this charge. It will repel it in the outward direction. Let's suppose if you place the charge here, it will be repelled. If you place the charge here, it will be repelled. If you place the charge here, it will be repelled. If you place the charge here, it will be repelled. Don't you think that, my dear friends, this charge is basically creating some sort of field around it? This charge is creating some sort of field around it. If in that charge some other charge comes, it experiences the force. So this charge is creating some sort of field around it. If in that field, if you place any other charge, it will experience what? Force. And this field is what we call electric field. I say it is a space around a charge. It is a space around a charge, okay? In which if any other charge comes, it experiences the force. So from now onwards, my dear friends, whenever you see the charge, always remember it creates the electric field. If you ever see the charge, it creates electric field. If you place the charge on this rod, it will also create the electric field. If you place the charge on this on this board, it will create the electric field. Okay. Now guys, this is a positive charge. If somebody asks you what is the direction of positive charge, always say direction of electric field in case of positive charges away. Why? Because if you place a charge Q0 here, we said this positive will repel this Q0 in the outward direction. So we can say electric field of this positive charge is away from the charge. Electric field of this positive charge is away from the charge. If, my dear friends, you have a negative charge and you place a test charge over here, that is this plus Q0, we say this plus Q0 will be attracted. Hence, we conclude that the electric field of negative charge is towards the charge. So guys, if this is the positive charge, electric field is away from the charge. If this is negative charge, electric field is towards the charge. Relative permittivity for a metal or conductor is infinity. We say dielectric constant for a metal conductor, we take it infinity. I'll show you this also. Wait. Okay. So this is what we call the electric field. Now guys, let's suppose you have a charge over here. This is plus Q. Since this charge creates the electric field around it. Okay. My dear friends, at our distance, sir, how much electric field it will exactly create? We say it is K, this charge Q divided by R square. So electric field is inversely proportional to R square. Guys. Electric field due to a charge. Guys, if this is a charge Q, at R distance, how much is the electric field? K Q by R square. Q is the charge, R is the distance. If the charge is bigger, electric field will be large. So electric field is directly proportional to charge. Electric field is inversely proportional to R. As you go away from the charge, electric field will decrease. As you come close to the charge, electric field will increase. So that's why we say electric field versus R. If you make the graph, it is inversely proportional to R square. So it will be rectangular hyperbola. Okay. Now, my dear friends, now, my dear friends, now, my dear friend, let's suppose this is a very famous question that you need to answer in this particular case. Find the electric field at this particular point. Guys. I'm saying, you have a charge Q, you have minus Q, you have plus Q, you have minus Q. So these are the charges which are going till infinity. You have to tell me electric field because of all of these charges at the origin. Net electric field. Guys, since we know that if we have to find the net electric field because of all the charges, guys, you have a plus Q charge. This plus Q charge will create the electric field at the origin. You say, how much? If this is a charge, sir, at r distance, how much is electric field? KQ by r square. So because of this charge at r distance, it will be KQ divided by, what is the distance? This distance, that is 1 square, that is 1. Then we say minus. Guys, the electric field because of this, that is KQ divided by. From here to here, this is at what distance? 2 meter distance. So 2 square is 4. Then plus. Because of this charge, it is KQ divided by. From here to here, what is this distance? 4 square, that is 16. Now from here to here, this distance will be minus KQ divided by 8 square is 64. Then we say plus, and so on, and so on. Okay. Now, my dear friends, I can say in this particular case, net electric field is, take KQ common over here. KQ will be common. Then here it is 1, then minus 1 by 4. Then plus 1 by 16, then minus 1 by 64, then plus so on. Okay. Now, guys, I would want you to understand one thing. If I say net electric field in this case, guys, see. What is this? This is what we call the GP series. That is geometric progression, GP series. So basically you have to add all of these till infinity, you will get the answer. Guys, how do we add all of these terms? Guys, see. There is a formula, that is sum. Sum will be A upon 1 minus R. This is the formula which we use to add all of these, terms. Now, guys, what is this A? A means first term. This A means first term. And in this GP series, what is first term? That is 1. And what is this R? R means common ratio. And how do we find this common ratio? Guys. This common ratio you can find. Take any term. Let's suppose I'm taking 1 by 16. Divide it with the term which comes before it. That is minus 1 by 4. Okay, 4 ones are 4 fours are. So it will come out to be minus 1 by 4. Now let's find the sum. So sum in this case will be A upon 1 minus R. So A will be 1 upon 1 minus 1 by 4. So you can say over here, this is 1 upon, minus into minus is plus. So 1 plus 1 by 4. So sum in this case will come out to be, that is 4 into 1 is 4, 4 plus 1 is 5, 5 by 4, that will be 4 by 5. Now, guys, we have added this GP series. What is the formula? That is this. From now onwards, you'll be remembering this. And my dear friends, one more thing. How do you find the common ratio? Take any term, divide it with the term which comes before it. That's it. Now, so net electric field in this case will be, that is KQ. And guys, sum of all of this is how much? That is 4 by 5. So this is 4 by 5. So this will be 4 KQ Is this clear? Guys, is this clear? Please tell me in the chats. Everyone means everyone. Is this clear? Please tell me in the chats. And smash the like button if you have not liked the session yet. We'll take the break exactly at 2 p.m. Not before 2. Break will be exactly at 2. Now guys, take a look. Guys, I told you if there is a charge, it creates the electric field around it. Cool. And what is the electric field because of the charge? Sir, because of a charge, electric field at r distance will be kq by r square. Because of a charge, electric field at r distance will be kq by r square. As simple as that. As simple as that. Now, my dear friends, if you place that charge, if you distribute that charge on a rod, the rod creates electric field. If you place that charge on a ring, the ring creates the electric field. If you place that charge on something else, that something else will create the electric field. Now guys, let's suppose you have taken a ring over here. This is the ring. On this ring, you have distributed the charge. This is the charge which you have distributed on the ring. Okay. Now this ring will also create the electric field. So I'm saying radius of the ring is r. At x distance, guys, it is something like this. This is the ring. You have to tell me electric field because of this ring at x distance. At this x distance, ring is something like this. So because of this ring, electric field at x distance will be k, q, x. Q is the charge on the ring. X is the distance where you have to find the electric field upon r square plus x square whole raised power 3 by 2. R square plus x square whole raised power 3 by 2. R is the radius of the ring. Okay. Now guys, if I say, sir, at x is equal to 0. If I say at x is equal to 0, means center. Center at center x is equal to 0. If you go away from the center, we say x will increase. So if x is 0, put the value of 0 over here. 0 multiplied by this term will become 0. So electric field at the center of the ring is 0. Electric field at the center of the ring is 0. Okay. Okay. One more thing I want you guys to remember over here. Very far from the ring. Very far from the ring. Very far from the ring means where r is much less than x. Means if you have this ring, guys, if you have this ring, if you go very far from the ring, so x will be very large. This x will be very large. Guys, it is something like this. This is r, this is x. So this is r and this is x. X is very large as compared to r. In that case, what will be the value of electric field? Electric field will be simply kqx upon, guys, r square plus x square. When you have a very small quantity, r is very small as compared to x. So adding a very small quantity to a very large quantity, it will not create any difference. Why? Because if you are adding a bucket of water to the ocean, it will not create any difference. Ocean has got billions of liters of water. So it will not create any difference. So my dear friends, you can neglect this r. So you can directly write, sir, x square whole raised power 3 by 2. 2 and 2 will cancel. So it will become kqx upon, we say, x cube. This and this. So it will become kq by x. So at very far from the ring, if we are talking about, electric field will be kq by x square. Now, one more point. If I say very close to the ring, if I say very close to the ring, guys, this is the ring, this is the radius r, and this is x, this is r. Now, if this is a ring just outside of the center, very close to the ring, don't you think that in this particular case, I can say x is much less than r? Yes. If x is much less than r, guys, what is the thing that I need to neglect? I need to neglect x. So I'll neglect x in denominator. Don't neglect in numerator, okay? In multiplication, we don't neglect in denominator. So what can we write over here? So electric field will be kqx upon I can say this is r square whole raised power 3 by 2. 2 and 2 will cancel, so it will be kqx divided by r. So this is the electric field very close to the ring. And guys, very close to the ring, electric field is directly proportional to x. Very far from the ring, electric field is inversely proportional to x square. And guys, this is the graph between electric field versus x in case of the ring. This is the graph between electric field versus x in case of the ring. Guys, see, if this is a ring, electric field will increase, will become maximum. At what distance it is maximum? X is equal to plus r by root 2. So electric field in case of the ring is maximum at plus r by root 2. Remember this directly. And then it will again decrease. Guys. See, if this is a ring very close to the ring, electric field is directly proportional to x. It is a straight line actually. It's a straight line. And very far from the ring, electric field is inversely proportional to x square. And from this side also, electric field will be negative. That's why we are making from the negative side. So electric field is something like this, then something like that. It's a straight line. So electric field will be maximum at x is equal to minus r by root 2 and x is equal to plus r by root 2. Simple, guys. This is the ring. Because of this electric field will be from left side, right side, from left side. So left side, this is the graph, right side, this is the graph. As simple as that. Give me the signal in the chats. Is this clear till over here? Guys, is this clear till over here? Tell me in the chats. Is this clear? Smash the like button if you have not liked the session yet. Guys, take a look over here. Let's suppose I am saying you have got this ring over here. This is a complete ring. Sir, can I say this will be the semicircular ring? Yes. Sir, can I say this will be the chord? Yes. So in a complete ring, you have 4 chords. 1, 2, 3, 4. In a complete ring, you have 2 semicircular rings, upper part and the lower part. Okay. And if somebody says, what is segment of ring? Segment of ring means some part of the ring. Cut this ring here and here. So this will be the segment of a ring. This will be the segment of some part of the ring. Now take this segment and place over here. Okay. Guys, if you join this point with center, this point with center, I know this is radius. This will be radius of the ring. Yes. Similarly, this is a segment of ring. Distribute the charge on this segment of ring. Place the charge over here. Okay, that is Q. And my dear friends, I am saying, this will be the radius. This is the radius. This is the center. So because of this ring, how much is the electric field at the center? I told you, if there is a ring, on the ring we say the charge is distributed. So because of this charge, electric field will be present. So electric field will be created. So at this point, because of this segment of ring, electric field will be 2k lambda by r sine of theta by 2. Guys, 2k. K is what? K is Coulomb's constant. Sir, what is this lambda? Lambda is what we call the charge per unit length. Charge per unit length. This lambda means total charge divided by total length. If you have this rod over here, okay, if you have this ring over here, it has length L. On this length L, how much charge is present? Q. If somebody wants to ask you what is the charge on its unit length, that will be lambda. Lambda will help us to find the charge on its unit length. How? Q by L, total charge by total length. That is Q by L. So we say 2k lambda by r. R is the radius. Sine of theta by 2. Theta is the angle between, join this point with one end of the rod of the ring, join this point with another end of the ring. So this angle is what we call theta. This is what we call the theta. I can say this is the electric field because of a segment of a ring. This is the electric field due to a segment of a ring at r distance, at the center, this is the electric field because of a segment of a ring at its center. Now guys, let's suppose I am taking a semicircular ring. Guys, join this point with one end of the ring. Join this point with another end of the ring. Angle between these two, I guess this is 180 degrees. Like here, angle between this line and this line is theta. Here, theta is 180 degrees. So if I am saying theta is 180, what is the electric field? Guys, use this formula. Use this general formula. That is 2k lambda by r sine theta by 2. We say electric field is 2k lambda by r. Then I am saying sine of theta by 2. Can I write this electric field will be 2k lambda by r sine of theta. Theta is how much? That is 180 divided by 2. That is 90. Sine 90 is 1. So electric field will be 2k lambda by r. So because of a semicircular ring, electric field is 2k lambda by r. Electric field is 2k lambda by r. Let's talk about chord. Electric field because of a chord. Guys. Join this point with one end of the ring. Join this point with another end. So how much is the angle over here? Theta in this case is 90 degrees. What will be the electric field? Electric field is 2k lambda by r. Because we are using the general formula. Then I am saying sine of theta by 2. That is 90 by 2. That is sine 45. So electric field will be 2k lambda by r. Sine 45 is 1 by root 2. Guys, do the rationalization. Multiply with root 2 and divide with root. Now guys, see. Root 2 into root 2. We say root 2 into root 2. This will be root 2 whole square. This and this will cancel, so it will be 2. So root 2 into root 2 is 2. Guys, root 2 into root 2 is 2. So this 2 will cancel with this 2. So electric field will come out to be, guys, take this root 2 here, root 2 k lambda by. So electric field because of a chord is root 2 k lambda by r. Electric field because of a semicircular ring is 2 k lambda by r. Electric field because of a semicircular ring is 2 k lambda by r. Electric field because of a chord is a root 2 k lambda by r. Root 2 k lambda by r. Okay. Okay. Now, take a look at this question. Find the electric field at the center. Guys. When you have a figure something like this, okay, do one thing. Divide this figure into 4 chords. Divide this figure into 4 chords. Okay. Now, guys, this chord has positive charge. This has negative. This has negative. This has negative. I have told you electric field because of the positive charges away from the charge. Electric field because of the negative charges towards the charge. See, guys, electric field because of this positive charge is away from the charge. Okay, let's call this E. Electric field because of this negative charge, this is E. Electric field because of this negatively charged chord, it is towards the charge. It is towards the charge. And guys, instead of E, I'll write how much is the electric field because of the chord? That is root 2 k lambda by r. Because of this chord, it will be towards this charge, but how much? Root 2 k lambda by r. Electric field because of a chord is root 2 k lambda by r. Because of this chord, it is root 2 k lambda by r. Because of this chord, it is root 2 k lambda by r. Okay. Now, electric field because of this chord will be towards the chord. Electric field because of this chord will be towards the chord. This and this will cancel. So if I say net electric field, guys, that will be this electric field plus this electric field. Root 2 k lambda by r plus root 2 k lambda by r. Now this is 1 plus 1 is 2. So this will be 2 root 2 k lambda by r. Is this clear? Next, let's talk about this one. Guys. Here in the upper part you have positive charge. In the lower part you have negative charge. So divide this in 2 semicircular rings. So upper part of the chord, because of this semicircular ring, electric field is away from the ring. And how much is the electric field because of the semicircular ring? 2 k lambda by r. So I can say electric field because of the upper portion, it is 2 k lambda by r. Electric field because of the lower portion, it is 2 k lambda by r. Okay, because of the lower portion, it is towards the charge. Because of the upper portion, it is away from the charge. So I can say net electric field will be, guys, this plus this, that is 2 k lambda by r, because two vectors are in the same direction, plus 2 k lambda by r, that will be 4 k lambda by r. Is this clear? Is this clear? Okay, now guys, let's talk about this one. Let's suppose we have a semicircular ring. We have a semicircular ring. Okay, we have a semicircle. We'll take the break at 2 o'clock exactly. And here, half of this semicircular ring has got positive charge. Half of this semicircular ring has got negative charge. Half of the semicircular ring has got positive charge. Half has got negative charge. Guys, see. In this case, let's suppose the radius of this ring is r. In this case, guys, I want you to divide this in two chords. We say this chord will have electric field towards the charge because of the, if you have negative charge, electric field is towards the charge. In case of negative charge, we say electric field is towards the charge. So because of this chord, electric field is towards the chord. Because of this charge, electric field is away from the charge. Guys, if this is a chord, how much is the electric field because of chord? Root 2k lambda by r. How much is the electric field because of this chord? Root 2k lambda by r. And this angle over here is 90. Guys, tell me, if you have two vectors which are at 90 degrees and similar, if this is f, this is f, resultant will be root 2f. If this is x, this is x, resultant will be root 2x. Now guys, if this is root 2k lambda by r, this is root 2k lambda by r, resultant will be 2, or I can say something like this, root 2 of root 2k lambda by r. Guys, because if this is x, resultant is root 2x. If this is y, resultant is root 2y. If this is root 2k lambda by r, resultant will be a root 2 of root 2k lambda by r. Root 2 into 2 is, root 2 is 2k lambda by r. And direction is towards right. Direction is towards right. And direction is towards right. Okay. Direction is towards right. Okay. Great. Now guys, we have got a rod exactly over here. See guys, we have got a rod exactly over here in this particular case. And the charge on this rod is Q. Q is the charge distributed on the rod. Now, my dear friends, in this particular case, you have to tell me, sir, if the charge is present on the rod, this rod will also create electric field. You have to tell me electric field because of the rod at this r distance, And at this point, if you join this point with one end of the rod, this angle we say theta 1. If you join this with another end of the rod, this angle we say theta 2. So electric field at this point will be K lambda by R. R is the distance, lambda is charge per unit length. Sine of theta 1 is this angle, plus sine of theta 2, plus cos of theta 1 minus cos of theta 2. This will be the electric field. This is the electric field because of the rod at arbitrary point, general point. Next, guys, if you say electric field because of the same rod at this equatorial position means at the center position. half of the rod is from upper side, half of the rod is from lower side. And when it comes to this equatorial position, guys, always remember, we say theta 1 is equal to theta 2. This angle is equal to this angle. Guys, in this case, directly I want you to remember, electric field because of this rod at this point will be 2k lambda by r sine of theta. 2k lambda by r sine of theta. 2k lambda by r sine of theta. So we say it is 2k lambda by r sine theta. Sir, when it comes to the general point, equatorial point will be somewhere around over here. General point. This is the general point. This is the electric field because of equatorial point. One more thing. Guys. If you have the infinitely long rod, the rod is going till infinity. You have to find the electric field because of this rod at point P. Then directly say electric field at point P will be 2k lambda divided by r. 2k lambda by r. Okay, my dear friends, I am saying like in this particular case, I told you first, electric field because of the segment of ring, 2k lambda by r sine theta by 2. Then I told you electric field because of a semicircular ring, that is 2k lambda by r. Then I told you because of the chord, root 2k lambda by r. Similarly, if you put this charge on a rod, it will also create electric field. At r distance, electric field is this. Okay, at arbitrary point. Then at equatorial point, electric field is this. Equatorial means center point. Okay. Then my dear friends, we say electric field because of infinitely long. This rod is going till infinity. It is going till infinity. It is 2k lambda by r. And my dear friends, electric field because of semi-infinite rod. If you have a semi-infinite rod, charge is placed on it, and one end of the rod is finite, it is here. Another end is going till infinity. It is going till infinity. So because of this rod, I can say electric field is root 2k lambda by r. Electric field is root 2k lambda by r. Keep that thing in your mind. I hope this is clear. Simple, very simple. Let's suppose there was a question which was asked in NEET 2019. Guys, see. You have an infinitely long rod. Charge on this is positive. Charge on this rod is negative. You have to tell me what is the electric field at the center. Guys, tell me. Electric field because of the negative charge is always towards the charge. So electric field because of the negatively charged rod. Electric field because of the positive charge rod is always away from the charge. Okay, that is positive. Now, when it comes to the net electric field at the center, guys, what will you say? Electric field because of negative plus electric field because of positively charged rod. Because both are in the same direction, that's why I'm adding. And because of the positively infinitely charged rod, guys, because of this rod, it will be 2k lambda by r plus, because of this also it is 2k lambda by r. So it will be 4k lambda by r. Why? Because of an infinitely long rod, electric field is 2k lambda by r. Okay. I hope this is clear. Now, guys, now we have the electric flux. What is electric flux? Guys. Electric flux simply means number of electric field lines crossing the surface perpendicularly. Like if you place a sheet over here, guys, you are placing a sheet over here, okay? And you place a charge over here. Because of the charge, electric field will basically come out. And that electric field will cross this sheet. Now, if I am saying three field lines are crossing the sheet, three field lines are crossing the sheet, I can say in that particular case, flux is 3. Why? Because flux means the number of field lines crossing the surface. So through this surface, flux is 3. If I say 4 lines are crossing, so means flux is 4. Number of field lines crossing the surface will be flux. Okay. And guys, we say flux is directly proportional to electric field. More number of field lines will cross, flux will be more. Sir, flux is directly proportional to area. If you place the bigger area over here, the chances will be that more field lines will cross. So flux will be more. So flux is directly proportional to EA. So we say simply if flux is proportional to EA, so I can say flux is equal to E dot A. Okay. More is the electric field, more is flux. More is area, more is flux. Or we also say flux is equal to EA cos of theta, where theta is the angle between electric field and area. Where theta is the angle between electric field and area. So simply, my dear friends, from now onwards, you'll remember that flux is defined as the number of electric field lines crossing the surface perpendicularly. That's it. Now, guys, take a look. Gauss law. Gauss law. What does Gauss law exactly say? Guys, let's suppose you have a cylinder over here. Okay, this is the cylinder that you have. Inside the cylinder, you have placed a charge. And we know that, sir, because of this charge, field lines will come out, because whenever you have charge, it will create electric field. Because of this charge, electric field will come out. This is the electric field coming out because of the charge. Now, if this charge is placed inside a cylinder, these field lines are crossing the walls of the cylinder. These field lines are crossing the walls of the cylinder. Okay. My dear friends, if these field lines are crossing the walls of the cylinder, then we can say flux is being produced. Flux is being produced. Why? Because whenever the field lines cross the walls, cross the surface, flux will be produced. Flux will be produced. So my dear friends, if somebody asks you, how much is the flux through this closed surface? Sir, you have placed the charge inside, field lines are coming out, so flux is produced. How much is the charge through this closed surface? You will simply say, sir, flux through any closed surface, is equal to the charge inside, charge enclosed upon epsilon naught. That is Q inside by epsilon naught. Means, if this is a closed room, you have placed a charge inside this closed room, then field lines will go out of this closed room. How much will be the flux through this closed room? That is Q inside by epsilon naught. This is called Gauss law. Flux through any closed surface is Q by epsilon naught. Now guys, this is a cube. Could you please tell me how much will be the flux through this cube? Sir, simply flux through this cube will be Q by epsilon naught. If let's suppose I'll place 10Q, then flux through this cube will be 10Q divided by epsilon. Whatever is the enclosed charge, flux will be enclosed charge divided by epsilon. Okay. And my dear friends, let's suppose before this question, let me show you this one. This is the hemispherical bowl. Curved part. Wait for this. Let me show you this first. Yeah. Guys. If I say charge is present inside, how much will be the flux through the cylinder? You say, sir, Q divided by epsilon. But right now, charge is placed at the mouth. This is a cylinder. It is something like this. Guys, see. You have a cylinder over here. charge is placed at the mouth of the cylinder. Okay, charge is placed at the mouth of the cylinder. You are supposed to tell me how much will be the flux through this cylinder. Charge is not enclosed over here. Guys, here charge is not enclosed. Here charge is not enclosed. Let's do one thing. Let's do one thing. Guys, I'm taking the same cylinder. I'm taking the same cylinder. If this charge is over here, let's do one thing. We will attach an imaginary cylinder. We will attach an imaginary cylinder to it. Let's consider this is an imaginary cylinder, or let's consider one more cylinder. Now, this Q charge becomes the enclosed charge for these two cylinders. Now, this is the closed surface. This is the closed surface. Now tell me, guys, closed surface here is two cylinders. For this charge, closed surface is how many cylinders? Two. So can I say flux through a closed surface will be here? Flux through two cylinders will be, that is Q divided by epsilon naught. So flux through two cylinders is Q by epsilon naught. Flux through one cylinder will be, take this 2 over here. So I can say flux through one cylinder will be Q divided by 2 epsilon. As simple as that. As simple as that. Now, let's suppose I say this one. I say this one. The charge is placed at the mouth of the hemispherical bowl. Guys, tell me one thing. We have to find how much is the flux through the bowl. Let's do one thing. Attach one more bowl to it. Attach one more bowl to it. Now, can I say flux through the closed surface here? For this charge, closed surface is how many bowls? This bowl, this bowl. So means that is flux through two bowls. Okay. So flux through closed surface, or you say flux through two bowls, that will be Q divided by epsilon. Now can I say flux through one bowl? Flux through one bowl, that will be Q divided by 2 epsilon. As simple as that. Take a look at this question. Is this clear? Is this clear? Guys, tell me. Is this clear? Guys, give me the signal in the chats and smash the like button if you have not liked the session yet. Give me the signal in the chats. Is this crystalline clear? Whosoever is watching, I want you guys to tell me in the chats. Is this crystalline clear? Great. Now guys, take a look. Take a look. Flux passing through R is phi. Okay. Guys, see. In this particular case, this is the surface P, this is the surface Q, this is the surface R. Means what I'm trying to say here is, you have got a cylinder. You have got a cylinder. This is the cylinder. How many surfaces are there in a cylinder? This one, curved surface, plane surface, plane surface. There are 3 surfaces in case of the cylinder: plane, plane, curved. If I say, what is the net flux through this surface? Q by epsilon naught. Now, what if I say, what is the flux through this one surface, this one plane surface? Guys, you will say, here, when it comes to the closed surface, guys, flux through closed surface, that will be flux through one curved surface plus flux through two plane surfaces. Guys, this closed surface is made up of three surfaces: curved, plane, plane. So I can say flux through a closed surface will be flux through one curved surface plus flux through two curved surface. Now tell me, how much is the flux through a closed surface? That is Q divided by epsilon naught. Okay, is equal flux through curved surface. Flux passing through R. R is this curved surface. R is this curved surface is phi. This is given as phi. Plus flux through two plane surfaces. Now take it over here. So I'll write Q divided by epsilon naught minus, I can say phi, is equal to, this will be flux through two plane surfaces. So because of the two planes, flux through two plane surfaces this much. So now if somebody asks you, how much will be the flux through one plane surface? One plane surface. What will you say? Sir, because of 2 it is this. So take this 2 here. So it will be 1 by 2 of half of this much. So that will be Q divided by epsilon naught minus phi naught. Guys, because of two surfaces, flux is, let's suppose, 10. Because of 1, it will be 5. Half of 10. So 1 by 2 of Q by epsilon naught minus this phi. I hope this is crystal and clear. I hope this is crystal and clear. Okay. This I'll give you as homework. Do let me know the answer of this in the comments. Okay. Take a look. Electric field due to a hollow sphere. Guys, please understand this. I have told you, if we take a charge, we place this charge on the rod will create electric field. If we take the charge, we place it on the ring, it will create electric field. Now, if we take the same charge, you place on the sphere will also create the electric field. Now, what I'm trying to say is, electric field due to a hollow sphere, or we also call it metal sphere or conducting sphere. Now guys, see, I am taking a sphere over here. This is the sphere, cool. And on the sphere, you are placing the charge. Q charge. Will it create electric field? Yes, it will create electric field. Why? Because charge is present on it. Now, if it creates the electric field, you have to tell me electric field because of this sphere at outside point. Sphere outside the sphere. Point number 1. You have to tell me the electric field because of the sphere on the surface. Point number 2. You have to tell me electric field because of the sphere inside the sphere. Point number 3. Guys. When it comes to outside point at small r distance, small r is variable. At outside point, electric field is KQ. Q is the charge on the sphere divided by r square, small r square. Small r is the distance where you have to find the electric field. E is inversely proportional to r square. Now, if you talk about the surface, guys, decrease the small r. At center, small r is 0. At surface, don't you think that value of small r will be equal to capital R? Value of small r will be the radius? Yes. So, use the same formula. KQ divided by, instead of small r, we'll be writing capital R square. Capital R square. I hope this is clear. Then, guys, when you talk about inside, guys, in case of hollow sphere, charge is stored on the surface. So inside charge is 0. Keep that thing in your mind. Q inside is 0. If there is no charge inside, do you think that there will be electric field? No. So I can say electric field inside will be 0. So inside electric field is 0 because there is no charge. Now let's make the graph. Guys, inside electric field, graph is electric field versus small r. Inside electric field is 0 till the surface of the sphere. Then at the surface, electric field is kq by capital R square. kq by capital R square. Okay. And then outside the surface, electric field is inversely proportional to R square. So outside the surface, electric field is, I can say electric field is inversely proportional to R square. Okay, this graph is very important. So it is something like this. Don't get confused. Till the surface, R is equal to R, electric field is 0. Then we say electric field is inversely. Okay. Okay. Now guys, let's talk about the solid sphere. Guys, solid sphere means the non-conducting sphere. You have a solid sphere. In real life, you might have seen the football. Football is hollow sphere because inside nothing is present. And cricket ball is a solid sphere. Similarly, here, when it comes to the solid sphere, we say charge is stored in its volume. Charge is stored inside also, surface also. In case of a solid sphere, charge is present inside also. So it will create electric field. We have to find electric field because of this at outside point. At outside point. At small r distance. We have to find electric field on the surface, capital R distance. We have to find electric field inside. Inside at what distance? Small r. Sir, small r is variable. Yes. For outside point, small r is greater than capital R. For inside point, small r is less than capital R. Now, see. Guys, when it comes to the outside, we say electric field is kq by small r square. Exactly this. Because at very far distance, we consider it the point charge. Electric field outside point. Now guys, at surface, don't you think that value of small r is capital R? Value of small r is capital R. So at surface, I can say electric field is kq divided by, instead of this small r, you will be writing capital R square. Okay. Now guys, when it comes to inside charge is present. Previously, we said in case of hollow sphere, no charge is present inside. So we considered electric field 0. But right now, electric field is present inside. So electric field inside will be, that is kq into small r, kq into small r, divided by capital R square, capital R cube. Capital R is the radius, small r is the distance where you have to find the electric field inside. This is the electric field inside in case of a solid sphere, And clearly you see electric field inside is proportional to small r. And here you see electric field outside is inversely proportional to small. Now, if we try to make the graph, guys, inside the sphere, electric field is directly proportional to small r. So from this origin, graph will be the straight line. Till what? Till the surface. So this is the surface where r is equal to capital R, where small r is equal to capital R. This is inside graph. Outside graph will be, guys, outside graph will be electric field is inversely proportional to small r square. Because as you go away from the surface, we say electric field will decrease. So this graph is also very important. This graph is also very important, previous graph. So this was the electric field because of hollow and solid. Now there is a question, very important question. It's a NEET level question. It's a NEET level question. Okay. Because when it comes to the we consider it non-conducting. When it comes to the solid, charge is present inside. In case of a conducting surface, we always consider the charge on its surface. That's why. Now guys, see. In this particular case, you have a sphere. Guys, all the three are solid spheres. You have to find the electric field at point P. This point P is outside of the sphere. Cool. This point P is surface, on the surface. Here point P is inside. Why? Radius of this is r by 2. Radius of this is r. Radius of this is 2r. Guys. Let's find the electric field here, E1. Guys, this is a solid sphere. Is this point P outside point or inside point? Outside point. So I can say, for this point, which formula I am supposed to use? Electric field because of a solid sphere outside, kq by small r square. So I will use electric field here will be kq divided by small r square, and small r means at what distance you are finding. Here small r is equal to capital R because its radius is capital R by 2. It will be this, or you can write it something like this: E outside kq by small r square. It will be kq divided by r square. Let's call this as E1. Now, if somebody wants you to find out electric field here, just tell me one thing. When it comes to this, don't you think that this point is the surface point? So in case of a solid sphere, what is the electric field on the surface? kq by r square. So can I not use the same formula? So I can say electric field E2, that is kq divided by capital R square. Guys, here capital R is capital R. So I can say capital R square. Okay. And charge here is 2q. So I'll have to write twice kq divided by capital R square. This is E2. Cool. Now, tell me. When it comes to this sphere, don't you think that this point is inside point? And in case of inside point, we recently got electric field is kq small r divided by capital R cube. So I can say here, guys, E3 is equal to kq small r divided by kq small r divided by capital R cube. Now tell me, guys, this is k. What is the value of q? That is 4q. What is the value of small r? Small r is the distance inside, that is capital R. Divided by radius of this, that is 2r whole cube. So this will be 4kqr divided by 2 cube is 8r cube. This 4 ones are 2s are. So it will come out to be kq upon 2r kq upon 2r square. Is this clear? Is this clear? So this is the electric field outside point, surface point, inside point. This is a very good question and very important question. Okay. Yes. Okay. Now guys, take a look. See, electric field due to an infinitely large non-conducting plate. I told you, if we distribute the charge on the rod, it creates electric field. If we distribute the charge on sphere, it creates electric field. If we distribute the charge on a sheet, if we distribute the charge on a sheet, on an infinitely large non-conducting sheet, okay, like this, positive, 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 positive. Now, my dear friends, because of this sheet, electric field will be produced. Why? Because it has got charge. How much is the electric field because of a sheet? Sir, it is sigma divided by 2 epsilon naught. Now, what is this sigma? I'll tell you. Guys, when it comes to this sigma, you say this sigma is what we call the charge per unit area, or we say surface charge density. Guys, if I am saying you have got a sheet over here, on this sheet we say Q charge is present. Area of the sheet is A. I'm saying, what is the charge present on the unit area? Sir, on unit area, sigma will help you to find the charge. This sigma is equal to total charge divided by total area, Q by A. This sigma is total charge by total area. So I can say this sigma is Q divided by A. Like lambda. Lambda helps us to find the charge on a unit length. Sigma helps us to find the charge on the unit area. Now, I'll write in terms of charge. Can I say, guys, I'll write E is equal to, instead of sigma, I say Q divided by, here I'll write 2A epsilon. Because sigma is charge per unit area, Q divided by A. Okay, so it is Q by 2A epsilon naught. So this is, guys, always remember, this is the electric field due to an infinitely non-conducting sheet. Because of the non-conducting sheet is sigma by 2 epsilon naught. Now, guys, let's talk about electric field due to a conducting sheet. Sir, what is the difference between conducting and non-conducting? Here it looks like there are two sheets. Okay, in between this here, no charge is present. Here, Q inside is equal to 0. So charge is it is basically one sheet, another sheet. So this is we consider as a non-conducting. Charge on this side, charge on this side. And in between there is a gap. Now, because of the non-conducting sheet, at point P, if you want to find the electric field, it is sigma by epsilon naught. This is a conducting sheet. Because of a non-conducting sheet, it is sigma by 2 epsilon naught. Because of conducting, it is sigma by epsilon naught. Now tell me, guys, if I say, what is the value of sigma here? Sir, sigma is total charge divided by total area. And we say sigma is, what is the total charge distributed here? That is Q. What is the total area? Area is 2A. Because area of this sheet, area of another sheet. Here, Q charge is distributed on A and A. In the previous case, Q charge is distributed on this area only, on 1A only. So I can say, sir, instead of, I can say in terms of charge, this electric field will be, instead of sigma, I say Q divided by 2A epsilon. Guys, if you take a look, in terms of charge, electric field because of conducting and non-conducting, is exactly same. Okay. So here we say In terms of charge, electric field because of conducting and non-conducting is same. But in terms of sigma, it is different. Why? Because density of charge here is different. Density of charge here is different. Why? Because here charge is present on one sheet only. Here the same charge is present on two sheets. Is this clear? Please tell me in the chats. Everyone means everyone. Tell me, guys. Is this clear? Is this clear, guys? Now, guys, let's suppose you have two parallel non-conducting sheets. So this is one sheet, this is another sheet. Okay. You are supposed to tell me find the electric field at A, B, and C. Okay. Here, electric field at this point, electric field at this point, electric field at this point. This is point A. This is point A. This is point B. And this is point C. You are supposed to tell me electric field at this point, and this point. At all the 3 points, you have to tell me electric field. Okay. Okay. Guys, see. This is one sheet. Or I'll make it something like this. This is a sheet. I'll make it something like this. This is a sheet. This is a sheet. Okay, infinitely long sheet. Guys. When it comes to electric field because of this sheet at this point. Sir, how much will be that? First of all, tell me, at which point electric field will be zero? At which point electric field will be zero? Sir, at this point, electric field because of non-conducting sheet, this is a negative, minus sigma. So electric field is negative. So here charge is negative. So electric field will be towards the sheet, and that is E, electric field due to the negatively charged sheet. And electric field because of this positively charged sheet, at point C, it will be away from the sheet, electric field due to positive. Sir, will these two electric fields be equal? Since point C is very far from this sheet, these two will be equal. Why? Because this electric field does not depend upon the distance. Electric field does not depend upon the distance. This is an infinitely large sheet. If you take point here, it's one and the same thing. If you take here, it's one and the same thing. It's infinitely large. So for infinitely large, all the points here, there, it will be same. So I can say in this particular case, net electric field here will be zero. Why? Because this electric field will cancel this electric. Now tell me here at point B, electric field because of non-conducting, because of this negatively charged sheet, it will be towards the sheet. Electric field because of positively charged sheet, this is positively charged sheet, it will be away. So here, this is electric field because of negative, electric field because of positive. In this case, I can say electric field is not equal to zero. Okay, electric field is not equal to zero. Now, my dear friends, let's talk about this one. Let's talk about this one. Electric field because of positively charged sheet away from the sheet. Electric field because of negatively charged sheet towards the sheet. Again, electric field net at point A will be zero. Guys, what I'm trying to say is that if you have a sheet, if you take this point or this point, provided this is infinitely large sheet, electric field at both the points will be same. So we say here 0, here 0. Okay. And how much? Guys. Electric field at this point will be Sigma by 2 epsilon naught. Because of non-conducting Shinga, how much is it? Is it sigma by 2 epsilon naught? So at this point, sigma by 2 epsilon naught, sigma by 2 epsilon naught. Here, sigma by 2 epsilon naught, sigma by 2 epsilon naught. It will be exactly similar. I hope this question is clear. Because electric field does not, because of the sheets, infinitely long sheets, does not depend upon the distance. Okay? Yes. Now, I would want you guys to focus on this particular point over here. I would want you guys to focus on this point. See, motion of a charged particle in uniform electric field parallel to the field. Guys, see. Let's suppose I'm saying there is an electric field over here. Sir, how does this electric field come over here? Let's suppose you have placed a charge. Because of this charge, electric field is created over here. Electric field is created over here. Okay. And in that electric field, you have placed a charge. This charge has charge Q. It has mass M. Always remember, whenever you place a charge in an external electric field, it experiences force. Force is applied on it. This electric field will apply force on it. And that force is equal to Q times of E. Q is the charge, E is the electric field. Now, if we say force acts on anybody, you have a mass, we say force is acting on it, acceleration will be there, force divided by mass. Now guys, if you are applying force on it, it will have acceleration. So that acceleration is Q E divided by M, force by mass. Q is the charge, E is the electric field, M is mass. Guys, see, one more thing. If acceleration comes, force is applying. Now, don't you think that now this charge will start moving in the forward direction? Yes. So when it starts moving because of the force, so it will gain some velocity. And that velocity we say is Q E divided by M into T. So after time T, this is the velocity of the charge. This is the velocity gained by charge. If force is acting, it will start moving. So after time T, how much is the velocity of the charge? That is QE by M into T. QE by M into T. Okay. Now, let's suppose, sir, after time T, it has gained some velocity. It has covered also some displacement. It has moved some displacement. So displacement after time T, call this as velocity after time T. Velocity after time T. Now, this is displacement after time T. This will be 1 by 2 QE by M into T square. Because initial velocity we consider 0. So this is the displacement. And guys, if you take a look over here, velocity is directly proportional to time. And if somebody asks you the graph between V and T, this is the graph between velocity and time. If somebody asks you the graph between S and T, so S is proportional to T square. So displacement and time, this will be the graph. Okay. Now guys, we say, since the charge is in motion, charge has got mass, it has got velocity, so it will have momentum. If there is a mass which has velocity, which is in motion, so it will have momentum. So momentum of the charge, momentum after time T is charge, electric field into time, QET. This is the momentum. T is directly proportional to time, graph is straight line. Okay, guys. Kinetic energy after time T. Guys, if I say you have a mass, this mass is moving with some velocity, it will have kinetic energy. That is 1 by 2 mv square. Similarly, if this charge is moving, it's in motion, it will have kinetic energy. So its kinetic energy is Q square, E square, T square divided by 2m. Q is the charge, E is the electric field, T is time, M is mass. So this is, I say, kinetic energy after time t. Kinetic energy after time t. Okay. Now. This is velocity after displacement x. Velocity after displacement x. Guys. Let's suppose I'm saying the charge has started from this point and it reached this point. It has covered the displacement x. What is the velocity of the charge after displacement x? Sir, what is this? This is the velocity of the charge after time t. This one is the velocity of the charge after displacement x. That is 2 QE by m into x. Okay, so you can take this root over there, under root of 2 QEm into x. This is the velocity. I hope all of these points are clear. One more thing. Guys, in this case, charge is moving in an electric field parallel to electric field. Electric field is forward, this is forward. But, if electric field is upward, direction of electric field is upward, I'll give the break at 2 o'clock. If the direction of electric field is upward, this is the electric field, okay? And you have placed the charge in it, its mass is m. Guys, in this case, electric field will apply force on it in the upward direction. Always remember, if you have electric field, if you place a charge in it, if it is positive, force acts on it in the forward direction, okay? If the charge is negative, force will act in the opposite direction. Keep that thing in your mind. Now, charge is positive, force acts in the opposite direction. Guys, this charge was supposed to go straight, but because of it was supposed to go straight, but because of the upward force due to the electric field, it will deviate its path and it will come out at this angle. It will come out at this angle. And here this angle is theta. This angle is theta. Charge was supposed to go straight, but due to the electric field, force is acting on the charge in the upward direction. So it is deviating from its path. So it will come out at an angle theta. Okay. This is the final velocity v. Guys, see. This is the distance in which electric field is present. D distance. Electric field is present in d distance. U is the initial velocity. Electric field is present in the d distance. Okay. Charge multiplied by electric field. Now, my dear friends, see, this theta is the deviation. This deviation is equal to tan inverse of QED. This is QED. Q is the charge, E is the electric field, D is the separation between this, or we say D is the region in which electric field is present. One of my very close friend is in the chats, ER Wasim Raja, physics expert, very good friend of mine. What's up, bro? How is everything going? Thank you. Means a lot. Thank you so much. Okay. Now, my dear friends, in this particular case, I'm saying electric field is present in this region. Okay. So that is the D region. If you want to find out this deviation, we say it is simply tan inverse of QED upon mu square. Okay. And this is the important relation that we have exactly in this particular case. Okay. So if you take a look, this theta is directly proportional to the charge. If charge is more, we say electric field will apply more force on it in the upward direction. So we say it will deviate more. So deviation will be more. Okay. Theta is directly proportional to electric field. Once again, the same thing. If electric field is more, force will be more, deviation will be more. Why? Because force is equal to Q times of E. Okay. And if this distance is more, this separation is more, we say charge has to basically remain for the more time in this electric field. So it will keep on deviating. So deviation will be more. And this deviation is inversely proportional to mass. If mass is more, it will be difficult for the electric field to deviate this greater mass. So deviation will be less. Similarly, if velocity is more, deviation will be less. If you send this charge with a greater velocity, it will come out very quickly. So deviation will be less. This equation is very important in this particular case. Before all of this, let me show you a question which was asked in NEET 2019. This was the question which was asked in NEET 2019. Okay, see, you have got an electron, okay, and there is an electric field over here. Electric field is something like this. Now guys, you have released this electron from certain height. This electron is falling, okay, and in the similar electric field over here, you have a proton. You are releasing this proton and it is falling in this particular case. This electric field is upward direction. Electric field is upward. You have an electron. You release this electron, it is falling down. So how much time it is taking in falling, that is time of electron. You have a proton. You are releasing the same proton, this proton in the same electric field, but the direction of electric field is opposite. And how much time it is taking? Time of fall of proton. You have to compare. And this is a gravity-free space. Find the time of fall of electron in comparison to the time of fall of proton. Basically, you have to compare which one is going to take more time or less time. Will this take less time or more time? Is this going to take less time or more time in falling? Guys, see, we say use S is equal to ut plus 1 by 2 at square. Use this equation. If you are releasing this, initial velocity is 0. And how much displacement it is coming down? Let's suppose it is h. How much displacement it is coming down? Let's suppose it is h. So I am saying this displacement is h, initial velocity is 0, 1 by 2. How much is the acceleration of a charge in an electric field? That is QE divided by m. So I can say this is QE divided by m into, we say, t square. Guys, tell me one thing. Take this 2m over here. So it will be basically 2mh divided by QE is equal to t square. Guys. Take a look at both of these two cases. See. Sir, mass is different. Okay. 2 is constant. Height. If this is coming h height down, this is also coming h height down. So height in both the cases is same. Sir, electric field. Magnitude of electric field is similar as compared to magnetic field over here. Electric field is same. Here electric field. Okay. But direction is opposite magnitude wise, I am saying. Charge on electron is same as charge on proton. Just charge on proton is positive, charge on electron is negative. Magnitude wise same. But t square is proportional to m. Here t square is proportional to m. So t is proportional to root m. So the one which has got more mass will take more time. Now tell me guys, can I say here mass of electron is less than mass of proton? So I can say time of fall of electron is less than time of fall of proton. So electron will take less time, proton will take more. Is this clear? Please tell me in the chats. Give me the signal in the chats. Is this clear, guys? With the fire emojis. Is this clear? Okay. Now guys, take a look. If proton, deuteron and an alpha particle are placed in an electric field, find the ratio of their momentum after time t. Guys. When it comes to proton, deuteron and an alpha particle. Okay. Proton, deuteron and alpha particle. You have got proton. Okay. You have got deuteron and you have got an alpha particle. Okay. Guys, in this particular case, charge of this is E. When it comes to the charge, charge of proton is E, charge of deuteron is E, charge of alpha particle is 2E. Guys, if all the three particles are placed in an electric field, this is proton, this is deuteron, this is alpha particle. You have to compare the momentum. You have to find the ratio of the momentum. Guys, when it comes to the momentum of proton is to momentum of deuteron is to momentum of alpha particle. Guys, what is momentum? Momentum is QET. If you place a charge in an electric field, the momentum is QET. So momentum of proton, deuteron and alpha particle. For proton, guys, we say charge, electric field is same. Electric field is same, all the three. Because electric field is, they are all placed in the same electric field. Okay. And time is same. ET are same. So I can say momentum only depends upon charge. Momentum only depends upon charge. Now, what is the charge of proton? That is E. I can say E is to. What is the charge of deuteron? That is E is to. What is the charge of alpha particle? That is 2E. So that is 1 is to 2. Also, this is your homework. I'm giving you one more in the same. Also, find the ratio of the kinetic energy of these particles. Okay. Also find the ratio of kinetic energy of these particles. Okay. Is that cool? We have almost we have 300 slides. And as of now, we have completed 65. And we'll have to finish all of these chapters. Okay. I think let's take a break, guys. What do you guys say? Let's take a break. And guys, we'll start the electric dipole after the break, and break is till break till 2:40 or 2:35. There's a lunch break. So be back at 2:35. Okay, let's start, guys. Let's get back to business. Now, guys, let's take a look exactly over here. Let's take a look exactly over here. We have got electric dipole. We have got electric dipole. Okay. Guys, see, when it comes to the electric dipole, we say when two equal and opposite charges are placed at a very small distance, it forms the electric dipole. Like you have got a charge minus q over here. You have got a charge plus q over here. These two charges are placed at a separation that is d. This combination is what we call the electric dipole. When two equal and opposite charges are placed at some distance, it is called electric dipole. Now, my dear friends, in this case, this electric dipole will have the dipole moment, and that dipole moment we represent with the P. Dipole moment kind of tells you the strength of the dipole. Okay, how stronger the dipole is, you can understand it like that. And always remember, this dipole moment is charge multiplied by separation between the two charges. Magnitude of charge multiplied by separation between the two charges. My dear friends, this dipole moment, it is from minus negative charge to positive charge. This dipole moment is from negative charge to positive charge. Keep that thing in your mind. The direction of dipole moment is negative to positive. Okay. And the magnitude of dipole moment is magnitude of charge multiplied by separation between the charges. Okay. Yes. Now, guys, let's suppose you get a question something like this. You will be asked to find the dipole moment in this particular case. Guys, see. Sir, first and the foremost thing is we have to check whether the dipoles are formed over here or not. Guys, see, let's redraw this figure. Let's redraw this figure. Can I say in this particular case, if I just check over here, guys, you have got 2q. Can you break this 2q into q and q? Yes. Can you write this minus q as it is over here? This minus q as it is over here. Now, my dear friends, in this case, we say this is minus q plus q. Minus q plus q. So here I can say the dipoles are formed from minus q to plus q, from minus q to plus q. And we say dipole moment of this dipole will be from minus q to plus q. And dipole moment of this dipole will be also from minus q to plus q. This angle is 60 degrees. Why? Because this is an equilateral triangle. Guys, see. You can draw these two vectors something like this. This P, you can draw it something like this. This is P. This P, you can draw it something like this. This is also P. Now, angle between these two, if this angle is 60, this angle would be also 60 degrees. Keep that thing in your mind. Now, guys, whenever you have the two vectors at an angle of 60 degrees, always remember, resultant in that particular case, net in that particular case is root 3p. Root 3 multiplied by p will be the resultant. And in this particular case, you can say under root p. When it comes to the p, P means magnitude of charge, that is Q, multiplied by separation between the charges, that is A. root 3q into A will be the net dipole moment. Root 3p will be the net dipole moment. Let's talk about this one. Guys, in this case, you are supposed to find net dipole moment. Your figure is something like this. Guys, tell me one thing. If I redraw this particular diagram, don't you think that, guys, here this is minus q, here this is minus q. Don't you think that I can write this minus q as it is? Because I have to find the net dipole moment. Before that, I have to see how many dipoles are formed over here. This is minus q. And what is this plus 3q? Can I write this as this will be plus q and this will be plus 2q? Plus 2q plus q will be plus 3q. This is minus 4q. Guys, I can write this minus 4q as minus 2q, minus 2q. And this plus 2q as it is over here. Guys, tell me, can I say this is one dipole? Equal and opposite charges. Whenever you see equal and opposite charges, this is a dipole. And its dipole moment is simply from negative charge to positive charge. This is P. Okay. And guys, can I say this is another dipole? Equal and opposite charges, plus 2q minus 2q. Its dipole moment will be from negative to positive. And value of dipole moment here will be, if it is P, so here charge is 2q, so it will be 2p. Can I say in this case, this is another dipole, and here dipole moment is also 2p. Now guys, I'll draw it over here. So guys, this P is in the upward direction. Okay, dipole moment. This 2p is in the downward direction. And this 2p is towards left. Guys, what is the resultant of 2p and p? That is bigger minus smaller. You'll make it something like this. So it will be in the downward direction, that is 2p. And in this direction, that is 2p minus p, it will be p. So it will be p and this is 2p. Now, resultant of this one and this one is this. Okay, this one and this one. Its resultant is p in the downward direction. Now, this one and this one. What is the resultant of this one and this one? Sir, this will be p net. Now, can I say P net will be, I have already told you, if there are two vectors at an angle of 90 degrees, in that case, if you are supposed to find the resultant of this one and this one, what will you say? You will say 2p whole square, okay, square of this, then you will say square of this, plus you say p square. This vector square plus this vector square. Now tell me, can I write this as, guys, 2p whole square, that is 4p square plus p square. And that will be under root of 5p square. And that will be simply root 5p is the net dipole moment in this particular case. I hope this is crystal and clear. Now guys, electric field due to an electric dipole. Since I told you that whenever you see the charge, it creates the electric field. If you have the dipole over here, it has also charge in it, minus q plus q. It will also create electric field, yes. First of all, if you have minus q charge, if you have plus q charge, dipole moment is from minus q to plus q. You guys are supposed to tell me what is the electric field at x distance, which is angle theta, which is at angle theta. What is the electric field at x distance? Guys, see, electric field will be kp by x cube. P is the dipole moment, x is the distance where you have to find the electric field. Then we say under root of 3 cos square theta. Theta is the angle between x and dipole moment. Then we say plus 1. This is the electric field at this point. And guys, remember, this is the electric field at arbitrary point. This is the electric field at arbitrary point. Arbitrary point in case of a dipole. This is the electric field at an arbitrary point in case of a dipole. Guys, now I'm taking the same dipole over here. But right now I'm not finding the electric field at arbitrary point, but electric field at the axial point. This is the axial point. Axial point. At axial point, I want you to directly remember, electric field is twice Kp by x cube. Twice Kp by x cube. K is Coulomb's constant, P is dipole moment, x is this distance. Okay. Okay. And we sometimes take this distance from the center because dipole is very small. You take from here, you take from center, it's one and the same thing. Now, guys, here in this particular case, electric field due to dipole on perpendicular bisector. So before this we calculated here. Now we have to find the electric field at perpendicular bisector or equatorial point. Here electric field will be minus Kp divided by x cube. Electric field at perpendicular distance, perpendicular bisector is minus Kp by x cube. At axial point is twice Kp by x cube. Arbitrary point is Kp by x cube under root of 3 cos square theta plus 1. Here it will be minus Kp by x cube. I hope you got it. Now guys, take a look. Let's suppose you have a question something like this. Okay, there is a dipole placed over here. You can see. You guys are supposed to tell me, sir, what is the electric field due to the dipole at point A, at point B? Tell me one thing. Sir, when it comes to the point B, for this dipole, point B is the axial point. Axial point. And this is the arbitrary point. Arbitrary means general point. Okay. Guys, let's first calculate the electric field because of this dipole at arbitrary point. Use the arbitrary formula. Okay. Okay. Guys, I am saying electric field is equal to, that is Kp divided by x cube under root of 3 cos square theta plus 1. Because at arbitrary point, this is the formula that we use in order to find the electric field, 3 cos square theta plus 1. Now tell me, can I say this electric field will be Kp divided by x cube? Guys, this is the distance for arbitrary point. If this is L, this will be root 2L. Diagonal. Now, can I say this will be under root 2L whole cube? Then I say under root of 3 cos square theta. Theta is given as 45 degrees. 45 plus 1. So you can solve this, guys. This will be the electric field at point A, Kp divided by root 2L whole cube. Okay. Then I can say this will be cos 45 is 1 by root 2. Cos square of 45 will be 1 by 2. So this will be 3 by 2 plus 1. Now, guys, simplify it and you will get the correct answer. Okay. Just the simplification. Similarly, if I say electric field at point B, B is the axial point. On the axial point, what is the formula we are supposed to use? That is twice Kp by x cube. So I can directly use, so it is twice Kp divided by x cube. So it is twice Kp. What is the value of x? Here you have to take the value of x as L. So in this case, this will be twice Kp by L cube. And this will become how much? That is 5 by 2, root 5 by 2. Okay, so E will come out to be Kp divided by, this will be root 2L whole cube. And then this will be exactly 5 by 2. Further also you can simplify. Okay, now my dear friends, I hope this is done. I hope this is done. Guys. I hope this, tell me in the chats, is this crystalline clear? Is this crystalline clear? It is, see. Don't get confused with this negative sign. Don't get confused with this negative sign. Where is it? Here. When it comes to the magnitude, When it comes to the magnitude, take this plus, no problem. It is because of this electric field will be towards, because of this electric field will be away. So resultant of these two will be in the left direction. That's why we take negative over here. That's why. In case of axis, we take positive. When it comes to the magnitude, take it positive. Don't get confused with this negative sign. No need to get confused. Okay. Okay. Now, let's move on to this one. Let's move on to this one. Let's move on to this one. Guys, let's suppose electric field placed in a uniform electric field. Sorry, electric dipole placed in a uniform electric field. Guys, see. You have got an electric field, okay? And in this electric field, you are placing a dipole. Understand carefully. Dipole means negative charge, positive charge. Tell me, whenever you place a positive charge in the external dipole, in the external electric field, what happens? Sir, we have already studied. Force acts on it in the direction of electric field. That is Q times E. If you place a negative charge in the external electric field, force acts on it opposite to the direction of electric field. That is also Q times of E, but direction is opposite. Tell me guys, here. This force and this force, don't you think these two forces will try to rotate the dipole? Okay, so here I can say the two forces try to rotate the dipole. So torque is produced. Sir, what is this torque? Guys, now is not the time to explain the torque in detail. Simply, whenever you say any body is rotating, means torque is produced. If I say body, guys, if I say there is a body which is at rest, somebody came and applied the force. Now body starts moving. So motion is, this linear motion is because of force. Similarly, if I say this body is rotating, it starts rotating. It is because of torque. Because of rotational motion, because of torque, there will be rotational motion. Because of force, there will be linear motion. Okay. And guys, if torque is produced, torque is the rotating effect or rotational version of force. Whenever there is rotation, there is torque. These two forces will try to rotate this. And if somebody asks you, how much is the value of torque over here? You say torque is P-E sine theta. Torque is simply P-E sine theta. And this torque, you say it is P cross E. This torque, you say it is simply P cross E. Because A cross B, AB sine theta is A cross B. So PE sine theta is P cross E. Okay. So this is the value of torque. Now guys, listen to me very carefully. Let's suppose if theta is equal to 0 degrees. Guys, if you place the dipole here, and one more thing. Sir, this theta is the angle between P and E. Dipole moment and electric field. Now tell me, if you place the dipole something like this, this is minus Q, this is plus Q. Dipole moment is from negative charge to positive charge. Electric field is also forward. Angle between P and E is 0 degrees. How much is the torque in this particular case? Guys, you say, sir, torque is, that is PE sine theta, and sine is 0 over here. Sine 0 is 0. Torque in this case is 0. That's what I'm mentioning. So, if torque is 0, means there is no rotating effect on this. So means it will not rotate. If it does not rotate, means torque is 0. As simple as that. Guys, here, if the value of theta is 90, this is minus Q, this is plus Q. Guys, in this case, what will be the value of torque? Torque in this case is PE sine 90. Sine 90 is 1, so torque will be PE. Torque will be PE. Here torque is 0. Here torque will be PE. As simple as that. Now. So from now onwards, you'll remember one thing. whenever you place an external dipole, whenever you place a dipole in the external electric field, it will rotate. It will have torque. The value of torque is Pe sine theta. If theta is 0, torque will be 0. If theta is 90, torque will be Pe. If theta is 270, then it will be Pe sine of 270. That is -1. So that torque will be minus Pe. I hope all of this is crystal and clear. Okay. Okay. Now guys, take a look. One more thing I just want to explain over here. What is that? What is that? See guys. Listen to me very carefully. Listen to me very carefully. Let me talk about potential energy. Guys, the basic thing you might have heard about this potential energy is, let's suppose this is the surface I'm taking. This is the surface of Earth. And from the surface, on the surface, there is a ball placed over here. Its mass is m. You are taking this ball to the height h. You are taking this ball to the height h. Okay. You are taking this mass to the height h. Guys. All of you must be knowing that, sir. All of you must be knowing that when it comes to the surface, we say potential energy is 0. On the surface, we say potential energy is 0. Sir, when you take this ball to the height h, so we say at height h, its potential energy is mg into h. Mg into h. Its potential energy is mg into h. So on taking the ball from surface to the height h, we say its potential energy has increased as mgh. Now, my question to you is, who has taken the ball from the surface to the height h? You'll say, sir, it is you. It is the external agent. So means I used my energy. I did the work over here in lifting the ball from the surface till the height h. Then only that work done of mine was stored in the form of potential energy. So I say the work done by the external agent is stored, the work done by the external agent is stored in the form of potential energy. The work done by the external agent. I did the work done. Because of that work done, only potential energy got stored. And guys, I can say because of that work done, potential energy was changed. How, sir? On the surface, it is 0. When I did the work, then potential energy became mgh. So from 0 to mgh. So I can say this work done is equal to U final minus U initial. So because of work done, potential energy is changed. This is called work done is equal to change in potential energy. Very important equation. Now guys, same is the case over here. Tell me one thing. Let's suppose you have an external electric field over here. In this external electric field, you have a dipole. Now guys, you are rotating this dipole from here to here at an angle theta. Now, can I say here also, external agent I will have to rotate the dipole from this angle to this angle. Now, my work done, which I used in rotating the dipole, will that go in waste? No. Like here, my work done was stored in the form of potential energy. Similarly, on rotating the dipole, you have to do the external work done. That will be stored in the form of potential energy of the dipole. That work done will be stored in the form of potential energy of the dipole. Here, That work done was stored in the form of potential energy of the mass. Here it is stored in the form of potential energy of the dipole. And guys, can I say here also, because of the external work done, potential energy is changed. W external is equal to change in potential energy. Yes, sir. Because when you do the work done, potential energy is stored. Potential energy is changed. Now, guys, we say, sir, how much is the potential energy at angle theta? That is minus PE cos theta. P is the dipole moment. E is the electric field. Theta is the angle between dipole moment. Let's suppose it is here. Dipole moment and electric field. P is the angle between dipole moment and electric field. Or you can also say it is minus P dot E, because AB cos theta is A dot B. P cos theta is P dot E. Okay. So if you rotate the dipole in the external electric field, you have to do the work done. That work done is stored in the form of, potential energy. Okay. Now, my dear friends, let's take a look. What about the reloaded batch? We take classes every day in the reloaded batch. Today I didn't take the class. Every single day we take the classes in the reloaded batch. Please check your this subscription that you have taken. There might be some error in your profile. That's why you are not getting the classes. Every single day we take the classes. Udab. If there is a reloaded student over here, please tell this guy. Now, take a look over here. Take a look over here, guys. Let's suppose if theta is equal to 0 degrees, theta is equal to 90 degrees. And if I ask you, sir, you have rotated the dipole till 90 degrees. What is the potential energy that got stored in the dipole? You say, sir, U is equal to minus PE cos theta. So theta is over here, cos 90. Cos 90 is 0. So at 90 degrees, potential energy is 0. Now, if theta is equal to 0 degrees, sir, how much is the potential energy at 0 degrees? U is equal to minus PE cos of 0 degrees. Cos 0 is 1. So U is equal to minus PE. Okay, tell me here. In this particular case, we say U is equal to minus PE. Guys, dipole moment is backwards. Electric field is forwards. Theta is 180. So cos of 180. Cos 180 is minus 1. So U is equal to plus PE. By the way, this is called maximum potential energy. Okay. This will be minimum potential energy. Okay. And my dear friends, in this particular case, so this is basically case 1, case 2, and this is case 3. Now, let's take a look at this. Okay, one more thing I have added over here. What is that? See, in this particular case, guys, when theta is equal to 0 degrees, net force on the 90 degrees, net force on the dipole will be 0. Why? Because positive charge is here, force is forward, negative charge is here, force is backward. These two forces are opposite, so they will cancel. Torque will be PE sin 90. Sin 90 is 1, torque will be PE. Okay, this is maximum torque. Potential energy will be 0. Guys, when theta is equal to 0 degrees, in that case, torque that will be 0. Potential energy, that will be minus PE. And this potential energy is what we call minimum potential energy. And we say this is what we call the stable equilibrium. Directly remember, when potential energy is minimum, in that case, we consider this as stable equilibrium. Now guys, here. In this case, we say potential energy is maximum. We consider this as unstable equilibrium. So when potential energy is minimum, directly remember stable equilibrium. This is unstable equilibrium. Okay. Is this clear till over here? Is this clear till over here, guys? Tell me in the chats. I would want you guys to tell me in the chats if this is crystalline clear. Okay. Now, guys, take a look. In this particular case, see, electric potential energy. Let's suppose we have got a charge Q1, we have got a charge Q2, and distance between the two charges is R. Sir, whenever you have the two charges, sir, is there potential energy between the two charges also? Yes. Like you might have a basic idea. If you have mass M1, M2, distance between them is R. Between these two masses, potential energy is there. U is equal to G M1 M2 divided by R minus G M1 M2 by R. Simply from now onwards, remember one thing. If you have a charge, if you have another charge, if there is a distance between the two charges, simply remember potential energy exists between the pair of these two charges. How much will be the potential energy between the two? Sir, that is simply K Q1 Q2 divided by R. So this is the potential energy between the two charges. Directly remember. Now if somebody asks you, sir, what is the potential energy here? Find net potential energy. Find U net. Find net potential energy. Guys, listen to me very carefully. If you want to find out the net potential energy in this case, first you write the potential energy of these two charges. Guys, see. Whenever you have the pair of charges, there will be potential energy. We say potential energy between these two charges. Potential energy between these two. Potential energy between these two. Potential energy between these two. Okay. Guys, see. I'll write U net I'll write. So we say U net is equal potential energy between these two charges, guys, that is K Q1 Q2, that is Q square divided by distance between them is L. Similarly, potential energy between these two. Potential energy between these two. Potential energy between these two. So I can say in this particular case, this is 4 times. Now guys, whenever you see the pair of charges, there is potential energy. Now tell me, between this charge and this charge also there will be potential energy. Between these two charges, diagonal charge, there will be potential energy. Then we say plus. Guys, what is the potential energy between this and this? That is K. Q into Q is Q square divided by distance between them is root 2L. Now, one more. Between these two also a similar potential energy. So I'll write 2 times. Okay, so this is the net potential energy for the system. This is the net potential energy for the system. Okay. This is the net potential energy for the system. Now, guys, let's suppose you get a question something like this. You get a question something like this. The question is, you have got the 6 charges. You have got the 6 charges over here. Okay. Plus Q minus Q. Plus Q minus Q. Plus Q minus Q. Are fixed at the corners of a hexagon. Are fixed at the corners of a hexagon. As shown in the figure. The work done in bringing a charge Q0. The work done in bringing a charge Q0 from infinity. Let's suppose the charge Q0 is at infinity. You want to bring this charge from infinity to the center of the hexagon. How much work we are supposed to do if we have to bring the charge from infinity to the center? Guys, see, when it comes to the work done, always remember, work done is equal to change in potential energy. Always remember, work done is equal to change in potential. So you say, work done is equal to U final minus U initial. Final potential energy, initial potential energy. Initially charge is at infinity. Guys, understand this very carefully. So we consider initial potential energy as 0, because directly remember, when it comes to the potential energy at infinity, that we consider 0. Okay. Sir, what about final potential energy? Final potential energy. Finally, charge is here. Tell me. What is the potential energy between these two? Sir, it'll be K. This charge is Q. This charge is Q naught divided by. Let's suppose this distance is D, so this will be also D. Okay. Now, guys, potential energy. Okay. This one and this one plus. Potential energy between this one, it will be same. Potential energy between this one, because these two are similar, these two are similar. So we say it will be 3 times. Okay. Then, guys, potential energy between this and this, it will be minus, because this charge is negative. So it will be K, that is Q naught divided by D. Guys, minus Q and Q naught. Here also minus Q and Q naught. Here also minus Q and Q naught. So these are 3 pairs. So this is 3. So this and this will also cancel. U final is also 0. So guys, can I say work done will be U final minus U initial, 0 minus 0. That will come out to be 0. So answer in this case is 0. This was the question which was asked in NEET 2022. 2022. Okay. So whenever they ask you to find the work done, directly use this formula. W is equal to change in potential energy. Okay. Now, guys, now comes the another concept, that is what we call the electric potential. That's what we call the electric potential. Guys, see. Guys, see. When it comes to the electric potential over here, sir, what is electric potential? Electric potential is simply potential energy per unit charge. Guys, see. Let's suppose if you have a charge over here Q, if you have another charge small q, distance between them is r, and value of this Q is 1 coulomb. If I ask you, tell me, what is the potential energy between the two? You say, sir, U is equal to K Q1 Q2 by R. But what is the value of Q2? That is 1. So place it over here. So it will become U is equal to KQ by R. So instead of this U, I am writing V. Why? Guys, what is this? This is the potential energy of, we say these two. Okay. Guys, when this charge is 1 coulomb, so I can say potential is nothing but potential energy per unit charge, So it is KQ by R, potential energy of 1 coulomb charge. Here you have placed 1 coulomb. It is potential energy of 1 coulomb charge. If another charge you place over here 1 coulomb, so then you consider potential energy of these two as electric potential. Now from now onwards, if somebody asks you, is potential the potential energy? You say yes. Potential is potential energy per unit charge, potential energy of 1 coulomb charge. So we also said something like this, guys. We say electric potential we represent with V. We say V is equal to potential energy is U divided by charge Q. Now tell me, guys. Let's suppose we can say V is equal to, instead of U, I'll write K, capital Q, small q, divided by R, and then this Q. This and this will cancel. V will come out to be KQ divided by R. So potential is basically potential energy per unit charge. Okay. So guys, from now onwards, like we got over here, what is the potential? Potential is KQ by R. From now onwards, you will remember that if you have a charge, sir, at R distance, what is the potential because of this charge? That is KQ divided by R. In reality, what is this? This is in reality potential energy. And we say here it would have been 1 coulomb charge. So then we say KQ, this one divided by R. That's why we call it the potential. It is actually potential energy. Now guys, see. Let's suppose you have got these charges over here till infinity. You have to tell me what is the net potential at the origin. Understand very carefully. We say when it comes to the net potential, what will you say? Potential due to this, okay? That is KQ divided by R. R is what? That is 1 meter plus. What is potential because of this at this? That will be KQ divided by. This is placed at what distance? That is 2 meters. Then we say plus. What is potential because of this? It will be again KQ divided by R. From here to here it is 4 meters. Plus potential because of this KQ divided by 8 plus so on. So now tell me, can I say net potential in this case is, what is the thing that we are supposed to take common? That is KQ. And it is 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 and so on. I have already told you this is what we call the GP series. And how do we find the sum of GP series? Guys, we say when it comes to the sum, it is A upon 1 minus R. A means the first term. R means the common ratio. How do we find R? Take any term, let's suppose 1 by 4. Divide it with the term which comes before it, that is 1 by 2. 2 1s are 2 2s are 4. So it is 1 by 2. Common ratio is 1 by 2. Now put over here, sum will come out to be 1 upon 1 minus 1 by 2. 2 1s are 2. 2 minus 1 is 1, 1 by 2. So it is 1 upon 1 by 2. So it will come out to be 2. So sum came out to be 2. Now can I say net potential in this case will be KQ. Instead of all of this, this will be 2. So 2 times KQ. So 2 times KQ. Is this clear? Give me the signal in the chats if this is crystalline clear. Give me the signal in the chats. Find the net electric field and net potential at the center. And guys, by the way, potential is a scalar quantity. Keep that thing in your mind. See, what is the net electric field at the center? Guys, see. Because of this charge, electric field at center is away from the charge. Because of this charge, electric field at the center is away from the charge. Because of this charge, electric field at the center is away from the charge. Because charges are positive. Because of this charge, electric field at the center is away from the charge. This will cancel with this. This will cancel with this. So I can say net electric field at the center is 0. Net electric field at the center is 0. Now, when it comes to the net potential, you say net potential is, guys, listen to me very carefully. Let's suppose the side is L. From here to here, how much is the distance? That is L by root 2. Guys, potential because of this charge at the center will be KQ divided by, what is the distance till center? L by root 2. Guys, what is the potential because of this at center? KQ upon L by root 2. KQ upon L by root 2. KQ upon L by root 2. So this is 4 times. Sir, what about potential? Will it not cancel? No. Because it's not a vector quantity. It does not have direction. It will add. So I can say this will be 4 root 2 KQ divided by L. 4 root 2 KQ divided by L. So net potential is this, net electric field is 0. Guys, see, I recently told you, if you have a charge, it will create potential. If you have a charge, it creates potential as KQ by R. Now, if you distribute the same charge on the sphere, it will also create potential. Okay. Now the topic is potential due to a hollow or solid sphere, or you say hollow conducting and solid non-conducting. Let's first consider this hollow sphere over here. And when it comes to this hollow sphere, we say charge on this hollow sphere is positive. Charge on the hollow sphere is positive. And my dear friends, you are supposed to tell me electric field at this r distance. Electric field at this r distance. Sorry, potential at r distance. Outside. Guys, outside the sphere, potential will be simply that is KQ divided by R. That is KQ divided by R. Potential because of this hollow sphere outside will be simply KQ divided by R. Simply because at very far distance, you consider this hollow sphere as a point charge. Now, sir, on the surface, how much will be potential? On surface, we say value of small r is equal to capital R. So, here instead of small r, you will be putting capital R. You will be putting capital R. Okay, this is KQ by capital R. When it comes to inside will be same as whatever is on the surface. Inside will be same as whatever is on the surface. So I can say from inside to surface, from center to surface, I can say potential is constant. Now, take a look. If we make the graph between V versus R, we say potential is constant till surface. Okay, potential is constant till surface. And outside the surface, I am saying potential is inversely proportional to R. Outside the surface, potential is inversely proportional to R. Now, guys, take a look. Guys, don't worry. I know how to complete all the chapters. Electrostatics is extremely big chapter, okay? Previously, I have covered all the 7 chapters in one marathon. You can check that out. So this year also, I'll be completing all the 7 chapters, okay? Okay, so you don't have to worry about, sir, how many chapters, how much time you are going to give that chapter. EMI AC is a small chapter. How much time? That will finish in just 1 hour. Electrostatics, current, these are the big chapters. It will take time. Rest of the chapters are very small. Now, potential due to a solid sphere. Let's suppose you have got a solid sphere. In case of solid sphere, charge is present inside also. Guys, when it comes to the outside point, potential will be KQ by R, small r. Small r is the distance outside. Guys. When it comes to the surface, it is KQ by capital R, because on surface, value of small r is capital R. Guys, see. Right now, charge is present inside also. So, inside potential will not be same as surface. No. When it comes to inside will be KQ divided by 2R cube. KQ divided by 2R cube. Then multiplied by 3R square minus R square. Capital R is, by the way, the radius. Small r is the distance inside where you have to find the potential. And I have told you, okay, I have told you this small r is variable. For outside point, small r is large. For inside point, small r is small. And guys, what is the potential at the center? This is the potential at the center. Okay, this is the potential at the center of a solid sphere. This is the potential at the center of a solid sphere. This is the potential at the center of a solid sphere. Now, my dear friends, in case of solid sphere, sir, this is the outside point. This is the potential outside. This is the potential on the surface. This is the potential inside. Now, I would want you guys to focus exactly over here. Guys, see. Graph between potential versus R in case of a solid sphere. This is for solid sphere. Guys, see. In this particular case, you'll see, sir, this graph, potential is maximum at the solid sphere. Potential is maximum in case of solid sphere at the center. Because at the center, it is 3 by 2 KQ by R. 3 by 2 means 1.5. It is 1.5. On the surface, it is KQ by R. 1 times, guys. Is this greater than this? Yes. This is 1.5 times KQ by R. This is only KQ by R. So I can say in this particular case, on the surface, it is 1.5 times. Okay. Sorry, at the center. This is the potential at center. This is the center. Okay. This is surface. Guys, on surface it is kq by r. At center it is 3 by 2 kq by r. Then outside it is inversely proportional to small r. It is inversely proportional to small r. You can check. V outside is inversely proportional to small r. That's why it is a rectangular hyperbola. So this is outside. This is inside. And this is surface, where small r is equal to capital R. Very important graph. This was asked so many times in your NEET examination. Okay. Cool. Let me show you this one. Guys, take a look. I'm saying find the potential. Find the potential at A, B, and C in case of hollow spheres. In case of hollow spheres. Tell me, guys, you have this sphere, you have this sphere. Guys. When it comes to the point A, I want you to understand very carefully. This point A is outside of the bigger sphere, it is outside of the smaller sphere. Don't you think that at point A, potential will be, guys, when it comes to the hollow sphere, potential outside is kq by small r, that is the outside distance. Surface is kq by capital R, inside is also kq by capital R. Take a look. When it comes to the outside point, potential will be simply, guys, because of the inner sphere, it is K. What is the charge on, first I'll tell because of the outer sphere. What is the charge on outer sphere? That is Q1. And at what distance it is from the center RA? KQ divided by RA plus. What is the potential because of the inner sphere? That will be K. Charge on the inner sphere is K2 divided by, from the center till here distance is RA. So this will be also RA. Done. Guys. Potential at B. For bigger sphere, B point is inside. So whatever is the potential on the surface of bigger sphere, that will be inside. So on the surface it is KQ1 divided by R1. So that will be also inside. Then plus point B is outside of this sphere, outside of this inner sphere. So here you will use outside formula. That is K, Q divided by small r. And what is Q? That is Q2 divided by, at what distance? That is RB. Guys, see, at point C. C point is inside of this sphere. C point is inside of this bigger sphere. So whatever is the potential on the surface of this sphere, that will be inside. Whatever is the potential on the surface of bigger sphere, that will be inside. So because of bigger sphere, it is Q1 divided by R1. This is the on the surface. Inside also it will be same at every point. Now, potential on this surface will be KQ2 divided by radius of this is R2. So this will be inside also. I hope this question is crystal and clear. If not, please do watch it later on once again. Right now, I will move on. This one. Guys, take a look. Electric potential due to a charged ring. Let's suppose you have a charged ring over here. Okay, this is a ring. And you are supposed to tell me what is the potential because of the ring at X distance. Ring potential at X distance because of the ring. Radius of the ring is capital R. We'll say simply, sir, it is KQ divided by under root of X square plus R square. X square plus R square. If somebody asks you at center, we say value of small r is equal to 0. value of x is equal to 0 at center, because if you move towards the center, x will be 0. Then put x 0 over here. VO will be, potential at center will be kq upon under root of x will be 0, so this will be r square. This and this will cancel, so it will be kq divided by r. So this is at x distance, this is at center, kq by r. Okay. Now guys, if I say one more point, very far from the ring. Let's suppose this is the ring, radius of this is r, and this is x. Can I say here x is much greater than r? Yes. If that is the case, this x is much greater than r, means r is very small as compared to x. When you add a very small quantity to a very large quantity, it does not create any difference. If this will not create any difference, so neglect small r. So we can say V will be equals to kq upon, I can say under root of x square. This and this will cancel. So it will be kq by x. Guys, it is very far from the ring. It is at the center of the ring. It is at x distance. I hope this is okay. Now, this one. Tell me, in this particular case, just a second. Guys, see, you guys are supposed to tell me VA minus VB. You have a ring over here. Charge on this is plus Q, radius is R. Charge on this is minus Q, radius is R. Guys, see. We have to find potential at A, potential at B, then VA minus VB. Tell me one thing. If I ask you to tell me potential at A, guys, this A point is at the center of the ring. At the center of the ring, what is the potential? KQ by capital R. So at the center of the ring, potential because of this ring will be KQ divided by capital R. Cool. Then this A point is at X distance because of from this ring. So potential because of this ring at A point will be guys minus KQ divided by X, because this point for this is X point, and that is very far point. This point is very far from this ring. That's why I say KQ by X. This point is at the center of this ring. That's why I told you KQ by R. Then VB. Potential at this point. Guys, this point is at the center of this ring. So it is minus KQ divided by R. Because of this ring at center, it is KQ by R. Now, this point is very far from this ring. So it will be plus KQ divided by X. You got VA, you got VB. Now you can easily find VA minus VB. That is your job. Now you find VA minus VB. Equipotential surfaces. Guys, when it comes to the equipotential surface, let me tell you over here. Let's suppose you have got a charge over here. Because of this charge at R distance, could you please tell me what is the potential? Potential is KQ divided by R. Sir, because of this Q, what is the potential at this R distance? It is KQ divided by R. If you go over here, it is KQ by R. Okay. If you go over here, it is KQ by R. Here also same, here also same. Means if this is a charge, at this R distance, KQ by R, 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 KQ. Now, if you join all of these points, don't you think that it will become a spherical surface? And on this surface, at every point, potential is same. So we call this as equipotential surface. So we say that surface at which potential is same everywhere is called equipotential surface. Come here. We say equipotential surfaces. That surface upon which potential is same everywhere is called equipotential surface. Like I told you, for a point charge, draw a sphere around it. This is a point charge around it. This is a point charge around it. Surface will be spherical. Okay. Now guys, the potential difference between the 2 points on equipotential surface is always 0. Why? Let me tell you why. If I am saying this is point A, this is point A, this is point B, tell me what is VA minus VB? Sir, at A point, how much is potential? KQ by R. Minus. At B point, how much is potential? KQ by R. This and this will cancel, so potential difference is 0. So potential difference on the equipotential surface is 0 at every point. Okay. Okay. Yes. Now guys, electric field is always, I hope this is visible. Electric field is always perpendicular to the equipotential surface. Guys. If we have a charge, we know because of the charge, electric field is always away from the charge. Electric field is always away from the charge. Now, if you want to draw an equipotential surface, that will be something like this. Now, how much is the angle between the equipotential surface and this electric field? That is 90 degrees. That's what I'm trying to say. Electric field and equipotential surface is always at an angle of 90 degrees. Electric field and equipotential surface is always at an angle of 90 degrees. Okay. Next. Electric field and equipotential surface is always at an angle of 90 degrees. Next. No work is done by the electric field in moving the charge from on equipotential surface. Guys. Let's suppose this is the equipotential surface. Equipotential surface. Okay. Let's suppose if you want to take the charge from this point to this point, this is point A, this is point B, from point A to point B. So you have to do the work done. We say yes. Remember directly, the formula for that work done is Q delta V. Sir, you have told us work done is equal to, delta U. Okay, I have told you this. See, tell me one thing. Divide both sides by charge, So this is W divided by Q is equal to, this is potential energy per unit charge. I guess that is potential. So I can say this is delta V. So multiplied over here, work done will be Q delta V. Now guys, tell me one thing. Sure, I can say work done is Q delta V. In case of equipotential surface, what is delta V? Delta V is 0. If this is 0, so work done will be 0. That's what is mentioned. No work is done by the electric force in moving the charge on an equipotential surface. Okay. Is this clear? We are done with this electrostatics and potential part. Please tell me in the chats if this is crystal and clear. This was one of the biggest chapters. I could have skipped some of the topics, but I didn't. Okay. All of this was important. That's why. Even guys, this electric field is 90 degree with the equipotential surface. This was the question which was asked in NEET 2022. The angle between the equipotential surface and this. Now guys, take a look. Next chapter we have capacitors. So we are starting the chapter capacitors. Okay. So in this particular chapter, we have the first thing that we need to understand, what is a capacitor. Guys, if I say I have got a bucket. Okay, I have got a bucket. I ask you the simple question. What is this bucket used for? You'll say, sir, this bucket is used to store water. We store water, we store fluid, we store milk in this bucket. Okay. Sir, what is this capacitor? We say it is a device which is used to store electrical energy / you can say charge. Electrical energy in the form of charge. It is that device you want to store charge. Where will you store it? Capacitor. Capacitor is a device which is used to store charge. Let's suppose I am taking the basic capacitor. Basic capacitor means normal sapphire, metallic sapphire. I am taking a sapphire over here. Okay. This is a spherical capacitor. Spherical capacitor. Okay. And I am storing charge Q on this sapphire. Okay, that you have been studying till now. Okay. Guys, tell me one thing. If Q charge is stored on the sapphire, we know that if there is a charge, there is potential. Sir, charge is directly proportional to potential. Recently you saw. Sir, because of a sapphire, potential is KQ divided by R. Now tell me, V and Q is directly proportional. Sir, if you increase charge, potential will increase. If you decrease charge, potential will decrease. So more you store charge on this capacitor, on this sapphire, we say more potential will increase. Now, replacing this with a constant C, we say Q is equal to CV, where C is the constant and is called, where C is the constant and is called the capacitance of a capacitor. Where C is the capacitance of a capacitor. What does capacitance mean? Guys, capacitance is the capacity of a capacitor to store the charge. You say, what is the capacity of the bucket? Sir, it is 10 liters. Sir, it is 20 liters. Similarly, what is the capacity of this capacitor? Sir, it is 20 farad. It is 30 farad. Farad is the unit. So, simply I am saying, capacitor is a device in which we store charge. If you store charge, potential will be developed. And we say Q is equal to CV, where C is the capacitance of the capacitor. Now, guys, let's suppose if we talk about this spherical capacitor. You say, sir, if somebody asks me what is the capacity of a spherical capacitor, how much charge it can store, it should have some value. This is the capacity. This is the capacity of a spherical capacitor. This is the capacity of a spherical capacitor, or you say capacitance. That is 4 pi epsilon naught R. And you can clearly see this capacitance depends upon the dimensions. If you increase the value of R, it is simple. If you increase the size of bucket, you can store more charge. If you decrease the size of bucket, you can store less charge. Similarly, if you increase the size of this capacitor, radius of this capacitor, you can store more charge. As simple as that. Next. Okay, guys. Very important. Very important. Directly remember this trick. See, guys. Let's suppose you have got capacitor. These are the small n capacitors, very small capacitors, okay? Like this is a small capacitor. Charge of this capacitor is Q. Capacitance of this capacitor is C. It's a small capacitor, it has charge Q in it, and its capacitance is C. Capacitance is C. And its radius is, by the way, R. Small r is the radius. And potential is V. Potential is V. Its potential is V. Okay? Charge is R and its potential is V. Now, my dear friends, I want you to understand one single thing. Sir, if we join all of these small capacitors together, like n capacitors are combined to form a big capacitor. N capacitors are combined, sir, with what process? Melting, welding, something like that. We have done it. Okay. To form a big capacitor. The radius of the big capacitor is capital R. Potential is V dash. Capacitance is C dash. Charge is capital Q. Guys, small capacitor has charge Q, small q, potential V, capacitance C, radius small r. Big capacitor, if somebody asks you, if these n capacitors are joined to form a big capacitor, what will be the value of final capacitance of this? What will be the value of V dash, R dash, Q dash? Directly. Charge of big capacitor is n times of Q, n times of small capacitor. Radius of big capacitor is n raised power 1 by 3 times of R. R is the radius of small capacitor. If I say value of n is 64, means 64 capacitors. Value of final capacitance of this is n raised power 1 by 3 into C. Value of V dash is n raised power 2 by 3 into V. Let me show you the question which was asked in NEET 2021. What does the question say? 27 drops. Even if say drops, consider this is capacitors. 27 drops of the same size at 20 volts. So we have got 27 drops. Okay. So n is given as 27 drops. Are charged at 220 volts, means potential of each drop is 220 volts. They combine to form a bigger drop. They are combined to form a bigger drop. You are supposed to tell me the potential V dash of the bigger drop. Guys, tell me, direct formula. Potential of bigger drop is n raised power 2 by 3 into V. So you say as V dash is equal to n raised power 2 by 3 into V. So V dash is equal. What is the value of n? N is equal to 220. 2 by 3 into V. And V is over here. V is over here. In this case, that will be 220. Oh, sorry. Value of n is 27. 27. 2 by 3 and value of V is 220. Okay. Now you can write it something like this. V dash is equal to 27. Guys, you can say it is 27 whole raised power 1 by 3 whole square. It's one and the same thing. Now cube root of 27. 1 by 3 means cube root. Cube root of 27 is 3 into 3 is 9. 9 into 3 is 27. So 3 into 3 into 3 is 27. So cube root of 27 is 3. So I can say this is 3 square. It will come out to be 9. Because this is 3, its square is 9. So instead of this, I'll write 9 into 220. So solve it, it will be 1980. So potential of bigger drop is 1980. Even ladies and gentlemen, you can find this also. Capacitance, radius and charge. Let's find capacitance in the same question. You can say, sir, C dash is equal to n raised power 1 by 3. 27 raised power 1 by 3 into C. So this is cube root of 27, that is 3. So 3C. Even you can find what? Radius also, that is 3R. You can find charge also, that is 27Q. I hope this question is crystal and clear. Then you have parallel plate capacitor. Guys, see, what does parallel plate capacitor mean? Sir, previously that we studied was the spherical capacitor. Sir, what is wrong with the spherical capacitor? I'll tell you. Guys, If you have a spherical capacitor, this one, you store the charge on the surface of the spherical capacitor. Okay. So there are high chances that this charge, this energy will leak over here. There will be leakage, high chances of leakage in case of the spherical capacitor. So we wanted a better capacitor in which we can store the charge, which remains safe. So we introduced the concept of parallel plate capacitor. So parallel plate capacitor is a better capacitor as compared to the spherical capacitor. How do we exactly make it? See, we take a plate, we take another plate, one plate, another plate, like I'll make the parallel plate capacitor over here. You have a plate, you have another plate. This is what we call the parallel plate capacitor. Okay. Now guys, if this is a parallel plate capacitor, separation between the two plates is D. Area of this is A. Like guys, this has the capacity to store. This is the capacitance of the spherical capacitor. Similarly, this is the capacitance of parallel plate capacitor. Epsilon naught A. A is the area of parallel plate capacitor divided by D. So this is the capacitance, ability, capacity to store the charge, to store the electrical energy. Is parallel plate capacitor better or spherical? Parallel plate capacitor is better as compared to the spherical capacitor. Now, the question which was asked in NEET 2022. See guys, find the capacitance of a capacitor if the area of the plates is A by 2. Guys. Let's suppose we have a parallel plate capacitor. This is a parallel plate capacitor. Okay. And its area is A, separation is D. Area of the plates is A and separation is D. I'm saying what is the capacitance? Capacitance is epsilon naught A divided by D. Now finally it says if the area of this is reduced to A by 2. Finally, area is A by 2 and separation is basically 2D. What will be the new capacitance? You say, sir, new capacitance C dash will be epsilon naught A by D. Instead of area, I can write A divided by 2. Instead of D, I can write 2D. So this will become epsilon naught A divided by 2 into 2 is 4D. So epsilon naught A by D is C. So C dash will come out to be C by 4. C dash will come out to be C by 4. So capacitance has been decreased by 4 times. So this was the question which was asked in NEET 2000. One more thing. Energy stored in a capacitor. Sir, since you said capacitor is a device in which we store energy. Now the question is, how much energy do we exactly store in a capacitor? See guys, see. Let's suppose this is a capacitor. You are storing Q charge in it. If you ever see plus Q on one plate, minus Q on another plate, then consider Q is the charge in the capacitor. If you see plus 2Q, if you see minus 2Q, then consider 2Q is the charge in the capacitor. If you store Q charge in the capacitor, C is the capacitance of the capacitor, then what will be the energy? Energy stored will be, guys, that is Q square divided by 2C. Energy stored in a capacitor is Q square by 2C. Also, you can say it is 1 by 2 CV square. This is the energy of a capacitor in terms of capacitance and potential difference. This is in terms of charge and capacitance. Also, it is 1 by 2 Q into V. 1 by 2 Q into V. So Q is the charge, V is the potential. This is the energy stored in a capacitor in terms of charge and voltage, capacitance and voltage, charge and capacitance. All of these three formulas we can use. Like we have a question over here. Okay. We have a question over here. Guys, we measure the capacitance in farad. Like we measure the volume in liters, we measure the capacitance in farad. What is the capacitance of a capacitor? 5 farad, 10 farad. Okay. Now guys, see. In this particular question, a capacitor of capacitance 700 picofarad. So capacitance is given as 700 picofarad. 700 picofarad. If you convert this to farad, you multiply with 10 raised power minus 12. So it will become farad. Is charged by a 100 volt battery. It is charged by 100 volt battery. The electrostatic energy stored by the capacitor will be, you guys are supposed to tell me what is the energy stored by the capacitor. So we say 1 by 2 CV square. Why do we use this particular equation, 1 by 2 CV square? Because if you take a look, capacitance is given, voltage is given. That's why I'm using this one directly. So U is equal to, in this particular case, this will be 1 by 2. Value of C, that is 700. Okay, into 10 raised power minus 12. And then V square, V is given as 100 square. Okay. So it will be 3.5 into 10 raised power minus 6 joules. I hope this is clear. Okay. That's great. Now, force between the plates of a capacitor. Guys, see, let's suppose we have got a plate over here. We have got one more plate over here. Okay. Guys. Since we do store the charge inside a capacitor, how do we store? It is like we store positive charge on this capacitor and we store negative charge on this capacitor. It is not we. It is actually the battery. Let me make you understand how. Guys, see. Let's suppose this is one plate, this is another plate. And you are connecting the battery to this plate. Guys, always remember, this is the positive terminal of the battery. This positive terminal is connected to this plate. This is the negative terminal of the battery. It is connected to this plate. So this battery basically stores the charge. It stores, it charges the capacitor. Like you have the phone. When you buy the battery from the market, okay, that big battery, you want to charge the phone, you'll plug it in, so it will charge the phone. Same you can consider, it is a capacitor over here. You are connecting a battery. Positive terminal means it will occupy positive charge on this plate. Negative terminal means it will occupy negative charge on this plate. Now guys, this is how charge is stored in the capacitor. Guys, see. If positive charge is present on this plate, negative is present on this plate, don't you think that positive charge will attract the negative charge? Yes. Or negatively charged plate will attract positively charged plate. So they will apply the force on each other. That is called force between the plates of a capacitor. And my dear friends, we said two plates will attract each other because of the opposite charges. To find that force with which they are attracting, that force is Q square upon 2A epsilon naught. Q is the charge on the capacitor plates. 2A, A is the area of the plates. Or in terms of sigma also you can write, guys, sigma is the charge per unit area. Sigma square A divided by 2 epsilon naught. This is also the force, sigma square upon 2A epsilon. Okay. NEET 2018, the question was asked. The electrostatic force between the metal plates of an isolated capacitor having charge Q and area A. Guys. The electrostatic between the plates of an isolated capacitor having charge Q and area A. What is the force between the plates of the capacitor? Q square upon 2A epsilon naught. Let's check. Here, which option is correct? Independent of the distance between the plates. Is there the distance over here? No. Is there separation over here? No. So I can say this is correct. Linearly proportional to the distance between the plates. No distance is present here. Incorrect, incorrect, incorrect. So it is independent of the distance or the separation between the plates. Guys, take a look. Just a second, just a second. Okay, now take a look. Common potential, very important. This I have to teach you in the current electricity also. See guys, common potential means, let's suppose you have a capacitor over here, you have a capacitor here, you have a capacitor here. Okay, this is the capacitor, this is the capacitor, this is the capacitor. I want you to understand very carefully. Guys, capacitance of this capacitor is C1, capacitance of this capacitor is C2, capacitance of this capacitor is C3. Okay. Potential, guys, these three capacitors are connected something like this. Potential of this end is V1. Okay. Before this, let me tell you something, guys. Just a second. See. Let's suppose you have got a battery. Okay. You might have seen a lot of times it is mentioned over here 20 volts. This is the symbol of the battery. This is the symbol of the battery cell. You might have seen a lot of times this is 40 volt battery. What is this? This is actually potential difference, delta V. This is actually potential difference. And this is one end of the battery, one terminal of the battery. This is another terminal of the battery. Always remember this point, we say if let's suppose this is A point, it has potential VA. This end has potential. Similarly, we say this potential will be having VB. And always remember, guys, that this potential minus this potential, VA minus VB, will be always equal to this delta V. Will be always equal to this delta V. Similarly, if we say this point, let's suppose this is VA, this is VB. Guys, we say always this is higher end. This is called the higher potential. This is called positive terminal. This is negative terminal. So positive means higher potential. So here also VA minus VB is equal to delta V. Keep this thing in your mind. Now guys, this VA, let's suppose the potential of this end VA over here in this particular case. Let's suppose if I say if VB is equal to 0, find the value of VA. What will you say? Sir, VA minus VB is 0 is equal to delta V. What is delta V? That is 40. So VA will come out to be 40 volts. Potential of this point is 40. One more trick. If I say if VB is equal to 20 volts, find the value of VA. What will you say? We'll say, sir, VA minus VB. VB is 20 is equal to delta V. That is 40. VA minus VB is equal to delta V. So take this 20 over here in this particular case. What will you say? Here, this VA will be VA will be, that is 40 plus 20, that will be VA will be equals to 60. Okay. Now, is this correct or incorrect? How do we check? We say, guys, VA minus VB should be equal to delta V. Now, VA is how much? 60. VB is how much? 20. So 60 minus 20. 60 minus 20 is equal to 40. That is 40. That is 40. Come over here. I have got three capacitors. Potential of this end is V1. It can be anything, 20 volt, 30 volt, 40 volt. Potential of this end is 30. V2. Potential of this end is V3. You have to find the potential of this common end. Directly remember, guys, potential of this, guys, why do we call it the common potential? This end is connected to this capacitor also, this capacitor also, this capacitor also. That's why we say this is the point, which is the midpoint. So this capacitance will be, this potential will be C1 V1 plus C2 V2 plus C3 V3 upon C1 plus C2 plus C3. This is the potential of this point. This is the potential of this point. Common point. Why we call it common point? Because this is common to this. Now, guys, understand one thing very carefully. If we have a question something like this, you are supposed to tell me, find the charge in 4 microfarad capacitor. Also, find VA. Guys. The trick that I am going to tell you in this case will be remembering it for the rest of your life. What is that? That is, first point is, assume 0 volt. If you ever get a question of this sort, assume 0 volt potential. Sir, will it create any difference? It will not create any difference. Assume 0 volt potential. Assume 0 volt potential. Okay. Assume 0 volt potential at a point. If you are assuming 0 volt potential at this point, guys, could you please tell me this potential difference is 20? What is the potential of this end? What is the potential of this end? See, you will say, in this case, sir, if this is CCC, this is the battery. This is 20, this is 0. What will be potential of this? Sir, VA minus VB is equal to delta V, that is 20. So VA will come out with 20. Can I say this point has got potential of 20 volts? Yes. If this is 0, sir, what is the potential of this end? That will be plus 10 volts. Why? Because 10 minus 0 will be 10. 20 minus 0 will be 20. Guys, the wire is straight till over here. This will be also having the potential 20 volts. If this is a straight wire, potential at this point will be same. Until and unless you put some load in between, potential at this point will be different. At this point, it is different. But if it is a simple wire, potential is same. Now, redraw. Guys, if we redraw this figure, can we redraw it right like this? See, guys, this will be over here. This point is 20 volts. This point here is 20 volts. This point, this is plus 10 volts. This point has 10 volts. Okay. This point has got 0 volts. And this is VA. Don't you think in this particular case, VA is the common point? Don't you think in this particular case, VA is the common point? And tell me, guys, over here, if VA is the common point, could you please tell me what will be the potential of this VA and how can we exactly find the potential of this VA point? Tell me. Guys, this is VA. It is exactly like this. VC. So that is C1 V1, C2 V2, C3 V3. So I can say, sir, VA is the common point. Guys, if VA is the common point, can I say, so I can say VC. It will be, or this is VA. VA is equal C1 V1. Guys, C1 is 5. This is 5 microfarad. This is 4. This is 1. C1 V1, that is 5 into 20. Okay. Then plus C2 V2, 10 into 4. 10 into 4. Then C3 V3, 1 into 0 plus 1 into 0 upon C1 plus C2 plus C3, that is 5 plus 4 plus 1. Guys, this is 520 is 100, 140. 140 divided by 14, it will come out to be 10. So this will come out, this is 10 divided by 5 plus 4 plus 1 is 10. So it will be 14 volts. It will be 14 volts. So value of this is 14. Now, you got the potential at A. Now, if you have to find the charge in this 4 microfarad, charge in 4 microfarad. Guys, take this 4 microfarad capacitor. See, this point has got potential 10 volts. This point has got potential recently VA you got 14 volts. And this is 4 microfarad. This is 4 microfarad. If you have to find charge, guys, we say Q is equal to C delta V. Sir, it was C into V. It is actually delta V. Guys, Q is equal to C. C is given as 4 and delta V. Delta V means higher potential minus lower potential. So that is 14 minus 10. 14 minus 10. That is 4. 4 into 4 is Q will come out to be 16 microcoulomb. Charge stored in this case will be 16 microcoulomb. Charge stored in this case will be 16 microcoulomb. Sir, can we find the charge in this also? Yes. Charge in 5. Guys. We say charge in 5 microfarad. How can we say? Q is equal to C delta V. Q is equal to C is 5. Delta V is, guys, this is 20, this is 14. Higher minus lower. 20 minus 14. That is 6. So that will be 30 microcoulomb. So basically, if you ever have to find the charge in any capacitor, try to find out the potential across the ends of the capacitor. You would be able to find out the charge in that capacitor. Please give me the signal in the chats if this is crystalline clear. Everyone means everyone. Whosoever is watching, I want you guys to tell me if this is crystalline clear. Tell me, guys. Everyone means everyone. I want you to tell me if this is crystalline clear. Great. Now, guys, take a look. Dielectrics in capacitors. Guys, see. Let's suppose you have a plate, you have a parallel plate capacitor. Charge on this is positive, charge on this is negative. Recently, you saw that positive plate attracts negative plate. Okay. So, if the two plates attract each other, so they will come close to each other and they'll stick to each other. So the two plates will actually stick to each other. There will no longer remain the separation between the two plates. So means separation will be 0. It will no longer remain a capacitor. When it comes to the capacitor, parallel plate capacitor, separation between the two plates should be there. So my dear friends, if you have two plates, these two plates are attracting each other. They stick to each other. It will no longer remain a capacitor. So what do you do to overcome this problem so that the two plates should not stick? You place a dielectric in between. Sir, what is this dielectric? Dielectric is a material like you have conductors, you have insulators. You place the dielectric in between. Only and only this plate should not stick to this plate. Okay. Now, this dielectric has a charge inside it, its own charge, positive, negative, positive, negative. Now, this positive plate attracts the negative charge of the dielectric, And this negative plate attracts the positive charge of the dielectric, So, guys, after some time, we observe that negative charge of the dielectric is occupied here. Positive charge of the dielectric is occupied here. And if somebody asks you, how much charge is stored, how much charge is occupied on the walls of the dielectric, you say, sir, this is what we call the induced charge. This is the charge induced on the walls of the dielectric. And this induced charge, Qi, is Q. Q is the charge on the external plates. Q into 1 minus 1 by K. This dielectric has a dielectric constant K. Just a sec. Okay, so this is the charge induced on the walls of the dielectric, Q into 1 into 1 minus K. Now, guys, see. What is K? Every dielectric has a dielectric constant. So, like for water, dielectric constant is 81. For air, dielectric constant is 1. For conductor, dielectric constant is infinity. So, this is how you can find the charge stored on the walls of the dielectric. Charge stored on the walls of the dielectric. And this is the sigma, charge per unit area, induced charge per unit area. Guys, this is the total charge on the walls of the dielectric. If I say how much is the charge induced on unit area, that is sigma I is sigma into 1 minus 1 by K. This was, by the way, asked in J Mains 2021. Okay, 1 minus 1 by K, sigma. Sigma is the induced charge. Sigma is the charge density of the external plates. This is the charge induced in the dielectric. I hope this is clear. Now, guys, understand one thing very carefully. Always remember one thing. Guys. There is a statement which is mentioned over here. Let's suppose you have got the two plates over here, positive and negative. And you have got the two plates over here, positive and negative. You have got two plates over here, positive and negative. And between the two plates, you are placing a dielectric. This is the dielectric. Its dielectric constant is K. Statement is, whenever we place dielectric in between the plates, its capacitance changes. If you remove this dielectric here, what is the capacitance of the capacitor? Epsilon naught A by D, that we know. But when you place the dielectric, we say its capacitance changes, its capacitance will change. Okay. Now, guys, what will be its final capacitance? Guys. T is the width. Just a second, guys. I need something for my throat. That's why. I got the chai. Now, guys, see. I say When you place this dielectric in between the plates, its capacitance will change. What will be the capacitance after the dielectric? C is equal to epsilon naught A D minus T. D is the separation between the plates. T is the width of the dielectric. Then we say plus T divided by K. Then we say plus T divided by K. Guys, please don't ask for the break. I have to cover a lot. I'm not skipping any of the topics out there. So if I give you the break, it is not possible for me to finish. Okay. So the maximum time of a live stream is 12 hours. We cannot exceed 12 hours. We'll have to finish this within the 12 hours. So listen very carefully. So we say epsilon naught A upon D minus T plus T by K. This is the capacitance of this capacitor after placing the dielectric of with T distance between the plates is D. Now guys, if you have the multiple dielectrics, here it was only one dielectric. If you have the multiple dielectrics in series and you want to find out the equivalent net capacitance after placing dielectric. Guys, this dielectric has dielectric constant K1, K2, K3. Width is D1, width is D2, D3, D4. Here, capacitance would be this. Epsilon naught A, D1 by K1, plus D2 by K2, plus D3 by K3, D4 by K4. This is also called the series combination of dielectrics. Okay. Now guys, take a look over here. This was the question which was asked in J Mains 2021. You have got a capacitor in which 3 dielectrics are placed. K, 3K, 5K. Okay. You have to find the capacitance here. Guys, tell me. Capacitance will be epsilon naught A. Then D1 by K1. Recently, D1 by K1 plus D2 by K2, D3 by K3 and so on. D1 is D. K1 is K plus. Then you say 2D divided by 3K. Then we say plus 3D by 5K. 3D by 5K. Okay. Now we can say C is equal to epsilon naught A. D by K you can take common over here. 1 plus 2 by 3 plus 3 by 5. So you can say C is equal to epsilon naught A upon D by K. Now this here you can write as, this is 34 divided by 15. So take this in the numerator, it will become 15K you take in the numerator. So it will become 15 by 34 epsilon naught A K divided by D. Option A. Simply formula based. Guys, if you place conductor as a dielectric in between the plates of the capacitor, what will happen? Guys, see. Epsilon naught A by D, D minus K plus T by K. This was the general formula. This was the general formula. Okay. Now for conductor, we say K is infinity. For conductor, dielectric constant is infinity. K is infinity. So it is epsilon naught A, D minus T, T by infinity. So this term will become 0. So simply it is epsilon naught A upon T minus T. D minus T. Okay. Now, parallel combination of dielectrics. Guys, when we talk about the parallel combination of dielectrics, here dielectric slabs are connected or placed parallel. This is a plate of the capacitor. This is negative plate, positive plate, negative plate. One dielectric, another. We say width of this dielectric is A1, width of this dielectric is A2, width of this dielectric is A3. Okay. And if you want to find the net capacitance over here, you say C is equal to epsilon naught by D. A1 K1 plus A2 K2 plus A3 K3. So A1 is this width, K1 is this dielectric, A2 K2, A3 K3. So this will be the capacitance of this dielectric when slabs are placed parallel. Let's suppose on this you have a question. See guys, two slabs are placed over here. This is air, okay? This is air and this is K. You have to tell me what is the capacitance of this capacitor. Guys, slabs are placed in parallel. So we'll use the formula epsilon naught divided by D. A1 K1 plus A2 K2. In case of parallel combination of dielectrics, this is the way to find the capacitance. C dash is equal to epsilon naught divided by D. A1, value of A1 is A by 2. A by 2. And K1 is, for air, dielectric constant is 1. So it is 1 plus A by 2 is also A by 2. A2 is also A by 2. K1 is K. Okay. Now guys, we can say this is epsilon naught A. Guys, here in these two, A by 2 will come out. Epsilon naught A divided by 2D. Then here it remains 1 plus K. Okay. What is epsilon naught A by D? That is the original capacitance without dielectric. You can say C dash is equal to C by 2, 1 plus K. Option A. Is this clear? Is this clear? Great. Now, let's move on to combination of capacitors. Combination of capacitors. Series combination. If you have three capacitors connected in series and you are asked to find the equivalent capacitance, what will you say? Sir, equivalent capacitance will be 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3. If you have to find the equivalent capacitance in series, this will be the way. Okay. Like for two capacitors, guys, for two capacitors, how can you say? So it will be 1 upon C equivalent is equal to 1 by C1 plus 1 by C2. Do the cross multiply. 1 by C equivalent will come out to be C2 plus C1 upon C1 C2. Do the reciprocal. So C equivalent will come out to be C1 C2 upon C1 plus C2. From now onwards, remember this directly. If you have two capacitors in series, you have to find equivalent capacitance C1 C2 upon C1 plus C2. If you have the capacitors in parallel, in case of parallel combination, capacitance will be C1 plus C2 plus C3. C1 plus C2 plus C3. This is the capacitors connected in the parallel combination. Okay. Now this one, you have to find the equivalent capacitance in this case. Guys, see. Let's suppose this is C, this is C, this is C. Guys, in order to solve this kind of problem, directly remember, mark the potential of all the points. First point is, mark the potential of all the points. Mark the potential of all the points. Okay? Okay. Mark the potential of all the points. So my dear friends, if you have this point A over here, so what is the potential of, let's suppose the potential of this is A. What is the potential of this point A? This point A, it's the same wire, same wire, same wire. It is point A. Guys, potential of this point is B. Okay. So this point will also have B potential. So same wire, this point will also have potential B. Sir, can this point have A potential? No, because here capacitor comes in between. I told you, as long as the wire is same, potential will remain the same. Okay. If the load comes in between, then you can't say potential will change. Then you can't say potential. Then you can't say potential remains the same. Now, guys, draw these points on the board over here. So first I'll say A point. Okay. How many points are there? A, B, A, B means only 2 points, A and B. Now, first capacitor is connected between A and B. Second capacitor is connected between B and A. So means same. Okay. Third capacitor is connected between A and B. Guys, it looks like it is the series combination. In reality, it is the parallel combination. C, C, C. So C equivalent in this case is 3C. Let me show you this. This was question asked in NEET 2021. Let's suppose the potential of this point is A. This will have A potential. Here also it will have A potential. Guys. This potential is B. This is B. This will be also B. So this will be also B. Yes. If same potential is across the ends of a capacitor, then it will short circuit. So basically, I want you to remove it. Guys, it will short circuit and it will remove it. You have to remove it. If the potential across the ends of the load is same. Now make this diagram. So I'll make the upper diagram. This one, lower diagram, the upper capacitor, this C, this C. This is point A, this is point B. Now tell me, these two capacitors are connected in parallel. So C equivalent in this case is 2C. Okay, we are done with this. Current electricity. Next chapter, third chapter. Okay. We have got current electricity. Let's begin with the third chapter, that is current electricity in this particular case. Okay. The very first thing that I want you guys to understand is, what is electric current? We say electric current, it is simply flow of charge. Flow of charge is what we call the electric current. Okay. Flow of charge is Wheatstone Bridge. I will teach you in current electricity. That is exactly similar to the Wheatstone Bridge of capacitors. No need to worry about that. See, guys, flow of charge is called the current. What does that mean? I will tell you. Let's suppose we have got a wire over here. This is a wire. Okay. And in this wire, this is a conductor. Wire, or you say conductor. Guys, remember always, whenever you have this conductor, it contains large number of free electrons. It contains large free electrons. Whenever you see a wire, you see a conductor, it contains large number of free electrons. Now, my dear friends, we say these free electrons which are inside this conductor, if they start moving, if these are in motion, okay, if these are in motion, we say they constitute electric current. Whenever inside a wire electrons flow, charge flows, we say it forms what? Electric current. That's why flow of charge is called current. So if somebody wants you to find out the current, you say charge upon time. This is a conductor, charge is flowing, electrons are flowing, current is produced. Now guys, there is a concept that is what we call average current. Average current simply means delta Q divided by delta T. Total charge flown upon total time taken. You can also say Q2 minus Q1 upon T2 minus T1. Guys, let's suppose this is a conductor. In this conductor, charge is flowing. From 9 a.m. to 1 p.m. Charge is flowing continuously. I'm saying how much current was produced from 9 a.m. to 1 p.m. That is called the average current in general. If I say, what is the current at 10:30 a.m. exactly? That is called the instantaneous current. How much is the current at any particular instant is instantaneous current? How much is the current in total? That is from 9 a.m. to 1 p.m., 9 a.m. to 5 p.m. That is average. This is instantaneous. This is average. That's it. That's it. And when it comes to the instantaneous, it is dq by dt. Differentiation of charge with respect to time. Example. Guys. If charge Q is equal to this, let's suppose you have a question. You have a conductor over here. Okay. In this conductor, we say charge is flowing. How much charge? Charge is flowing. Q is equal to 2t square minus 3t plus 1. This is the charge flowing in a conductor. Find the current at t is equal to 2 seconds. You have to find the current at t is equal to 2 seconds. Means you have to find the instantaneous current. At t is equal to 2 seconds means instantaneous. So I can say current instantaneous will be dq divided by dt. So you can say instantaneous current will be, that is d by dt of differentiation of this charge, that is 2t square minus 3t plus 1. So you can say instantaneous current will be simply, that is 2 into 2 is 4t minus 3. Differentiation of 3t is 3. Now guys, I can say in this particular case, at t is equal to 2 seconds, I can say at t is equal to 2 seconds, we say current will be simply, that is 4 into 2 minus 3. 4 into 2 is 8. 8 minus 3 is, that is 5 ampere. So current at t is equal to 2 seconds is how much? 5 ampere. This was the instantaneous current. Now, guys, understand one thing. Previously, I told you, if charge is given, you have to find the current. What do? You do the differentiation. Now see. In this case, current is given. Let's suppose you have a wire. In this wire, current is flowing and that current is 4 plus 2t. You have to find the charge. Means if the current is flowing in this wire, obviously it is because of charge flow. How much is the charge? To find the charge. Reverse. Guys, remember, as when it comes to the current, you say it is dq by dt. Simply, you say current is dq by dt. Can you say over here, when it comes to the dq, multiply here, it will be I dt. Now do the integration from both the sides. Integrate. What is integration of dq? Integration means adding the small quantities. It will give you total charge, that is q. It is integration of I dt. So guys, from now onwards, you'll remember that if current is given, you have to find the charge. You will have to do the integration. So I can say q is equal to integration of I. What is the value of I? That is 4 plus 2t. Then we say dt. And you have to find the charge from 0 to 2 seconds. So you'll be putting over here 0 and you will be putting 2. Okay. Now tell me one thing. Can I say q is equal to, what is the integration of 4? It will be 4t. Guys, I'll not teach the integration differentiation here directly. So 4t plus integration of 2t will be 2t square by 2. This and this will cancel and limits are from 0 to 2. And q will come out to be, guys, 4 into, instead of this t, you will put, guys, first in this t, we will have to put the upper limit, minus lower limit, then plus. Then in this t, you have to put this upper limit, that is 2 square. So how much it will be? 4 into 2 is 8. 8 plus 4 is, that is 12 coulomb. That is 12 coulomb. Is this clear? Simple integration, guys. Simple integration. Okay, one more question. If I is equal to t plus 1, calculate average current. Now current is given, current is asked. Current is given, current is asked. So, guys, in this case, if you have current given and current is asked, always remember, guys, use this formula. I average is equal to integration of I dt upon integration of dt. Guys, let me go back. If charge is given, you have to find the current. You will do the differentiation. Next question. If current is given, you have to find the charge. You will do the integration I dt. But my dear friends, if current is given, you have to find the current only. Then you will do this. Now see, what will I do? I say integration of I. Instead of I can write t plus 1. And then I say dt upon integration of dt. Now from where to where you have to find average? 0 to 2. Put the limit 0, put the limit 2, put the limit 0, put the limit. Now I can say, guys, t plus 1. What is the integration of t? That is t square by 2. What is the integration of 1? That is t. Okay. And limits are from 0 to 2. Then integration of. We say, sir, integration of dt will be t only. And limits are from 0 to 2. Now, put the upper limit in t. So it will be 2 square divided by 2 plus. Put the upper limit in t. That is 2 divided by. Put the upper limit over here. That is 2. Now 2 square is 4. 4 into 2. This will be 2. 2 plus 2 is 4. So this will be 4 divided by 2. It will come out to be 2 ampere. Okay. Is that clear? Okay. Guys, give me the signal in the chats. Is this crystalline clear? With the fire emojis, I want everybody of you to give me the signal in the chats. If this is crystalline clear, everyone means everyone, whosoever is watching. Sir, is the NEET PYQs, JEE main PYQs and mock test chapter wise enough for physics for now as I have boards? No. Yes, that's more than sufficient. NEET PYQs, JEE mains PYQs are not enough. That's not, we say, mandatory for the NEET. I would recommend you to go with any of the coaching modules out there, previous year questions and teachers' questions and NCRT questions. That's more than sufficient. Do you know Shimon sir? Yes, I know him. He's Wasim sir's very close friend. but I know him also. Okay. Now guys, take a look. Listen to me very carefully. Let's say take a look at this table. Guys, from now onwards, you'll remember that if charge is given, okay, if charge is given, and you will have to find the current instantaneous, you'll do the differentiation dq by dt. Already, I have shown you. If charge is given, you have to find the average current. Then you will have to basically use delta q by delta t, simply q2 minus q1 upon t2 minus t1. That's it. Now guys, if current is given, you have to find the average current. You will have integration of I dt upon integration of dt. Next one, if current is given, you have to find the charge. You'll do the integration of I dt. This is the table that you guys are supposed to remember. All the questions will be from this one. Next, drift velocity. Guys, see, let's suppose we have got a conductor over here. In this conductor, there are large number of free electrons. In this conductor, there are large number of free electrons. Okay. Conductor means wire. What you do over here is you connect a battery to it. This is the battery which you are connecting. Always remember, guys, this battery will set up the electric field. The work of the battery, it will set up the electric field. How? This positive terminal occupies the positive charge on this side. Okay. This negative terminal occupies the negative charge on this side. And electric field is always from positive charge to negative charge. Because we saw in electrostatics, because of positive charge, electric field is away from the charge. Because of negative charge, it is towards the charge. So as a whole, electric field is from positive to negative charge. So electric field will be from positive to negative charge. Now, because of this charge, guys, because of this electric field, the electrons inside this conductor, this charge inside this conductor will experience the force. We know if we place a charge inside an electric field, it experiences the force. So these electrons will experience the force. These electrons will experience the force in opposite direction. So they start moving in the opposite direction. Now, if they start moving in the opposite direction, they will gain some velocity. That velocity is called drift velocity. It is the velocity due to which free electrons are drifted towards the positive terminal or drifted towards the positive end of the conductor. We have a conductor, we applied battery. Because of the battery, electric field is set up. Because of the electric field, electrons experience force. Because of that force, electrons will move. They will gain some velocity. That velocity is called drift velocity. So basically, drift with the help of drift velocity, electrons are drifted in a conductor. And the value of this drift velocity is E. This small e is charge on an electron. This capital E is electric field. Okay, this electric field. This m is the mass of the electron. This tau is the relaxation time. E by m into tau. This is the value of drift velocity. Next, relation between drift velocity and current. Guys, tell me one thing. I am saying this is the conductor. You connected battery. Electric field is set up. These electrons experience the force. They start moving with a drift velocity. When they move with a drift velocity, when the charge moves, when the electrons move, we say current is being produced. Here, electrons are being drifted due to the drift velocity. So, current is being produced. And how much will be that current? NEAVD. That current will be, which is because of the drift velocity of electrons, will be N. N is the number of free electrons per unit volume. in the unit volume, how many number of electrons are there? E is the charge on an electron. Area A is the area of cross section. Vd is the drift velocity. Vd is the drift velocity. NEA Vd. Okay. This is called the relation between current and drift velocity. NEA Vd. Take a look at the question. The drift velocity of free electrons in a conductor is V. Okay. The drift velocity of free electrons in a conductor is V. If the radius of the conductor is doubled and current is also doubled, find new drift velocity. Guys, see. We say I is equal to NEAVD. Okay. Yes. Can I say this drift velocity will be simply, that is I upon NEA. Let's suppose if we have this conductor, cylindrical conductor. In case of cylindrical conductor, this side will have the radius. This area of cross section will have the radius r. Then we say area of cross section will be pi r square. Always remember this is pi r square. Then can I say this drift velocity will be I upon NE. Instead of area, I can say pi r square. Now guys, what does the question say? If the radius of the conductor is doubled, means r dash becomes 2r if the radius is doubled. And current is also doubled, means current I dash is also 2i. We have to find new drift velocity. Guys, how do we find that drift velocity? Vd is equal to I. Instead of I can write 2i. I upon NE pi r square. I can say pi, and instead of r I can write 2r whole square. So Vd in this case will be, that is 2i upon, this is NE pi, 2 square is 4 r square. So 2 1s are 2 2s are. So I can say in this particular case guys, Vd will come out to be, that is I upon NE pi or 2 NE pi r square. I upon NE pi r square, that is Vd, and that is given as V. The drift velocity is V initially. So Vd will become V by 2. So drift velocity is halved. Drift velocity is halved. Okay. So drift velocity is halved. So V by 2 is the answer. Current density. Guys, see, when it comes to the current density, let's suppose you have a conductor over here. Okay, you have a conductor over here, and in this conductor, let's suppose the current I is flowing. Okay, you are taking the area. Okay, let's suppose area of the cross section is, we say, A. What is current density? Current density is simply how much current is flowing through the cross-sectional area, unit cross-sectional area. Sir, if I say more current is flowing over here, then we say density of current is more. If I say less current is flowing over here, we say density of current is less. So in this particular case, it is simply current divided by area. Current density is simply, we say current flowing through the unit cross-sectional area. I divided by A. I divided by A. Okay, I divided by A. I divided by A. So it is current flowing through unit cross-sectional area. J is equal to I by A. It is J is equal to I by A. So my dear friends, you have got the cross-sectional area over here, and this is J, this is J. So we say J is equal to I divided by A. More is the current, more will be the current density. Okay. And here you can also say, I is equal to J dot A. You can also say I is equal to JA cos theta. I is equal to JA cos theta. Okay. This is also the formula of current density in this particular case. Now guys, current density in terms of drift velocity. What is the relation between current density and drift velocity? Guys, J is equal to I by A. J is equal to, instead of I can write NEA VD. Instead of I can write NEA VD divided by A. Now, can I say this A and A will cancel? So, J is equal to NEVD. So, this is the relation between, this is the relation between, we say, current density and drift velocity. This is the relation between current density and drift velocity. Next, guys, see, the current density, drift velocity at A, B and C will be. Let's suppose this is a conductor and this is a neutral conductor. Okay. Guys, always remember, if let's suppose 10 electrons are coming from this side, so 10 will cross A, 10 will cross B, 10 will cross C. So always remember, whatever is the current at A will be current at B, will be current at C. Current always remain the same. Current always remain the same. Okay, because in case of a neutral conductor, the amount of electrons crossing A will be the same as B, will be the same as C. Now guys, tell me one thing. What about current density? As J is equal to I by A. Guys, current is constant. J is inversely proportional to area. I can say ABC, area of cross section here, area of cross section here, area of cross section here. I can say I, A are same at all the 3 points. So current density at A is equal to current density at B is equal to current density at C. Let's talk about drift velocity. Guys, as we say J is equal to NEVD. So current density is directly proportional to drift velocity. So whatever is the relation of current density, same is the relation of drift velocity. So VA is equal to VB is equal to VC. Next, this one. Guys. If 10 electrons are crossing A, 10 will be crossing B, 10 will be crossing C. So current at A is equal to current at B is equal to current at C. What about drift velocity? Current density, J is equal to I by A. Guys, here area is less. So if area is less, current density is more, inversely proportional. So I can say J is inversely proportional to area. So can I say, guys, I can say current density at A is greater than current density at B is greater than current density at C. Because area is less, current density is more. Here area is more, current density is less. Here area is more, current density is less. Similarly, J is equal to NEVD. So J is directly proportional to VD. Whatever is the, we say, value of current density, same will be for drift velocity. It is directly proportional. So I can say VA is greater than VB is greater than VC. It is obvious. Here area is less. So electrons will have to move faster. Area is more, electrons will bit slowly. Ohm's law. Guys, take a look. Take a look here. Let's suppose we have a conductor over here. Okay. You are connecting a battery. Due to the battery, electric field is set. Because of the electric field, electrons will experience the force. Electrons will experience the force. Due to the battery, electric field is set up. Force acts on the electrons. So if force acts on the electrons, electrons will start moving. So current is produced. Okay. Now guys, you are saying, guys, see. Because of the potential difference, electric field is set. Because of electric field, electrons experience force. Because of that force, electrons move and current is produced. If You apply the stronger battery which has got strong potential difference, 100 volt, 200 volt. Okay. So we say strong electric field will be set up because it will occupy more charge here, more charge here. So electric field is more. We say it will apply strong force here. More electrons will flow, more current is produced. This is proportional to this. This is proportional to this. This is proportional to this. So can I not say V is proportional to I? If potential difference across the ends of the conductor is more, then current will be more. That is potential difference across the ends of the conductor is proportional to the current. If you apply more potential difference, current will be more. If you apply less potential difference, current will be less. As simple as that. So V is directly proportional to I. Replacing the proportionality with a constant, that is R. So V is equal to R into I. This is called the Ohm's law. What does Ohm's law say? Ohm's law says that potential difference across the conductor is directly proportional to the current produced in the conductor. If you apply strong potential difference across the conductor, more current will be produced. Current produced will be stronger. It is directly proportional to V is directly proportional to I. This is called the Ohm's law. Okay. Now guys, graph between V versus I. Graph between V versus I. Tell me here, in this particular case, guys, graph between V versus I will be straight line. V is directly proportional to I. Okay. Guys, in this case, if you want to find the slope, always remember, slope is tan theta. Slope is tan theta. Tan theta means this perpendicular, if you take it over here, perpendicular divided by base in this triangle, if this is theta. So that is perpendicular by base. Perpendicular is V divided by I. Okay. Now tell me one thing. Guys, let's call this as equation first. Can I say, as we know, we recently studied Ohm's law. V is equal to I into R. Ohm's law is V is equal to I into R. V is directly proportional to I. Can I say here, in this case, sir, this R will be equals to V divided by I. Call this as equation second. Now, here V by I is slope. Here V by I is R. So can I say from first and second? Can I say from first and second? Guys, slope is equal to R in case of VI graph. So my dear friends, from now onwards, you'll remember that in case of V versus I graph, if you want to find out the slope, you will have to find out the resistance. Because in case of V versus I graph, slope is given by the resistance. In case of V versus I graph, slope is given by the resistance. Okay. Is that clear? Is that clear? In case of V versus I graph, if you want to find out resistance, what will you find? Slope. Now take a look here. Guys, I versus V graph. Tell me, what is slope over here? Slope is perpendicular by base, that is I divided by V. Call this equation first. Now. Since you say, as we know, you recently saw that R is equal to V by I. Resistance is V divided by I according to Ohm's law. Do the reciprocal. So can I say V divided by I divided by V is equal to 1 by R. Call this as equation second. I by V is slope. I by V is 1 by R. So can I say here from first and second, I can say slope is inversely proportional to resistance. Slope is equal to 1 by R. And this is in case of IV graph. In case of IV graph. What I'm trying to say is that if you get a graph from, I'll show you the questions also, V versus I, and they ask you to find the resistance, you'll find slope. And in case of I versus V, if they ask you to find the resistance, you find inverse of slope. Like, let's suppose you have this question. Guys. Compare the resistance of wire A, wire B, wire C. This is V versus I graph for A wire, B wire, C wire. Okay? Guys. We know in case of V versus I graph, in VI graph, V is slope is directly proportional to resistance. Okay, so the one which has more slope will have more resistance. This has less slope, more slope, more slope. So can I say here, slope of A is greater than slope of B, because this is more steeper, its angle is more, is greater than, I can say, slope of C. So I can say resistance of A is greater than resistance of B is greater than resistance of C. This wire has more resistance as compared to this, as compared to this. Similar question in this one. Wait. Let me make it over here. Okay, let me write it over here. Tell me, guys. Let's suppose you have I versus V. Wire A, wire B, wire C. This is A, this is B, this is C. Tell me which has got more resistance. We say in case of IV graph, here, slope is inversely proportional to resistance. So, slope of A is greater than B is greater than C. I can say resistance of A is less as compared to resistance of B as compared to resistance of C. Give me the signal in the chats. Give me the signal in the chats. Is this crystalline clear? I would want you guys to tell me in the chats. Is this crystalline clear? Tell me, guys. Is this crystalline clear? Okay. You have to compare in this particular case. What is mentioned? Nothing is mentioned. Huh? Temperature of wire 1, temperature of wire 2. Just a second, I'll see what they have asked in this one. I versus V. Okay, we have to compare the temperature in this case. Okay. We have to compare the temperature in this case. Guys, see here in this particular, compare the temperature of two wires. Guys, this is V versus I graph. So in V versus I graph, resistance is directly proportional to slope. We say here R1 is greater than R2. Guys, always remember this resistance is directly proportional to temperature. Temperature is directly proportional to resistance, because in a conductor, if you increase the temperature of a conductor, inside the conductor there are a lot of ions which are atoms, ions, molecules which start vibrating. So if the electrons are moving inside the conductor, they will have to face more collisions. If they face more collisions, means resistance will increase. So there will be the resistance in current. Resistance will increase. If resistance increases, it is because of temperature. So I can say T1 is greater than T2. Temperature of this wire is greater than this. And here in this case, I say resistance of 1 is less than resistance of 2. Why? Because in case of I versus V graph, slope is inversely proportional to resistance. The one which has more slope has got less resistance. This has more slope, its resistance is less. So I can say here temperature of 1 is less than temperature of 2. And because you said temperature is directly proportional to resistance. Slope means tan theta. Slope means tan theta. Slope means tan theta. If theta is more, slope will be more, tan theta is more. That's why I'm saying. Okay. Let's take a look. Okay, for non-ohmic conductors, guys, what are ohmic conductors? Ohmic conductors are those conductors which follow Ohm's law. And guys, wait, I'll give you the break at 6 p.m. At 6 p.m. we'll be taking the break for 25 minutes. 25 minutes or 20 minutes, 20 minutes break. Okay. 20 or 25 minutes. Let's see. At 6 p.m. Chill. Now, my dear friends, what I'm trying to say in this particular case, non-ohmic conductors are those conductors which does not obey Ohm's law. What is Ohm's law? Ohm's law is potential difference is directly proportional to current. If I say, sir, potential difference is directly proportional to current square. Is this Ohm's law? No, this is not Ohm's law. Potential difference does not linearly vary with current, or current does not vary linearly with potential difference. Okay. So it's not Ohm's law. It should be power 1, power 1. So when it becomes square, it does not remain Ohm's law. In case of non-ohmic conductors, sir, does current vary with the potential difference? Yes, but not linearly. Okay, not linearly. We say here V is not linearly proportional to current. Okay. Now, can I say, let's suppose this is point A, this is point O, this is point A, this is point B. Guys, from O to A, graph is a straight line. From O to A, I is directly proportional to V. So, from O to A, I is directly proportional to V. So, it follows Ohm's law. Ohm's law. Okay. Then, from, we say A to B. A to B, it does not. It does not. From A to B, it does not. So, my dear friends, what I'm trying to say is that if you have a conductor, you are applying potential difference. You say, sir, potential difference is 1, current is 1. Potential 2, current 2. Potential 3, current 3. Sir, if in a conductor, you are applying potential difference 1, current is 10. Current does not linearly vary with potential difference. So, means it is not following the Ohm's law. But current is increasing with the potential difference. So, if the graph is a curve, means it is not following the Ohm's law. If the graph is a straight line, that's why I made over here. In case of the Ohm's law, all the graphs that I made over here was the straight line. So here it is not straight line. Like for semiconductor, this is the graph of I versus V. See, it is a curve. It's not a straight line. In case of a semiconductor graph, this is how current varies with the potential difference. This I'll teach you in the semiconductors. Now guys, let's talk about the resistance. We say, what is the resistance? Let's suppose I am saying I have got a conductor over here. I have got a conductor over here. Okay. And in this conductor, electrons are flowing. So these electrons have to face a lot of collisions. Okay. So while facing these collisions, so these collisions are creating, these ions, atoms, molecules are creating the hindrance to the flow of electrons. So this hindrance is what we call the resistance. Now tell me, in this case, if the length of the conductor is more, these electrons which make the current has to face more collisions, so resistance will be more. If area of the conductor is bigger, the electrons can flow easily with less collisions, so resistance will decrease. R is inversely proportional to area. So we say resistance of a conductor is equal to rho L divided by A, where rho is called the resistivity of a conductor. It is the, I'll just write over here, it is the opposition to the flow of electrons. And value of resistance is rho L divided by A, where rho is called the resistivity. Where rho is called the resistivity. Okay. Okay. Where rho is called the resistivity. Now, my dear friends, I say resistance is proportional to the length. Resistance is inversely proportional to the area. So I can say R is equal to, combine these two, R is equal to rho L by A, where rho is called the resistivity. Well, rho is called the resistivity. Now, my dear friend, let's take a look over here. Let's take a look over here. Let's suppose I am saying I have got a conductor over here. Okay, I have got a conductor over here. And radius of this is R. Radius of this is R. Radius of this is R. I'm saying you the simple thing. Length of this is L. What is the resistance of this conductor? You say, sir, resistance is rho L divided by A. Now you say, sir, rho, length is L. Area of cross section, that will be pi R square. Pi R square. Okay. Now see the question here. This is a conductor. It is like that pipe. It is like that pipe. Okay. Inside it is hollow. Inside it is hollow. This is the hollow portion. Oh, okay. It is air. So current does not flow through the hollow portion. It does not flow through the air. Current flows through this portion only. Here. This is matter is present here. Okay. Matter is filled here. So current will flow through this portion only. Through this portion only. So if current flows through this portion only, we say this portion only will offer the resistance. This portion will only offer the resistance. Now guys, listen to me very carefully. We say radius of this portion, inner cylinder, this is kind of concentric cylinders. Inner, it is like this, guys. It is like hollow from the inner side, and it has got the width. Okay, this portion will have the width. So current will flow through this portion. Now, in this case, guys, could you please tell me the area through which current is flowing? Current is flowing. The area through which current is flowing. Guys, what is the whole area? Area from this to the outer side, it is 3R. And area of this inner side is R. So current does not flow through this R portion. Current flows through this portion only, this portion. How to find this? Guys. So this area will be, that is pi into 3R whole square. Pi into 3R whole square minus this area, that is pi into r square. So you find the whole area from center to the outside, then minus subtract this portion, you will get this area. So how much is that? That is 3r whole square, that is 9 pi r square minus pi r square. So it will be 8 pi r square. So current is only flowing through 8 pi r square. I hope this is clear. Current is flowing through this portion of the, it is something like this. Guys, let me show you over here. So this is hollow. So current is flowing through this portion only. This portion only. Okay, this. So current does not flow through here. So you have to find this area. That is whole area minus this area. That will be this area. I hope this is clear. I hope this is clear. Now let's find the resistance. So if current is flowing through this portion only this portion will create the resistance. So resistance will be rho L divided by 8 pi r square. Rho L divided by 8 pi r square. As simple as that. Okay. Let's take a look at this. Resistance in terms of mass and length. Guys, this is the resistance rho L divided by area. This is the resistance of the conductor in terms of length and area. In terms of length and area. But if you want to find the resistance of the conductor in terms of mass and length, guys, see. I say in terms of mass and length, this resistance will be rho L square divided by m into, we say, d. What is this d? D is the density. D is the density of the material. D is the density of the material. Like this conductor is made up of some material. What is the density? Rho is the resistivity, D is the density. Rho is constant, D is constant. So I can say this resistance will only depend upon, it is proportional to L square by m. Resistance is proportional to L square by m. Now guys, resistance in terms of mass and area. That formula of resistance which is in terms of mass and area, I can say that is rho is equal to rho m divided by dA square. Rho is resistivity, D is density. For every material, it has got the resistivity. Okay, resistivity basically is, resistivity is the ability of a conductor. Resistivity is the ability of a conductor to produce. Resistivity is the ability of a conductor to produce. Resistivity is the ability of a conductor to produce the resistance. Resistivity is the ability of a conductor to produce resistance. If this conductor has got more resistivity, okay, if this is the material, if it has got more resistivity, means it has got more resistance. Tendency of a material to produce the resistance, that is resistivity. So R is proportional to m by a square. Like there is a question over here, I want you guys to focus. Mass of the 3 wires are in the ratio of 1:3:5. Masses, let's suppose we have got 3 wires over here. Okay, 1, 2 and 3. Masses of the 3 wires are in the ratio of 1:3:5. So we are given M1 is to M2 is to M3. This ratio is given as 1:3:5. And length of the 3 wires are given as And length ratio is given as L1 is to L2 is to length of this is to length of this is to length of this. This is given as 5 is to 3 is to 1. We have to find the ratio of resistance. Guys, we have to find R1 is to R2 is to R3. Now tell me what is given? Mass is given, length is given. Do we have any relation of resistance in terms of mass and length? That is R is proportional to L square by M. Sir, rho and D are constants. P wires are made of same material over here. Okay. So R is proportional to as R is proportional to L square by M. So my dear friends, R is proportional to L square by M. What is L? L is 5. For first wire it is 5. So it is 5 square divided by L square by M. Then we say is to. Guys, what is L? L square of this, length of the second wire, that is 3. So 3 square by 3. Mass of second is 3. Mass of third is 1. Okay, sorry, length of third is 1. So I can say 1 square divided by mass of third is 5. Okay, so how much this will be? 5 square is 25 is to. This is 3 square is 9 by 3 is to. I can say this is 1 by 5 in this particular. Okay, 3 ones are 3 threes are 9. Okay, so this will be 25 is to 3 is to 1 by 5. So this will be 125 is to 15 is to 1. So this will be 125 is to 15 is. Okay. I hope this is clear. I hope this is clear. Now guys, take a look over here. Temperature dependence of resistance and resistivity. Temperature dependence of resistance and resistivity. I would want you guys to focus exactly over here. Guys, see. Let's suppose you have got a material over here. Let's suppose you have got a conductor over here. Okay. You have got a conductor over here. Okay. Now guys, its resistance initially is R0. R0 is the resistance initially. R0 is the resistance at temperature Ti initially. Okay. Now guys, if temperature is increased, understand one thing very carefully. If temperature is increased, we say because of increase in temperature, I have told you the collisions inside this material will increase. Collisions increase. So resistance will increase. Okay. Let's suppose if it's a conductor, if resistance increases, so I can say, so at temperature T final, resistance is RF. At temperature TF, resistance is RF, final resistance. Now if somebody asks you what is the value of that final resistance, that will be RF is equal to R0. R0 is the resistance of the material at Ti temperature, initial. Then when you change the temperature, its resistance also changes. Because resistance depends upon temperature. If you change the temperature, resistance will change. So RF is equal to R0 1 plus alpha delta T. Alpha is the temperature coefficient in this particular case. Okay. And delta T is the change in temperature. Okay. And delta T, where you can say delta T is final temperature minus initial temperature. If somebody asks you, if you have a material over here, you are increasing the temperature of the material, what will happen to resistance? Its resistance will change. So what is the value of final resistance? R final is equal to R initial 1 plus alpha delta T. R naught is the temperature at Ti. Rf is the temperature at Tf. Alpha is the temperature coefficient. Delta T is the change in temperature. Similarly, guys, its resistivity will also change. Its final resistivity will be rho f is equal to rho naught 1 plus alpha delta T. Simply you remember, if you change the temperature of a material, its resistance will change. Final resistance will be this. Now, I know a lot of people will be confused over here. What is this alpha? Guys, directly remember, when it comes to alpha, for a conductor, we say value of alpha is positive. Value of alpha, this alpha basically gives you an idea. If in a material, if you increase the temperature, will the resistance increase or decrease? Like, guys, if alpha is positive, we say R final in case of temperature conductor, R naught 1 plus alpha delta T. Tell me one thing. If you keep alpha negative, then R naught minus something will be this. R naught is the initial resistance. So initial resistance minus something. So final resistance will decrease. But no, if you keep alpha positive, so what will be the final resistance? R final will increase. So basically, alpha gives you an idea. If you increase the temperature of a conductor, then its resistance will increase. Why? Because alpha for a conductor is positive. Because if you keep positive over here, something plus R naught means it is increasing. And then when it comes to a semiconductor, we say for a semiconductor, we say alpha is negative. If alpha is negative, we say final resistance will be R naught 1 minus alpha delta T. Final resistance will be 1 minus alpha delta T. Guys, in this particular case, something is subtracted from initial resistance. Guys, initially resistance was 10 minus, let's suppose value of this is something, let's suppose 2. So 10 minus 2, final resistance will be 8. So resistance has decreased. So in this case, our final will decrease. So basically alpha gives an idea. What happens to the final resistance? Guys, tell me in the chats, is this clear? Is this clear? Everyone means everyone. Quick. Tell me. Tell me, is this clear? With the thumbs ups in the chat, guys. I'll give you the break at 6 o'clock exactly. Okay. Now take a look. Guys, let's suppose we have this question. You have to find VA minus VB. What is given? We are given a branch over here. In this branch, you have got a resistance. You have got a battery. You have got another resistance. You have got another battery. You are supposed to tell me what is the value of VA minus VB. You are supposed to tell me what is the value of VA minus VB. Cool. Now guys, take a look. In this particular case, what I want you to understand is, the first thing is select the path. Okay, select the path. Guys, before selecting the path, if I am saying the direction of current is this, if you ever get a question like this, I'll show you one, rest of the questions you have to solve. If the direction of current is this, 2 ampere, always remember current flows from higher potential to lower potential. So my dear friends, this will be the positive higher potential. Positive means higher potential. This will be the lower potential side, because current always flow from higher to lower. If the direction of current was this, then this would have been positive, this is negative. Similarly, in this case, this is positive, this will be negative. Done? Then select the path. Whatever the path you want to select. Sir, I'll select the path from B to A or A to B. Whatever you want to select. Let's select the path from A to B. From A to B. Okay. So first mark the higher potential, lower potential. Second, select the path. Done? If you selected the path from A to B, you write the first potential of this point A. Okay. Then you have to write the potential drop of this. Guys, in case of resistance, how do you write the potential drop? V is equal to I into R. So V is equal to I into R. I is 2, R is 3. 2 into 3 is 6 volts. Then potential drop of this is 4. Potential drop in this resistance is I into R. I is 2, R is 5. 2 into 5, that is 10 volts. Select the path A to B. Then you write this potential, that is 6 volts over here. Okay? Cool. Now tell me one thing. If your path is from A to B, if this is your path from A to B, you are moving from lower to higher or higher to lower? You are moving from, this is moving from lower to higher. When you move from low to high, you have to take this potential drop as positive. Remember, on moving from low to high, take potential drop as positive. Okay. And if you move from high to low, then you have to take potential drop as negative. Then guys, here, this is positive terminal of this is negative. You are moving from higher to lower. So its potential drop 4 volt you have to take as negative. Then here you have to move from, you are moving from low to high. Its potential drop will be plus 10 volts. Then potential drop of this battery, it will be minus 6 volts, because higher to lower, is equal to finally you reach point B. Again, I'll repeat. If you are selecting the path from A to B, first you have to write the potential of this, that is VA. Then potential difference of this, that is 6 volt. Now positive or negative. If this is your path, so means you are moving from higher to low to high. So its potential drop will be negative. Here, you are moving from high to low. Its potential drop will be negative. Here, you are moving from low to high. Its potential drop will be positive. Here, you are moving from high to low. Its potential drop will be negative. Now guys, tell me in this case, this is 10 plus 6 is 16. 6 plus 4 is 10. So this is VA. Then we say plus 16 volts. Then we say minus 6 plus 4, that is 10 volts, is equal to VB. Okay. Okay. Now tell me 16 minus 10, that is 6. So VA plus 6 volts is equal to VB. So you say VA minus VB will come out to be minus 6 volt. Let me show you one more. That will take the confusions out. This was the question asked in NEET 2016. Guys, this is the direction of current. So first and the foremost thing is, can I say current always flow from higher potential to lower? So this will be high, this will be low. Here also, this will be high, this will be low. Then select the path. I am selecting the path from A to B. Then write the potential of this point first if you are selecting the path from A to B. So VA. Then potential drop of this. So that will be V is equal to I into R. I is 2, R is 2. 2 into 2 is 4 volt. 2 into 2 is 4 volt. Potential drop of this. That is 2 into 1 is 2 volt. Now tell me, VA. Potential drop of this is 4 volt. I'll write 4 volt. Now positive or negative? You are moving from higher to lower. This is your direction of the path. It will be minus 4. Here, you are moving from higher to lower. So minus 3. Here, you are moving from higher to lower. So minus 2 is equal to V. Now 4 plus minus 4 minus 3 minus 2. So it's minus 9. VA minus 9 volt is equal to VB. So you can say VA minus VB is equal to 9 volts. Done. Is this clear? I hope now this pattern of questions you would be able to solve very easily from your end. Okay. Midpoint potential in case of current electricity. I'll give you the break exactly at 6 o'clock. Midpoint potential in case of current electricity. Guys, see, let's suppose you have got 3 resistors connected over here. Potential across, this is R1, R2, R3. Potential of this end is V1. Potential of this end is V3. Potential of this end is V2. Don't you think that this is the common end? This is one end of this resistor also. This is the end of this resistor also. This is the another end of this resistor also. This is common end. What is the potential of this common end? In case of capacitors, it was C1 V1, C2 V2 plus C3 V3 upon C1 plus C2 plus C3. But here, I'm saying potential simply is V1 by R1, V1 by R1 plus V2 by R2 plus V3 by R3 upon 1 by R1 plus 1 by R2 plus 1 by R3. As simple as that. This is how we find the midpoint potential here. Okay, like you have the question. You are supposed to find the potential of this point. Guys. I have told you previously, when it comes to the question of this type, consider the potential 0 at any point. Consider the potential 0 at this point. Now tell me, if there is 0 potential at this point, what will be the potential of this end? What will be the potential of this end? Sir, this is 0. Potential of this end will be plus 20 volts. 20 minus 0 will be 20. If this is 0, potential of this end will be plus 10 volts because 10 minus 0 will be 10. If this is, okay, if this is 20, here also it will be plus 20. If this is 10, here also it will be plus 10. Okay. Now tell me, redraw this diagram and tell me what is going to be the answer in this particular case. Redraw the diagram and tell me what is going to be the answer in this particular case. Tell me, guys. So if we redraw it, guys, this resistance, you have this resistance, you have this resistance. So this is plus 20 volts, this is plus 10 volts, and this is over here 0 volts. And you are supposed to find the value of Vm. You are supposed to find the value of Vm. Okay. And this is 10 ohms, and this is 5 ohms, and this is 20 ohms. Guys, tell me how to find the value of Vm. That is V1 by R1. V1 is 20, R1 is 10. That is 20 divided by 10 plus V2 by R2. 10 by 20, 10 by 20 plus V3 by R3, that is 0 by 5 upon 1 by R1, 1 by 10 plus 1 by R2, 1 by 20 plus 1 by 5. Solve this, it will come out to be 50 by 7. So potential of this point is 50 by 7. Now, guys, always remember, if you want to find out, let's suppose if somebody asks you, what is the current in this resistor? Current in 20 ohm. Guys, see. How do we find current? Let's make this 20 ohm resistor over here. This is 20 ohms. Potential of this end, it is plus 10 volts. Potential of this end that we recently got, it is 50 by 7. Plus 50 by 7. You have to find current in this one. Guys. Always remember, current is delta V by R. Sir, what is this? V is equal to I into R. I is equal to V by R. What is this V? This V is actually delta V. Potential difference. Potential difference. Vm is equal to V1 by R1. Formula here is V1 by R1, potential of this end, resistance of this one. V2 by R2, V3 by R3. Same I'm using. V1 by R1, V2 by R2, V3 by R3. Then 1 by R1, 1 by R2, 1 by R3, 50 by 7. Then take this resistor. What is the potential of 1 and 10? What is the potential of this that we recently got? 50 by 7. Now use I is equal to delta V by R. Delta V will be higher potential minus lower. Which one is higher? This one is higher than this. 10 is greater than 50 by 7. So you say 10 minus 50 by 7 divided by R. R is 20. How much is this? Guys, this is 70 minus 50 divided by 7. So this is 70 minus 50. That is how much? This is 70 minus 50. That is 20 divided by 7 upon 20. Okay. Is that cool? So that will be 1 by 7. That will be 1 by 7. So current will come out to be in this case 1 by 7 ampere. Is this clear? Is this clear? Please tell me in the chats. Similarly, if you want to find the current in this one, what will you say? I is equal to delta V by R. So higher potential minus lower potential. Okay, so you can find the current in this one. I hope this is clear. Okay. This question I want to show you. This was asked in J Mains 2021. Okay. Guys. Find the potential difference across AB. In this branch, this is an open branch. Current in this branch will be 0. Current in this branch will be 0. So remove this. Okay. And remove this. When you remove these two, it will be something like this. Why did I say current in this branch and this branch is 0? Because current always flows in a closed loop. Current does not flow in open branch. So you can remove this and this resistance. So it will be something like this. Okay. So this is 1 volt, 2 volts, 3 volts. This is 1 ohm, 1 ohm, 1 ohm. I would want you guys to focus exactly over here. Now this is point A. Now this will behave like point A. This will behave like point B. Assume 0 volt potential at this point. If you are assuming 0 here, what will be potential at this point? 0. What will be potential at this point? 0. If this is 0, this is 1 volt. What is the potential of this point? 1. If this is 0, this is 2. What is the potential of this? That is 2. If this is 0, this is 3 volt. What is the potential of this? That is 3. Now guys, this is point A. Redraw this figure. Guys, you can say it is something like this. Okay, so this is point A, VA. This point has got potential 1 volt. This is 1 ohm. This point has got potential 2 volt. This is 1 ohm. This point has got potential 3 volt. This is 1 ohm. Now you want to find the value of VA. Simple. Sir, VA is equal to V1 by R1, 1 by 1, plus V2 by R2, that is 2 by 1, V3 by R3, that is 3 by 1, plus 1 by R1 plus 1 by R2 plus 1 by R3, 1 by R1 plus 1 by R2 plus 1 by R3. How many of you understood this, guys? Huh? So in this particular case, A will come out to be, that is 2 volts. Potential of this is 2 volts. Okay. So you were supposed to find potential difference between A and B. So VB is 0. You can write it VA minus 0 is equal to 2 volts. So instead of 0, you write VB. VA minus VB is equal to 2 volts. I know I was a bit fast over here because I have shown you some questions on the same topic before. That's fine. So you can repeat it later on if you get any sort of confusion. Tell me in the chats, is this clear? Everyone, tell me in the chats, is this clear? Is this clear? With the fire emojis, I would want you guys to tell me in the chats if this is crystal and clear to each and every single student whosoever is watching. Series and parallel combination of cells. Series and parallel combination of cells. Okay. Guys, understand one thing very carefully. You want me to give the break to you? Okay. Let's take the break, guys. Let's take the break. Break till, what's the time right now? 6:20. Okay, guys, let's take a look. Let's take a look. Guys, series and parallel combination of cells. Cell means battery. Cell means battery. And what is the symbol of a battery? This is the symbol of a battery. And guys, always remember, let's suppose if I am making a battery over here. If I am making a battery over here, okay, the battery has its own resistance. That is what we call the internal resistance. So I am saying this cell which is present over here, let's suppose its EMF or potential difference is E. The resistance is internal resistance is R. This is the EMF and this is internal resistance. So every cell has the internal resistance. Now guys, if you take a look over here, we say you have got a cell which has a resistance R connected with it. So this is the internal resistance of this cell, its own resistance. You have another battery, its own resistance. You have another battery, its own resistance. Another battery, its own resistance. These are N cells connected in series. If you want to find their net EMF, like EMF of this is E1, like 10 volts, 20 volts, 30 volts. Simply, when the cells are connected in series, their net EMF will be E1 plus E2 plus E3 plus E4 and so on up to En. This will be the net EMF. And guys, since these resistors are also connected in series, if you have the resistors connected in series, their net resistance will be R1 plus R2 plus R3 up to so on, I would say up to Rn. So this is the equivalent resistance. This is the net EMF in this particular case. Next. Let's suppose you have the cells connected in parallel. This is E1, its internal resistance. This is E2, its internal resistance. In case of parallel combination, always remember, net EMF, guys, I can write over here, instead of this will be net EMF. Net EMF is E1 by R1 plus E2 by R2 upon 1 by R1 plus 1 by R2. This is how you can find the net EMF in case of parallel combination of cells. Okay. Then you have, sir, these two resistors are also in parallel. How to find the equivalent resistance of these two resistors? Sir, R equivalent will be R1 R2 upon R1 plus R2. This will be the equivalent resistance in parallel. This will be the equivalent EMF in parallel combination. Okay. Now guys, if you have N cells connected in parallel, but these N cells are, I would say identical. If this is E, this is also E, this is also E, this is also E. Internal resistance R. So these are the similar cells connected in parallel. If that is the case, always remember, net equivalent EMF of all of these will be only E. That is the EMF of one single cell. If identical resistances are connected in series, EMF is potential voltage only. Don't get confused, sir. What is this EMF you are saying? If I am saying this is a battery over here, it's mentioned over here 20 volt. What is this 20 volt? You call it EMF, you call it potential difference. I have no problem. It's one and the same thing. Okay. So we say net voltage or net potential difference in this case will be E only. And equivalent resistance here will be, if these are N connected in parallel, so it will be R divided by N. It will be R divided by N. As simple as that. Now guys, if you have the cells connected in series as well as parallel, this cell, this cell, this cell, this cell, all these cells are connected in series. Okay. Now my dear friends, how many times? We say N times. N cells are connected in series and M times parallel. So N cells in series and M rows in parallel, M times. So here in this particular case, guys, if this is E n times, and then how many rows? M number of rows. All of these are E. Now here E equivalent in this particular case will be n times of E, n times of E. So in case of mixed grouping, this is what we call the mixed grouping, when cells are connected in series as well as in parallel. So here equivalent EMF will be n times of E. And equivalent resistance will be NR divided by M. NR divided by M. Keep this thing in your mind. What is N? N means number of cells over here. N means number of cells in series. Number of cells in series, NR. M means number of rows. In case of mixed grouping, keep this thing in your mind. E equivalent is N times of E. R equivalent is NR divided by M. That's it. Next. Okay. Let's suppose you have got this question over here. Find the current through the ammeter. Ammeter means this is a device which is measuring the current. Guys, always remember. This is 120 volt battery. Resistance of each is 60 volts. Sorry, 60 ohms. Okay. Guys. I am saying this battery is connected to this resistance also, this resistance also, this resistance also, this resistance, this. Let's suppose I'm saying, sir, find the current in this resistance. You'll say, sir, current in this resistance is I is equal to V divided by R. V means how much battery is connected to this. That is 120. 120 divided by R is given as 60. So this will be 2 ampere. So means this current is 2 ampere. Sir, how much is the current to this? This resistance is also directly connected to the battery. So this will be also 2 ampere. This is 2 ampere. In this resistance also 2 ampere. Guys. Simply, in this particular case, I would want you guys to understand one thing. We say this 2 ampere current will complete. See. Here also current will flow. Here also current will flow. So this current will flow through this path because current always flow in a closed loop. This current will flow through this loop. Okay. This current flows something like this. This current flows something like this. Okay. This current flows something like this. Now tell me, what is the amount of current flowing through ammeter? Sir, this 2 ampere, this 2 ampere, this 2 ampere. Total is 6. So current through ammeter is 6 ampere. Current through ammeter is 6 ampere. So basically what I'm trying to say, this battery will send the current of 2 amperes through this resistance. Similarly through this 2 ampere. Similarly through this 2 ampere. Now all of these will flow through the ammeter. So 2 plus 2 plus 2 is 6 ampere in total. Okay. Yes. Let's suppose you have this question. Guys. You are supposed to tell me what is the net EMF or net potential difference. Tell me one thing. This cell. These cells are connected in series. When the cells are connected in series, how to find the net EMF of the cells? E1 plus E2 plus E3 and so on. Tell me guys here. In this particular case, can I say E1 plus E2 plus E3? 6 plus 6 is 12 plus 14. So I would say instead of these 3 cells, I'll make one cell only which is having 14 volts of EMF. Now these 2 resistors are in series. So 3 plus 4 is 7 volts, 7 ohms. Here 6 plus 1 is 7 volts. And 3 plus 2 is 5. 5 plus 3 is 8. So this will be 8 ohms. Now you have to find what is the net EMF. Now these 2 cells are in parallel. Guys, how can you find the net EMF in parallel? E1 by R1 upon E2 by R2. So E1 by R1. So that is 14 by 7 plus we say 7 by 8 upon 1 by R1 plus 1 by R2, 1 by 7 plus 1 by 8. Solve this will be the answer. This is how you can find the net EMF in such cases. How you can find the net EMF in such cases. Now guys, we have got this concept over here. That is what we call the bulb. That is what we call the bulb. Understand this very, very, very carefully. Understand this very, very, very carefully. Bulb is something which we use in our rooms, okay, so that we can basically glow the room, okay. So bulb, let's suppose I'm saying I have got a bulb over here. I'm saying I have got a bulb over here. If you go to the market, you buy the bulb from the market. Over there on the bulb, it would be mentioned, let's suppose 100 watt and 220 volts. If you are buying 100 watt bulb, it would be mentioned 100 watt bulb. If you are buying 50 watt bulb, then it would be 50 watts mentioned and it would be 220 volts over here. 50 watts and 220 volts over here. Guys, understand this very, very, very carefully. What is this 100 and 220? This 100 watt means rated power. This 220 means rated voltage. It means that if we give a supply of 220 volts to this bulb, if we give a supply of 220 volts to this bulb, it will give us the power of 100 watts. So basically, if you have a bulb, you went to the market and you got the bulb and you are using the bulb in your room. You are saying, sir, it is not glowing, even though it is 100 watts. That is because you are not giving the enough supply to the bulb. If you give the proper supply of 220 volts, it will give you exact 100 power. If you give less, so how would you expect that the bulb is going to give you 100 watts? That's what it means. Rated voltage, rated power means if you give this much of voltage to the bulb, it will give you this much of power. Okay, cool. Yes. Now, my dear friends, one more thing I just want you guys to remember over here. What is that? What is that? See. There is a formula. That is, if you want to find the resistance of the bulb, you use this particular formula. Guys, power is equal to V square divided by R. Power is equal to V square divided by R. This is the way by which you can find the power supply in the bulb. You can find the power in the bulb. Sir, what is this power? I will tell you. Guys, let's suppose you have got a bulb over here. Sir, you are giving energy, you are giving current to this bulb. What is this current? This current is energy. With the help of this energy, this bulb glows. It gives you the light energy, brightness. So this energy is itself power. So you are basically supplying the energy to it. Then it gives you the energy, light energy. That light energy is also the power. So you are giving the energy, it is giving you the power. And how do we find this power? How much power is there? V square divided by R. Okay. Now, in this particular case, guys, you know that this is the rated voltage. This is what we call PR. This is what we call VR. Rated voltage, rated power. Guys, if you have the formula, power is V square divided by R. Can you find the resistance of the bulb? Resistance of the bulb will be simply, that is voltage rated square divided by power rated over here. Okay. Because guys, what you are trying to do is that in order to find the resistance of the bulb, if you know the voltage, if you know the power, you can find resistance. Take it over here. Resistance of the bulb is VR square divided by PR square. Now, example. Let's suppose you have a bulb, its power is 50. watts. And voltage rated is 220 volts. Can you find the resistance of the bulb? Resistance of the bulb will be simply, that is VR square divided by PR. So VR square, that is 50 square divided by power rated is VR square, that is 220 square. 220 square divided by, we say, 50. Solve it, you will get the resistance of the bulb. And this resistance is inversely proportional to the power rated, you can see over here. Now guys, one thing I just want to tell you over here. I hope you got it. I hope you got it. What I'm trying to say in this particular case. What I'm trying to say in this particular case. Okay, rated voltage and rated power. Rated voltage and rated power. Rated voltage means how much voltage you are giving. Okay. And rated power means how much power it is giving to you. Okay. Okay. So now guys, let me just tell you one more thing over here. Let me just tell you one more thing over here. What is that? That is, guys, power consumed. Power consumed. Power consumed. Guys, one formula is always there. Power is equal to V square divided by R. Voltage divided by resistance will give you the power. Okay. Now guys, understand this very carefully. Power consumed means voltage supplied, its square divided by resistance of the bulb. I would want you guys to please focus. There are two things. One is power rated. Second is power consumed. Power consumed or power delivered. Guys, see, I'm saying I have got a bulb. The bulb has the capability of giving 100 watts if you give it to the supply of 220 volts. Now, my dear friends, the bulb is not giving you the exact power of 100 watts. It's giving you 70 watts only. That is the power delivered. Why? Because power rated, it will give you 100 watts only if you give 220 volt supply. Let's suppose you are giving it 170 volt supply. That's why you are getting less power. That power will be power consumed. Can I say this power consumed will depend upon voltage supplied. Voltage supplied. If you give more voltage to it, it will give more power. Divided by voltage supplied divided by resistance of the bulb. Guys, tell me, this is power consumed is equal to voltage supplied divided by resistance of the bulb. So I can say power consumed is equal to voltage supplied, its square. So this will be Vs square divided by, what is the formula for the resistance of the bulb? That is VR square divided by PR. So you can say VR square divided by PR, and that I can write over here. So this is power consumed and this is a rated power. Rated power and power consumed is different. It is different. Now guys, one more thing I just want to mention over here. What is that? That is, let's suppose you have over here three bulbs. Okay. And power of this is P1, power of this is P2, power of this is P3. Okay. If you want to find out the net power consumption, sir, net power consumption in series combination. Sir, how much is the power consumed by this, or how much power is given by this? How much power is given by this? Guys, if this is a bulb, if you give it a more supply, it will give you more supply. As simple as that. So here, if you want to find the net power consumption, okay, what will you say? How will you find it, guys? Power of this is P1. So it will be 1 by P1 plus 1 by P2 plus 1 by P3. Okay. So if there are bulbs connected in series, you want to find their net power consumption, 1 by P1 plus 1 by P2 plus 1 by P3. Now guys, one more important thing I want you to remember over here. What is that? Power consumed is inversely proportional to the power rated. Power consumed is inversely proportional to the power rated in series combination. in series combination. What does that mean? That means the one with more power rated, which has got more power rated in series combination, will consume less power, will give less brightness. So if power consumption is less, brightness will be less. Guys, see, 25 watt, 50 watt, 100 watt. Which has got more power rated? 100 watts. So power consumption is equal to power, inversely proportional to the power rated. So my dear friends, here in this particular case, I can say brightness of, or we say power consumption of 25 watt, brightness of 25 watt is greater than brightness of 50 watt is greater than brightness of 100 watt. I want you to remember this directly. What I'm trying to say is that power consumption is inversely proportional to the power rated. Okay, in case of series combination, the one which has got more power rated, okay, will consume less power, will give you less brightness. So it is like if you are buying the 3 bulbs from the market, you are using in your room in series combination, you are expecting 100 watt will give you more brightness, more light. But when you used in the series combination, so it is giving you less power, it is giving you less brightness. And next over here, guys, in case of parallel combination, when it comes to the parallel combination, we say power consumption 1 by P consumed. So here net power consumption will be simply, that is P1 plus P2 plus P3. I hope there is no confusion in this one. Guys, I want you guys to remember it directly. When you have the bulb, there are 2 things: power rated, voltage rated. Power rated means if 100 watt is mentioned, okay, so if you are giving 220 volt supply, it will give you exact 100 watt. If you give less, it will give you less. So that less is the power consumed or power delivered. Now, guys, in this particular case, so when you have the bulbs connected in parallel, net power consumption by each bulb will be P1 plus P2 plus P3 and so on. And here, always remember, power consumption is directly proportional to the power rated. Means the one which has got more power, rated will consume more power. 25, 50, 100. Which one will consume more power? 100. The one which consumes more power delivers more power, gives more power, gives more brightness. So here I can say brightness of 100 is greater than brightness of 50 is greater than brightness of 25. So always remember, in our homes, we connect bulbs in parallel combination, not in series combination. Guys, is this clear? Give me the signal in the chats. Here you have the question. Is this clear? Please tell me in the chats. Is this clear? I would want you guys to tell me in the chats. Is this clear? With the thumbs ups, with the fire emojis. Great. Now take a look. This will clear the confusions out. This will take the confusions out. 6 similar bulbs are connected as shown. Okay. This, identical bulbs. The ratio of power consumption by the bulb when all are glowing. Guys, first, when all are glowing, when all the bulbs are glowing, at that point of time, you have to tell me the power consumption. Guys, these 3 bulbs are in parallel. Could you please tell me what is the equivalent power in parallel combination? P1 plus P2 plus P3. So can I say it is P plus P plus P? So it will be 3P. What is the net power consumption in this case? This is 3P. Now 3P and 3P are in, I'll show it something like this. Now 3P and 3P are in series. This is 3P, this is 3P. What will be net power consumption in series combination. Guys. In series combination, we say 1 upon P equivalent is equal to 1 by P1 plus 1 by P2. Do the cross. 1 upon P equivalent is equal to P2 plus P1 upon P1 P2. Do the reciprocal. P equivalent is equal to P1 P2 upon P1 plus P2. This is now 3P. How do we find the P equivalent? Sir, P equivalent in this particular case is P1 P2, 3P into 3P, that is 9P square divided by 3P plus 3P, P1 plus P2, that is 6P. Okay, this and this will cancel. 3 2s are 3 3s are 9. So this will be 3P divided by 2. This is, let's suppose this is P1 when all the bulbs are glowing. Second, it is saying that when 2 from section A and 1 from section B are glowing. Now tell me, guys. When 2 from section A, 1 from section B. 2 from section A, 1 from section B. P plus P, it will be 2P. And here it is P. Tell me, what is the final power consumption P2? Guys. In this case, P2 will be when 2 from section A. So in that case, you don't have to consider this the third one. When 2 from section A and 1 from section B, 1 from section B are glowing. Guys, 2P, P, they are in series. So we say net power consumption finally will be 2P into P, that is 2P square, divided by 2P plus P, that is 3P. It is basically P1 P2 upon P1 plus P2. So this P and square will cancel. So it will come out to be 2P divided by 3. You have to find the ratio. Find the ratio. So I can write P1 divided by P2 will be, guys, this is 3P divided by 2 upon, we say 2P divided by, we say 3. Now in this particular case, PP will cancel. 3 into 3 is 9, 2 into 2 is 4. So answer is 9 by 4. So ratio is 9:4. Ratio is 9:4. Is this clear? Is this clear? Now we have galvanometer. We have galvanometer. I would want you guys to understand. Guys, focus. Is this clear, guys? Give me the signal in the chats. Guys, what is galvanometer? Simply, galvanometer is a device which is used to detect the current, which is used to measure the small range of currents. Let's suppose you want to find out if the current is flowing in a circuit or not. Let's suppose you have got this circuit. This is a resistance. Okay. This is battery connected to this resistance. Okay. Battery is sending the current over here. You want to find out how much is this current. What will you do is that you will attach a galvanometer here. You will use the galvanometer. So this galvanometer helps us to find the current in the circuit. Okay. Next, it measures the small range of currents and it also detects the current. If large current enters, it will burn. Okay. It will burn the galvanometer. Now, guys, so there is a problem in the galvanometer. It cannot measure the large currents. So what we do instead is that we convert this galvanometer into an ammeter. Guys. Conversion of galvanometer into an ammeter. So galvanometer has a problem that it cannot measure the large range of currents. So we make the ammeter from the galvanometer. We convert this galvanometer into ammeter. Ammeter is that device which measures the large range of currents. Now guys, see. You have a galvanometer over here. You have a galvanometer over here. This is the galvanometer. Okay. Let's suppose you are sending the current I, which you need to measure. Okay, cool. Now, how much is the current that can flow through the galvanometer? That is Ig. This is the maximum current. Sir, if you send current more than Ig, what will happen? It will burn the galvanometer. Okay, yes. Now, Ig will go through the galvanometer. Then, guys, if you do one thing over here, if you connect a resistance, namely shunt, parallel to this galvanometer, this instrument will become the ammeter. So we say when shunt is connected in parallel, it becomes ammeter. When shunt is connected in parallel, it becomes ammeter. And why do we make ammeter? So that we can measure large currents. Okay. Now guys, here Ig, what is the current that can flow through this one? I minus Ig. I minus Ig will go here. And this shunt resistance is S. Now guys, this instrument is called the ammeter. Conversion of galvanometer into ammeter. If somebody asks you, what is the value? Why did you connect the shunt to the galvanometer? Because I have to make it an ammeter so that we can measure large currents. Somebody asks you, what is the value of the shunt? Shunt is Ig into G upon I minus Ig. Ig into G upon I minus Ig, where G is the resistance of the galvanometer. Resistance of the galvanometer. Now, let's take a look. Guys, see. See, I want you guys to understand a galvanometer of resistance 100 ohms. We have got a galvanometer. It has resistance of 100 ohms. Is used to measure 10 ampere current. Guys, this galvanometer can only measure how much Ig is 10 ampere. What if you send current more than 10 ampere? It will burn the galvanometer. As simple as that. Now, find the value of shunt resistance. If we connect a shunt resistance in parallel, find the value of shunt resistance. Okay. If connected in parallel, so that its range becomes 50 ampere, it should be able to measure 50 ampere. What should be the value of this shunt so that it can measure how much? 50 ampere. Because we connect shunt only so that we can measure large currents. How do we find the shunt? S is equal to Ig into G upon I minus Ig. Now tell me, S is equal to, what is the value of Ig? That is 10. What is the value of G? That is 100 upon I minus Ig. That is 50 minus 10. That is 40. This and this will cancel. 100 by 4 means 25. So guys, if you connect a 25 ohm resistor in parallel, it becomes an ammeter and it can measure the current of 50 ampere. Is this clear? Is this clear? Is this clear? Please tell me in the chats. I would want you guys to tell me in the chats. Is this clear? One more question we have. In an ammeter, 0.2% of the main current passes through the galvanometer. 0.2% current of the current passes through the galvanometer. Okay, guys, if I is the current flowing through galvanometer, okay? I is the current flowing through galvanometer. And, sorry, if I is the current incoming current, only 0.2% current passes through the galvanometer. How much current will pass through the shunt? 99.8 I. 0.2% plus 99.8%. Total is 100%. Okay. 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 Now, this is I minus Ig. If the resistance of the galvanometer is G, this resistance is G. Resistance of the ammeter will be, ammeter is whole. Guys, let's find shunt first. Let's find shunt. Could you please tell me, sir, shunt is Ig into G upon I minus Ig. Sir, shunt is Ig into G. What is Ig? 0.2I. 0.2I into G upon I minus Ig. That is 99.8I. 99.8I. Now tell me, in this case, can I say this I and I will cancel? This I can write over here. 0.2 means 2 divided by 10. And this is G. Multiplied by 99.8, I can write 998 divided by 10. Because after point, there is only one digit. This and this will cancel. So 2 ones are 2, 4, 99s are. So value of shunt comes out to be G divided by 499. So we got the value of shunt in this case. But we are supposed to find the resistance of ammeter. Means as a whole. Guys, see. Now, resistance of ammeter is, we have the galvanometer, its resistance is G. We have the shunt. Its resistance is what? That is G by 499. This whole is ammeter. Now tell me, don't you think these two resistors are in parallel? Yes. So resistance of ammeter will be R1, R2 upon R1 plus R2, because that's how we find in parallel. Okay. We say R1, R2 upon R1 plus R2. That's in the parallel combination how we find the resistance. So we say G into G by 499, R1, R2 upon R1 plus R2. G plus G by 499. Now this will be G square by 499 divided by 499G plus G, 500G divided by 499. 500G divided by 499. This. So G by 500. So resistance of ammeter RA is G by 500. Okay. Conversion of galvanometer into a voltmeter. Guys, voltmeter is a device which measures potential difference. Ammeter is a device which measures the current. Okay. Ammeter is a device which measures the current. Ammeter is a device which measures the current, and voltmeter is a device which measures the potential difference. How do we make ammeter from the galvanometer? If this is the galvanometer, you want to make ammeter, you connect the shunt resistance in parallel. Value of shunt is Ig into G upon I minus Ig. But when you have to make a voltmeter from the galvanometer, you connect the shunt resistance in series. This in series. Okay. So my dear friends, I would write connect shunt in series. If you connect the shunt in series, and what should be the value of that shunt? V divided by Ig. V is the voltage of the voltmeter divided by Ig. Ig is the current in the galvanometer minus G. G is the resistance of the galvanometer. Question. Let's suppose a galvanometer of resistance 100 ohms. A galvanometer of resistance 100 ohms. So G is 100. Gives a full scale deflection of 30 milliampere. Means in this galvanometer current can flow, that is 30 milliampere. So if you want to convert this 30 milliampere into ampere, You can say this is 30 into 10 raised power minus 3 ampere. If it is to work as voltmeter, if we have to convert this into a voltmeter, which has the voltage range of 30 volts, which should have a voltage range of 30 volts, the required resistance to be added will be, it says if you have to convert this galvanometer into voltmeter, how much should be the shunt that you need to add in series? Guys, V by Ig minus G. So shunt in this case will be V divided by Ig minus G. Shunt in this case is V, that is 30 divided by Ig is 30 into 10 raised power minus 3 minus G. G is 100. So this and this will cancel. 10 raised power minus 3, if it goes in the numerator, 10 raised power plus 3. So S will be, this is 10 raised power plus 3 means 1000 minus 100. So it is 900 ohms. So it is 900 ohms. It is 900 ohms. Okay. Now guys, meter bridge. Before this meter bridge, let me talk about Wheatstone Bridge. Guys, Wheatstone Bridge. Guys, let's suppose I have a resistance over here. I have a resistance over here. Okay. I have a resistance over here. I have a resistance over here. And I have one more resistance over here. Okay. Let's suppose this is R1, this is R2, or this is R2, this is R3, this is R4, this is R5. Okay. And my dear friends, I want you to understand one thing. I want you to understand one thing. Listen very carefully. Listen very carefully. Guys. If you have a structure something like this, directly remember, we say if this resistance by this resistance, R1 divided by R2, comes out to be equal to R3 divided by R4. If this by this comes out to be equal to R3 by R4, then current is 0 in R5. Then no current flows through R5 directly, please remember directly. If, let's suppose this is 4 ohm, this is also 4. So 4 by 4, this is 4, this is 4. 4 by 4 is equal to 4 by 4. Yes, in that case, we say no current flows through middle resistance. Then we can remove R5. Then we can remove R5. So in that case, we can remove this R5 because no current flows through, and the diagram would look something like this. Diagram would look something like this. This is R1, this is R2, this is R3, this is R4. Now, you can solve this with series parallel. These two are in series, these two are in series, then these two are in parallel. So Wheatstone bridge concept says that, I'll write over here, according to Wheatstone bridge concept, if R1 by R2 is equal to R3 by R4, then no current flows through the middle resistor R5. Or you can do the reverse also. If no current flows through the middle resistor, then R1 by R2 is equal to R3 by R4. As simple as that. That's it. This is the Wheatstone bridge. That's it. Let's come on to this one. Meter bridge. We say meter bridge is an instrument. Meter bridge is an instrument. It is used to measure the It is used to measure the unknown resistance. It is used to measure the unknown resistance. It is based on the concept of Wheatstone Bridge. Guys, see. I'm saying, you have, this is a structure of meter bridge. Why do we say meter bridge? Because we take a wire over here which is 1 meter long. 100 centimeters means 1 meter long. That's why meter bridge. You connect a resistance over here, that is P. This is a known resistance. Known means you know the value of this resistance, 2, 3, 4, something like that. This is unknown resistance. You don't know the value of this resistance. Unknown. Okay. You have to find the value of this Q. So basically you connect this resistance and a wire. And then you take a galvanometer over here. Okay. And then you take a jockey. This jockey is slidable on this wire. Let's suppose I am sliding this jockey on this wire until I get the balance point. Okay. Until I get the balance point. Guys. Balance point is that point when no current flows through the galvanometer. In this case, no current flows through this. Okay. Guys. Let's slide the jockey on the wire. So basically, in case of meter bridge, we have one known resistance, unknown resistance, and the wire and a jockey. We slide this jockey. Let's slide the jockey on the wire, and we got balance point at L1. Let's suppose we got balance point at distance L1, at L1 length. Then how much will be this length? This will be 100 minus L1. This will be 100 minus L1. Okay. Now guys, understand one thing. So I is equal to 0 through galvanometer. So if you are getting balance point here, means at that time no current will flow through this galvanometer. I is 0. Cool? Yes, sir. Now guys, how much is the resistance of this part of the wire? See. How do we find the resistance? Sir, if this length is L, length of the wire is L, resistance is R. Always remember, we can say lambda will be equals to R by L. What is this? It is, sir, if total resistance is R, total length is L. What is the resistance of unit length? Total resistance by total length. This is what we call resistance per unit length. Resistance per unit length. From here, you can get R is equal to lambda into L. Now, guys, tell me one thing. So this is the formula by which you can find the resistance. See, if you want to find the resistance of this part, how will you write? R is equal to lambda into L. So resistance of this part will be lambda into L1. Cool. Resistance of this part will be how much? Resistance of this part will be how much? Lambda into length of this part, that is 100 minus L1. As simple as that. So what I did is that I keep on sliding the jockey until I get the balance point. Once I get the balance point here, means current is 0. Now, resistance of this part, I can use this formula, lambda into L. So lambda into L1. Resistance of this part is lambda into 100 minus L1. Now guys, redraw it. Guys, don't you think it exactly looks like Wheatstone Bridge? It looks like Wheatstone Bridge. Tell me, how does it look like Wheatstone Bridge? One resistance, another resistance, another resistance, another resistance. Let me show. It is like this resistance, this resistance, this resistance, this resistance, and this middle resistance. Guys, this is P, this is Q. This resistance is which one? Lambda into L1. Lambda into L1. this resistance is lambda into 100 minus L1. And this, in this middle branch, you are saying, sir, at balance point, current is 0. Now, what does the Wheatstone Bridge say? If current is 0 in the middle resistor, this divided by this is equal to this by this. Here, P by lambda into L1 is equal to Q by lambda into 100 minus L1. This and this will cancel. You can say P divided by L1 is equal to Q divided by 100 minus L1. This is the equation of meter bridge. This is the equation of meter bridge. Guys, take a look. Okay, done. This one. Okay, let's take a look here. In the question, it says that we are getting the balance point as 20 centimeters. Find the value X. Find unknown resistance X. Guys, simple. You have to find unknown resistance X. It says that balance point it has 20. If balance point is at 20, so current is 0 in the middle resistor. Then can I say this resistance 5 divided by this resistance? Guys, P divided by, what is the formula? P divided by L1 is equal to Q divided by 100 minus L1. Tell me. P divided by L1. So 5 divided by 20 is equal to Q divided by X divided by 100 minus L1, that is 20. So 5 divided by 20 is equal to X divided by 80. This and this will cancel. 5 ones are, 5 fours are. So I can write 5 into 4 is 20. X will be 20 ohm. So this X is 20 ohm. Guys, please tell me in the chats, is this crystal clear to each and every single student? I have covered all the topics of current electricity. Please tell me in the chats. I would want you guys to tell me in the chats, is this crystal and clear to each and every single student? See. When it comes to the Kirchhoff's law, I do not teach Kirchhoff's law in the current electricity because I have shown you the midpoint potential formula. With the help of midpoint potential formula, you can solve every single question, that is for sure. And that we say, in which I told you, select the path. With the help of those two questions, every single problem will be solved without using the laws. And one more thing over here. Guys, just a second. Yeah. If you want to solve more questions from the current electricity portion, let's suppose our electrostatics portion, capacitors portion, here, this is the Game of NEET 2.0 playlist, okay? Go and check that particular topic only. If you want to solve more questions, every single, like this is the current electricity. I have taught current electricity for 11 hours scratch. I have shown a lot of problems. So you can solve the questions from that particular portion, from that particular topic. Okay. So if you want from capacitors, you can go to the capacitors. It is on YouTube only. If you want from magnetism, you can go to the magnetism. Here is the full chapter of magnetism. Okay. For 10 hours. Okay. Now guys, we have the chapter 4 that is called the magnetic effects of current. Notes I'll be sharing in this Telegram channel. t.me/YAWARMANZOOR. Okay. Let's first start with Biot-Savart's law. Let's first start with Biot-Savart's law. Okay. 720, 820, 920. 920. Then 1020. Okay. Cool. We'll finish it. Let's go. Yay. Come on. We have got the Biot-Savart's law. So, ladies and gentlemen, what does this Biot-Savart's law actually say? Let's suppose I am taking a wire over here. This is a wire in which current flows. Okay. And in this wire, how much current is flowing? We say I current is flowing through the wire. Okay. I want you guys to do one thing, do an experiment. Sir, if there is a wire in which current is flowing, it creates the electric field around it. A wire in which current is flowing, a current carrying wire produces the current carrying wire produces the magnetic field around it. Sir, what is magnetic field? Like, my dear friends, if you have got a magnet over here, you say, sir, if I place the coin over here, it will be attracted. Here it will be attracted. Why? Because it creates a magnetic field around it. Similarly, if you have a wire in which current is flowing, it also creates the magnetic field around it. Now, if somebody asks you, take a small element over here, small part of the wire, that is DL, or I call it current carrying element, that is IDL. Because of this small current carrying element, sir, go at R distance, which is at angle theta. How much will be the magnetic field? Guys, magnetic field due to this current carrying element. If a wire is producing magnetic field around it, let's suppose go at R distance. Sir, at R distance, magnetic field because of a small current carrying element, it will be dB is equal to mu naught by 4 pi. This is a constant. Like over there you have epsilon naught. Here you have mu naught. This is called permeability of free space. IDL sine theta. IDL means I is the current, DL is the element. This is current carrying element. Sine theta. Theta is this angle. Angle between IDL and R. Divided by this R square at what distance you are finding. This is the, guys, don't get confused in this. This is the magnetic field due to magnetic field, by the way, we represent with B. This is the magnetic field due to a current carrying element at R distance. If somebody asks you, is this the magnetic field because of the whole wire? No. This is the magnetic field because of a small current carrying element at R distance. This is called the Biot-Savart's law. So Biot-Savart's law helps us to find the magnetic field because of a small current carrying element at R distance. Okay. Now vector form. This was asked in NEET 2020. NEET 2020. Vector form is mu naught by 4 pi IDL cross R. IDL is the small current carrying element cross R divided by R cube. Okay. So this is the vector form of Biot-Savart's law. What is Biot-Savart's law? It helps us to find the magnetic field due to a small current carrying element. Okay. DL is the small part of the wire. I is the current. So IDL as a whole means small current carrying element. Now, direction of magnetic field. Guys, let me show you how do we find the direction. Place your thumb along the direction of current. Let's suppose if this is a wire, direction of current is upward. This is your thumb. Place your thumb along the direction of current. Curl your fingers. If you want to find magnetic field here, curl. It is inwards. So if the magnetic field here is inverse, if it is showing inverse, so make it cross. This cross means inverse. This cross means inverse. Similarly, from this side, place your thumb along direction of current. Curl your fingers. It is coming out, so it is outwards. So magnetic field from this side is outwards. Cool. Next. Now guys, magnetic field due to a finite wire. Previously, I told you magnetic field because of a small current carrying element that was given by Biot-Savart Law. Right now, I am telling you magnetic field because of the whole wire. At what distance? At R distance. At this R distance. Now guys, join this point with one end of the wire. This angle is theta1. Join this point with another end of the wire. This angle is theta2. Now see, because of the whole wire, magnetic field at point P will be mu naught I by 4 pi r sine theta1. I is the current, r is the distance at which you have to find the magnetic field. Sine theta1 plus sine theta2. This is theta1, this is theta2. This is the magnetic field because of the whole wire. Previous one was because of a small current carrying element. How do we find direction? Place your thumb along direction of current. Curl towards, curl your fingers. It is inwards, so magnetic field is inwards. Next. Magnetic field due to an infinite wire. See guys, this wire is not till here, it is till infinity. This wire is till infinity. So at R distance, you are supposed to find the magnetic field because of this. Directly, it will be mu naught I by 2 pi r. Mu naught I by 2 pi r. Okay, because of an infinite wire, mu naught I by 2 pi r. Graph will be rectangular hyperbola, B versus R, because B is inversely proportional to R. Next, magnetic field due to a semi-infinite wire. Semi-infinite means which is going till infinity from one end only. Another end is finite. So because of this, it is mu naught I by 4 pi r. Mu naught by 4 pi. By the way, value of mu naught by 4 pi is 10 raised power minus 7. So if you want to find the value of mu naught, it is 4 pi into 10 raised power minus 7. Like previously, value of K in electrostatics was 9 into 10 raised power 9. Similarly over here. So because of semi-infinite wire, mu naught I by 4 pi r. R is the distance where you have to find. I is the current. Next, find the magnetic field in this case. Guys, see. This angle is theta1 and always remember, this angle theta1 here, theta1 is given as 90 degrees. Theta2 is given as, let's suppose this is given as theta. Because angle between this line and R, that is what we consider as theta1. We have to find the magnetic field here. Use this formula. Use this formula. Mu naught I by 4 pi r sine theta1 plus sine theta2, because this is the general formula. See, I'll write B is equal to mu naught I divided by 4 pi r. Then I say sine of theta1, that is 90, plus sine of theta2, that is theta. Sine 90 is 1, so magnetic field will be mu naught I divided by 4 pi r. Sine 90 is 1 plus sine theta, 1 plus sine theta. This will be the answer. Next. Okay, let's talk about this one. This is a square. Guys, take a look. Take a look. In this particular case, you have a square. If I ask you to tell me what is the magnetic field because of this square over here? This square is made up of 4 wires. 1, 2, 3, 4. So if you find the magnetic field because of one wire and multiply it with 4, you'll get the net magnetic field. I'll write magnetic field due to one wire. I'll write magnetic field due to one wire. Can I say that will be B is equal to, guys, let's suppose I'll take this wire. Guys, join this point and this will be the R distance. Perpendicular distance is R. Join this point with one end of the wire. Join this point with one end of the wire. Join this point with another end of the wire. Can I say this is theta1, this is theta2? This is theta1 and this is theta2. And guys, here I can say theta1 is 45 degrees because this total angle is 90. Theta2 is also 45 degrees. Guys, if the side is L, what is this half of this? So R will be L divided by 2. Now, tell me. R is L by 2. Tell me, guys. Can I say magnetic field will be mu naught I divided by 4 pi R. Then sine of theta1, that is 45. Theta1 is 45. Then I can say sine of theta2, that is also 45. And instead of this R, I can write over here 4 pi instead of R, that is L by 2. Okay, so this will 2 ones are 2 twos are 4. So magnetic field will come out to be mu naught I divided by 2 pi L. 2 pi L. Sine 45. This is 1 by root 2 plus 1 by root 2. Because sine 45 plus sine 45. 1 by root 2 plus 1 by root 2. That is 2 by root 2. So magnetic field here will be mu naught I divided by 2 pi L. And here it is 2 by root 2. It is 2 by root 2. Now guys, 2 and 2 will again cancel. This comes out to be, that is mu naught I divided by root 2 pi into L. Guys, this is the magnetic field because of one wire. But how many wires are over here? 4 wires. So I can say net magnetic field is 4 times magnetic field due to one wire. So that is mu naught I divided by root 2 pi into L. Do one thing. Multiply with root 2. Divide with root 2. Okay. Multiply with root 2 and divide with root 2. Root 2 into root 2 is 2. So this 2 ones are 2 twos are 4. So net magnetic field will come out to be 2 root 2 mu naught I divided by pi into L. This is the net magnetic field. This is the net and direction, guys, let's check the direction. In this particular case, place your thumb along the direction of current, curl your fingers, it is inwards. In this case, place your thumb along direction of current, curl your fingers, it is inwards. Because of this wire, it is also inwards. Because of this wire, place your thumb along direction of current, curl your fingers, it's inwards. So it is inwards. Inwards means cross. Is this clear? Give me the signal in the chats. Is this clear? Guys, quick. If you are not like the session yet, smash the like button as soon as possible. Inward means cross, outward means dot. Okay. Let's talk about, now guys, take a look. Whenever you have a current carrying wire, it produces the magnetic field. Magnetic field on the axis of a circular current carrying loop. Guys, let's suppose you have a circular current carrying loop or wire, whatever you say, in which current is flowing. Whenever current flows in wire, loop, it creates magnetic field. Because of this wire, it will create magnetic field at x distance. This is a loop. At x distance, how much is the magnetic field? Radius of this is given as r. You have to tell me at x distance, what is the magnetic field at this point? Guys, see, you say magnetic field is mu naught I. I is the current flowing in the loop into r square. R is the radius of the loop. 2 into r plus x is the distance at which you have to find the magnetic field. Whole raised power 3 by 2. Okay. Now guys, if I say at center, what is the value of x at center? Everybody knows value of x at center is 0. If you keep on reducing the x, reach the center, x is 0. Put the value of x 0 over here. This expression will become mu naught I by 2r. This is the magnetic field because of this loop at the center, mu naught I by 2r. At x distance, how much it is? Mu naught I into r square upon 2 into r square plus x square whole raised power 3 by 2. At the center, this is the expression, mu naught I by 2r. Very important, this one. Now guys, let's suppose I am taking a segment of the ring. Is this a semicircular ring? Okay. Is this a semicircular ring? No, this is a segment of the ring, some part of the ring. Magnetic field due to a segment of ring. Here in this ring, current I is flowing. Join this end with one end of the point. Join this point with another end of the ring. Angle between these two is theta, and this is r, and this is r. What is the magnetic field because of this ring at this point? Guys, mu naught I is the current here, divided by 2r, r is the radius. Theta divided by 2 pi. Theta is the angle between these two lines, these two radius. This is the magnetic field because of this ring, because of this segment of ring at point P. How do you find the direction? How do you find the direction? Curl your fingers along the direction of current. Thumb is pointing outwards. Thumb is pointing outwards. How do you find the direction? Mu naught I by 2r, theta by 2 pi. This is the expression. Okay. Let's find the direction. Guys, it is not like straight wire. In case of straight wire, how do we find the direction? Place your thumb along direction of current, then curl your fingers. No, here in this case, direction is direction of magnetic field. We say curl your fingers along current. Curl your fingers along current. Curl. Thumb is pointing up outwards. That will give the direction of magnetic field. Thumb gives the direction of B. Thumb gives the direction of magnetic field. Let's take a okay. Let's suppose this is the segment of ring. Current is flowing in this direction. What is the magnetic field direction in this case? Curl your fingers along direction of current. Thumb is pointing inwards, so here it is inwards. Let's talk about this one. Guys, this is a semicircular ring. In case of semicircular ring, theta is 180. So theta is equal to pi. Pi means 180. What will be the magnetic field because of this? Use the general formula. Mu naught I by 2r, theta by 2 pi. So I can say as magnetic field is mu naught I divided by 2r, theta by 2 pi. I can say magnetic field is mu naught I divided by 2r, theta. Theta is pi divided by 2 pi. Because guys, this is the general formula. That's why I'm using. So pi and pi will cancel. 2 into 2 is 4. So B is equal to mu naught I divided by 4R. Guys, what is the direction? Curl your fingers along that right hand. Curl your fingers along direction of current. Thumb is pointing outwards. So it is dot. Dot means outwards. Tell me in case of chord. Tell me in case of chord. Guys, in the chord current I is flowing. And this is the radius R, this is the radius R. Can I say in case of chord theta is equal to pi by 2 means 90? What is the magnetic field? Magnetic field formula is mu naught I divided by 2R, theta by 2 pi. This is the general formula. What is theta? Pi by 2. So B will be equals to mu naught I divided by 2R, pi by 2 pi. This and this will cancel. Okay, pi by 2 pi. 2 into 2 is 4 and 2 is 8. Mu naught I divided by 8R. You guys have to directly remember this. Because of the chord, it is mu naught I by 8R. Because of the semicircle, it is mu naught I by 4R. Because of the segment of ring, mu naught I by 2R, theta by 2 pi. And at the center of a ring, complete ring, mu naught I by 2R. Okay. Tell me. Find the net magnetic field at the center. Find the net magnetic field at the center. Guys. Here, magnetic field will be due to this. Magnetic field will be due to this. Let me show you. Net magnetic field in this case will be. Guys, this is a semicircular ring. Okay. This is a semicircular ring. My dear friends, in this particular case, if you want to find out the magnetic field because of the upper ring and magnetic field because of the lower ring. I see magnetic field because of the semicircular ring. How much is that? Mu naught I by 4R. Now, because of this part of the ring, it will be mu naught I divided by 4R. R is the radius. What is the radius for the bigger part? That is 2R. Plus magnetic field because of this part of the ring. So that will be mu naught I divided by, this is also semicircle, but its radius is only R. So it will be 4R. We direct 4R because its radius is R only. So this will be 4 into 2 is 8R. Mu naught I divided by, this is 8R plus mu naught I divided by 4R. That's it. You can further simplify this also. So this is the concept. And direction. Guys. Because of this, curl your fingers along direction of current, thumb is pointing inwards. Now, because of this, curl your fingers along the direction of current, thumb is pointing inwards. Because of both direction is inwards. Okay. So it is inward. And mu naught I by 4R plus mu naught I by 8R. Okay. Yes. Is that clear? It will be inwards. What about this one? Tell me the answer of this. Yes, 3 by 8 mu naught I by R. That's clear. Previous year students मतलब ये समझ नहीं आया मुझे. Guys, what is the answer of this one? Guys, take a look. This is a semi-infinite wire. This is a semi-infinite wire. This is semicircular ring. First of all, let's check the magnetic field because of a semi-infinite wire. Here it is. Mu naught I by 4r. Because of a semicircular ring. Mu naught I by 4r. Oh, because of that, because of this, it is mu naught I by 4 pi r. 4 pi r. Okay. Now, guys, so this structure is made of 3 parts. This one, this one, this one. Can I say in this particular case, net magnetic field is magnetic field due to first part, second part, third part, plus magnetic field due to second, plus magnetic field due to third. What is the magnetic field due to first part? So, mu naught I divided by 4 pi r, because you are supposed to find at this distance, that is r, 4 pi capital R. Magnetic field because of the semi-infinite. Magnetic field because of the semicircular ring, plus mu naught I divided by 4r, plus magnetic field because of semi-infinite wire. At what distance? This is also r. That is mu naught I divided by 4 pi r. Okay. Now do the simplification from your end. You are done. And what is the direction? Guys. In this wire, current is flowing in this direction. Place your thumb along the direction of current. Curl your fingers. So at this point, magnetic field is inwards. This is inwards. Okay. I'll write over here. This is cross. Sir, what about this? Curl your fingers along direction of current. Thumb is pointing inwards. Because of this also it is inwards. Cross. Because of this, place your thumb along direction of current. Curl your fingers. Thumb is pointing inwards. So this is also cross. Cross. Inward. Okay. Cool. Ampere's law. Let's move on to the Ampere's law. Okay. Guys, when it comes to the Ampere's law, what does Ampere's law actually say? Ampere's circuital law. Guys, it is simply used to find the magnetic field. It's simply used to calculate the magnetic field. It helps us to find the magnetic field. See, guys, let's suppose if you have a wire over here, okay, because of this wire, you want to find the magnetic field at this point. You have two laws. First is Biot-Savart's law. Till now you were using Biot-Savart's law, all of that. Second is Ampere's law. You can use both the laws to find the magnetic field due to a wire, infinitely long wire. Okay. So my dear friends, in this particular case, we just have to see how do we apply the Ampere's law. We can find easily, that's not a problem. But the main point is how do we apply the Ampere's law? That is important. Question comes on that. Okay. See guys, what do we do in this particular case if we have to use the Ampere's law? If you want to find the magnetic field at this point at r distance, see what you are supposed to do. You are supposed to draw an Ampere's loop. This is the first step that you are supposed to do. Draw an Ampere's loop. If you have to find magnetic field because of this wire at this point, draw the Ampere's loop at that point, such that this ring, kind of ring, Amperean loop. Okay. Then take a small element on the loop, that is dl. Then take a small part of the loop, dl. Let's suppose this is the direction of dl. And my dear friends, let's suppose magnetic field because of this wire at this point is B. Cool. What is the first thing? Draw, if you want to find a magnetic field here, draw an Ampere's loop. Okay. Then take a small element dl, small part of the loop dl. Then consider magnetic field at this point B. Done, done, done. Yes. Then see how do we apply. Then Ampere's loop says that do one thing. Take this integration, closed line integral of this magnetic field and this dl, B and dl. Sir, why are we doing it? Because Ampere said. It's his law. He is saying, I'm following, you guys are supposed to follow. So close a line integral of B and dl will be equals to mu naught times of I. Sir, mu naught is permeability of free space. I enclosed. I is that current which is enclosed in the loop. This is the Ampere's law. This is the Ampere's law. So Ampere's law says that if you have a wire, you want to find the magnetic field at this point, draw a loop at this point, then take a small element at this point, then consider magnetic field at this point B, then take the closed line integral of B and dl, make it equal to mu naught into I. That's it. We don't have to find out how does this come from. He said we are following. Now guys, understand one thing very carefully. Understand one thing very carefully. See, if magnetic field and dl, if B and dl are in the same direction, then take current as positive. I'll show you. If magnetic field and dl are in the opposite direction, then take current as negative. Now guys, let me show you over here. Question says, use Ampere's law in the given figure. You have wire 1, wire 2, wire 3. And the loop is given from there only. You have to use the Ampere's law. Guys, say. What does Ampere's law say? Closed line integral B and dl, B dot dl is equal to mu naught times of I enclosed. First question here. Is this the enclosed current? No, because it is not present within the loop. So leave it. I enclosed, so I can write B dl is equal to mu naught times of, when it comes to the enclosed current, it is I1 and I2. Enclosed current will be I1, will be I2. Now guys, take a look exactly over here. I would want you guys to focus. What does it say over here? If magnetic field and dl are in the same direction, then take the current as positive. If magnetic field and dl are in the same direction, then take the current positive. Guys, see, if the current is in the upward direction, because of this current, what is the direction of magnetic field here? Place your thumb along direction of current, curl your fingers. So it will be something like this only. This is magnetic field due to wire 1. I call it B1. Now direction of dl you can clearly see upward. B and dl, B1, magnetic field because of this wire, and dl, both are in the same direction. Okay. B1 and dl, both are in the same direction. Now, my dear friends, if B1 and dl are in the same direction, then this current we are supposed to take as positive. That's what is mentioned over here. If B and dl are in the same direction, then take current as positive. See guys, now because of this wire, current is downwards. Curl your fingers over here. So current magnetic field will be something like this. This is B2. Now B2 and dl are in the opposite direction. Take this current as negative. So it will be plus I1 minus I2. One more I'll show you. Let's suppose this one. Guys, this is I1 cross I2 is dot. This is the direction of dl. So basically these are the two currents. First wire is going inside the board, another wire is coming out of the board. Use Ampere's law. Guys, I can say closed line integral BDL is equal to mu naught times of I enclosed. If there is a current outside, you don't have to consider that. So I enclosed will be I1, I enclosed will be I1 and I2. Now positive negative you have to decide. Guys, because of this current which is inward, curl your fingers, place your thumb along direction of current, curl your fingers. So magnetic field because of this I1, it will be in this direction. So this will be B1. Now B1 and DL are in the opposite direction. So this current will be negative. Similarly, this current is outward. Place your thumb along direction of current. Curl your fingers. So magnetic field because of this current, that will be this. This is B, this is B2. B2 and DL are in the same direction. This current would be positive. I hope this is clear. I hope this is clear. I hope this is clear. Magnetic field due to a hollow cylinder. Magnetic field due to a hollow cylinder. Guys, take a look. Hollow cylinder means in which current is flowing through its surface. In which current is flowing through its surface. This is the current. This is the current. And inside current is zero. No current flows through the cross section. Hollow cylinder, hollow. Like pipe. It is not filled inside. Current is flowing through the surface. Guys, let's suppose a radius of this is given as capital R. You have to find, if you have a cylinder, you have a wire in which current is flowing. You have to find it will create magnetic field. We know a current carrying cylinder, wire, rod creates magnetic field. Because of this cylinder, you guys are supposed to tell me what is the magnetic field outside at R distance, what is the magnetic field on the surface, what is the magnetic field inside at this small r distance. For outside, this r is by the way variable. Guys, when it comes to inside, we say magnetic field inside will be zero. Why? Because inside no current is flowing through the cylinder. If there is no current, there will be no magnetic field. Magnetic field itself is because of the current. Okay, magnetic field inside is zero. Now, my dear friends, when it comes to the outside, so outside is mu naught I divided by 2 pi r. I is the current flowing through the cylinder. At r distance, it will be mu naught I by 2 pi r. And B is inversely proportional to R. You can clearly say. Sir, what about surface? At surface, value of small r is equal to capital R. So that will be mu naught I divided by 2 pi capital R. That's it. If you want to find out, if you want to make the graph will be inside the cylinder, magnetic field is zero. So magnetic field is zero inside. Till the surface. Outside the surface, magnetic field is inversely proportional to R. We said this was asked in NEET 2021. The graph was asked in NEET 2021. Next, magnetic field due to a solid cylinder. Guys, in case of solid cylinder, we say current is flowing through its cross-sectional area also. Because matter is filled inside also. Current is flowing through the cross-sectional area also. You have to find, we say, magnetic field produced inside. You have to find magnetic field produced outside. Guys, inside magnetic field will be, in this case, magnetic field inside will be mu naught I into small r. Mu naught I into small r. Divided by 2 pi capital R square. What is this capital R? Capital R is the radius of the cylinder. 2 pi into capital R square. 2 pi into capital. This is inside. And inside R is less than capital R. Okay. Guys, when it comes to outside R is greater than capital R. So outside will be mu naught I divided by 2 pi into small r. So whatever is the value of outside for hollow, same is for solid, because at very far distance, we consider both hollow and solid as an infinite wire only, as a wire only. So whatever is the expression for infinite wire, same is for hollow, same is for solid. If you make the graph over here, guys, you can see when it comes to inside, B inside, it is directly proportional to small r. When it comes to the B outside, it is inversely proportional to small r. Don't you think that graph will be, sir, inside B is proportional to small r. This is inside the cylinder. And outside it is inversely proportional to small. Is this clear? Okay. If I apply the hollow cylinder, Ampere's law on this hollow cylinder, solid cylinder, it will take a lot of time. That's the derivation that we do over here. तभी मैंने बोला इसको directly use करो, इसको directly याद रखो. This is important. This was asked in NEET 2020. This graph. Previous one was asked in NEET 2020, 2021. Magnetic force. Magnetic force. Guys, take a look. Let's talk about the magnetic force. Guys, let's understand this magnetic force concept. If a charge is placed in a magnetic field and is given some velocity v, we say magnetic force acts on it. I have told you previously in electrostatics, if you have an electric field over here, okay, in this electric field, if you place a charge, we say force acts on it, and that force is equal to Q times of E. This is the force acting on the charge which is placed in the external magnetic field, external electric field. Guys, even if you place this charge at rest or in motion, electrostatic force will still act. But, let's suppose you have a magnetic field over here. Sir, you have a magnetic field over here. In which direction magnetic field is present? Inward direction. And in this magnetic field, you are placing a charge. This is the charge which you are placing in this magnetic field. Okay. And my dear friends, you are giving some velocity to this charge. You are giving some velocity to this charge. Whenever a charge is placed in the external magnetic field and some velocity is given to it, there is a force called magnetic force which acts on it. That magnetic force is equal to, that is Q into V cross B. Q into V cross B. Okay. Or you can say F is equal to QVB sine theta, where theta is the angle between. Theta is the angle between, where theta is the angle between V and B, where theta is the angle between velocity and magnetic field, where theta is the angle between velocity and magnetic field. Okay. Yes. Now guys, understand one thing. It is mentioned over here, V cross B. Let's suppose if you have magnetic field in the forward direction and charge is moving also in the same direction, velocity and magnetic field are parallel. We say theta in this case is 0. If theta is 0, we say magnetic force will come out to be QVB sine of 0. Sine 0 is 0. Magnetic force in this case will be 0. Okay. Magnetic force acting on this charge in that case will be 0. Now guys, let's suppose if magnetic field is backward, charge is moving in the forward direction. In this case, theta is 180 degrees. Here, I can say QVB sine 180. So force in this case will be 0. So force in this case will be 0 because sine 180 is also 0. Now guys, let's suppose if a charge enters the magnetic field perpendicular to the magnetic field. Magnetic field is inwards, okay? Magnetic field is inwards. Okay. So we say magnetic field is inwards. In this particular case, I would want you guys to understand, if magnetic field is inwards, you apply velocity is forward. Velocity is forward, magnetic field is inward. How much is the angle? 90. If case 3 is when theta is equal to 90 between velocity and magnetic field. Between velocity and magnetic field. In that particular case, guys, the charge performs the circular motion. Whenever charge enters the magnetic field at an angle of 90 degrees, when it makes 90 degrees with the magnetic field, in that particular case, the charge performs the circular motion. In that case, charge performs the circular motion. And the radius of that circle will be mv into qb. And if somebody asks you what is the radius of that circle, that is mv into qb. M is the mass of charge, v is the velocity of charge, q is the charge itself, b is the magnetic field. And guys, time period. Time period means in how much time it will complete one cycle, one complete revolution. This time period will be 2 pi m divided by qb. M is the mass of charge, q is the charge, b is the magnetic field. Okay. And guys, this is the radius in terms of mass and velocity, or we can say in terms of momentum. But radius in terms of kinetic energy. So it will be under root of 2mke divided by qb. This is the radius of that circular path in which charge moves in terms of kinetic energy, 2mkb. And if somebody asks you what is the value of velocity, velocity is simply qbr divided by m. This is the velocity of that charge. Radius, charge, magnetic field, mass of the charge. Is this clear? Is this clear, guys? Is this clear? I would want you guys to tell me in the chats, is this clear? Tell me. Tell me. Now, let's talk about force on a wire placed in the uniform magnetic field. Force on a wire. एक कहावना की है यार बात हो कुछ उठ गो खत्म Wasim. Now guys, take a look. Force on a wire placed in a uniform magnetic field B. Force on a wire placed in a uniform magnetic field B. Okay. Guys, I would want you guys to understand one thing in this particular case. The previous topic that we discussed over here, what was that? That is the force on a charge placed in the external magnetic field B. Okay. Placed on the force on a charge, magnetic force on a charge placed in the external magnetic field B. We had the magnetic field over here in which we placed this charge. So the force which this charge was experiencing, that is Q into V cross B. Now, my dear friends, I would want you guys to understand over here. Let's suppose if you have a wire which is placed, this is a current carrying wire, which is placed in the external magnetic field B, like this is the magnetic field which is inward over here. Inward magnetic field, inward magnetic field. In this inward magnetic field, you have placed a wire over here. You have placed a wire over here. And in this wire, current I is flowing. Current I is flowing. Guys, here length of the wire is basically L. Length of the wire is basically L. So whenever a wire is placed in the external magnetic field, we say it also experiences the force. It also experiences the force. If a rod is placed in the external magnetic field B, force on it will be. So it will experience the force of, I can say F is equal to I into L cross B. So you can say over here it is ILB sine of theta. ILB sine of theta. So where theta is the angle between L and B. Simply, if you have a magnetic field from now onwards, you place a current carrying wire. So this current carrying wire also experiences the force. And that force is equal to ILB sine of theta. Or you can say I into L cross B. I into L cross B. Now, my dear friends, one thing I just want to tell you over here. Let's suppose if you ever get a question something like this, you have got a wire, okay, this is a semicircular wire. In the semicircular wire, let's suppose current I is flowing, radius of this is R. It is placed in the external magnetic field. It is placed in the external magnetic field. Now, if somebody wants you to find out the force on this wire, what is the formula? You say, sir, force on the wire will be ILB and then we have sine of theta. Guys, whenever you have a structure something like this, which is not straight, always take its effective length. Always take its effective length. Join one end of the rod with another end of the rod. We say this effective length in that case will be, guys, if the radius is R, this is R plus R, this will be exactly 2R. This will be exactly 2R. So here I can say this force will be I into L effective length B and theta. Theta is the angle between length and magnetic field. Length is this in x-axis. Magnetic field in Z, angle is 90. So sine 90 is 1. So I can say F is equal to I, B and L effective, we can say 2R. So this will be the magnetic field in that particular case. In that particular case. Okay. Okay. This is the force in that particular case. So basically there is important concept in this case is force per unit length that I'll show you after some time. So we have got this, we have got this. Okay. Now, one more thing I forgot to tell you. That is that. What is that? That is the direction of magnetic force. Guys, if you place a charge in the external magnetic field, you have to find what is the direction of force. Guys. Always remember, the direction of force will be, what is the direction of velocity? Sir, forward. Place your fingers along the direction of velocity, curl towards magnetic field. Magnetic field is inwards. So, place your fingers along direction of velocity, curl towards magnetic field. Thumb is pointing in the upward direction. So, this will be the direction of magnetic force. This will be the direction of magnetic. Okay, place your fingers along velocity. Then curl towards magnetic field. Thumb gives the direction. Thumb gives the direction of magnetic force. Thumb gives the direction of magnetic force. Thumb gives the direction of magnetic force. Okay. Now, my dear friends, in this case, if you want to find the direction of magnetic force, guys, place your fingers along the direction of current, curl towards magnetic field. thumb is pointing towards left, that will be the direction of magnetic force. As simple as that. This is the direction of magnetic force here. That is the direction of magnetic force there. I hope this is also clear. I hope this is also clear. Let's suppose if I make a question here, something like this. Let's suppose this is the charge. Okay. This is the velocity of the charge. Okay. And this is the magnetic field. This is the magnetic field. Find the direction of force. Find the direction of force. Find the direction of force. Guys, what we are supposed to do is V cross B. Place your fingers along the direction of velocity. Okay. Curl towards magnetic field. Velocity is inward. Magnetic field is upward. Velocity is inward. Magnetic field is upward. So we say V cross B. It is towards right. So force on this will be towards right. V cross B. V cross B. Okay. Velocity is inwards. Okay. Magnetic field is upward. So V cross B. Force is towards the right. Velocity. Charge is moving inwards. Cross means inwards. Charge is moving inwards. Magnetic field is upwards. Place your fingers along direction of velocity. Curl towards magnetic field. Thumb is pointing towards right. If my dear friends, if the charge was negative, guys, this is also important. This is also important. If let's suppose same question I am saying, this is the velocity. Okay. The charge is negative. Magnetic field is upward. What is the direction of magnetic force? You will have to apply the same logic, but the direction of magnetic force you consider opposite. Towards left. Okay. Sure. Okay. If the charge is positive, force will be towards right. But if this is negative, then consider force opposite. One more concept you have over here, that is force per unit length. Force on I2 wire due to I1 wire. Okay, let's take a look over here, guys. See, let's suppose you have a wire over here. This is infinitely long. At R distance, you place another wire which has the length L. This is at R distance. Now, my dear friends, in this particular case, here current in this wire is I1. Here current in this wire is I2. Guys, understand very carefully. Because of this wire, magnetic field will be present at this point. Why? Because a current carrying wire produces magnetic field. Place your thumb along direction of current. Curl here, it will be inwards. Because of I1, magnetic field is present over here. Now, in this magnetic field, this I2 wire is present. Whenever you place a wire in the magnetic field, it experiences force. Okay. Now, guys, what is the... See. Force on this wire is because of this magnetic field. And this magnetic field is due to this wire. In nutshell, you say, whenever you have two wires parallel to each other, they apply force on each other. If the current is flowing in the same direction, then force will be attractive. These two will attract each other. Okay. Guys, force between the two parallel wires. F is equal to mu naught I1 I2. I1 is the current in this wire. I2 is the current in this wire. Divided by 2 pi R. R is the distance between the two wires. R is the distance between the two wires. Multiplied by L. Where L is the length of this wire. So whenever you have the two parallel wires in which current is flowing, they apply force on each other. If the current is flowing in the same direction, then the force will be attractive. They attract each other. This is the force. If somebody asks you force per unit length, force on the unit length, that will be total force divided by total length. This, guys, this is the force on this wire because of this wire. This is the force because of this wire on this wire, on the whole wire. But if you want to find the force on the unit length, that will be force divided by length. Okay, so take this expression of force divided length, LL will cancel. So this is what we call mu naught I1 I2 divided by 2 pi r. So what I'm trying to say is that, guys, what I'm trying to say is that if you have two wires, let's suppose this is I1, in this case I1 is flowing. If you have another wire, this is I2. In this case, this is R. These two wires apply force on each other. Okay. Now, if somebody asks you how much is the force per unit length, force per unit length, that will be how much force they apply on their unit length. That is mu naught I1 I2 divided by 2 pi r. And question was asked on the same concept. An arrangement of three parallel wires. Let me make the new diagram. An arrangement of three parallel wires. So this is B wire. This is over here A wire. This is over here C wire. Such that the distance between this and this is D. Distance between this and this is D. And my dear friends, this wire is coming out of the plane. This wire is coming out of the plane. So wire is coming out. Here current in this wire is I. This is I. This is I. Magnitude of force per unit length on the middle wire B is. You have to tell me what is the net force on this middle wire. Force per unit length. I told you, if you have two wires, force between the two parallel wires, force per unit length, mu naught I1 I2 by 2 pi r. Don't you think that in this case also, if you have to find the force on this wire, so this wire, C wire, will attract it towards itself, let's suppose with a force F. This will also attract it towards itself with a force F. These two forces are at an angle of 90. We say this will be the resultant, that is root 2F. That is the net force, root 2F. Now guys, what is this root 2F? F is the force between these two parallel wires. And force what? Force per unit length. So net force in this case will be root 2. And this F is mu naught I into I, that is I square, divided by 2 pi. And distance between these two is D. Is anyone matching? No. Do one thing. Guys, it is root 2 into F. F is the mu naught I1 I2 divided by 2 pi r. So I can say multiply with root 2 divided with root 2. Root 2 into root 2 becomes 2. That will cancel with this 2. So now it will become mu naught I square divided by root 2 pi into D. Is this clear, guys? Is this clear, guys? Option 1. Is this clear? Tell me. We'll take the break at 9, huh? Now guys, take a look. Magnetic field due to a solenoid. Magnetic field due to a solenoid. Guys, what is a solenoid? Let's suppose you have a wire over here, something like this. If you make n number of turns in this wire, so it will become something like this, solenoid. This is called the solenoid. It is a circular wire of many turns, of n turns. A circular wire of n number of turns is called the solenoid. Okay. And if in this solenoid, I say current I is flowing, so this will also create the magnetic field. Guys. Now, in this case, we say magnetic field is present inside the solenoid. We consider a solenoid is a coil of n number of turns. Similarly, in outside the magnetic field, outside the solenoid, we consider zero. Magnetic field outside the solenoid is zero. And magnetic field inside the solenoid. Guys, I would want you guys to remember, magnetic field inside the solenoid, that is mu naught n into I. What is this n? N is the number of turns per unit length. Okay. And we also say this number of turns per unit length means total number of turns divided by total length. So can I say this solenoid will be equals to, that is mu naught capital N I divided by L. This is the magnetic field inside the solenoid. And guys, when it comes to at the ends of the solenoid, magnetic field at the ends of the solenoid, it is mu naught Ni divided by 2. Half of the magnetic field, whatever is inside. Okay. Magnetic field at the ends is 1 by 2 of magnetic field inside. Okay. And this magnetic field is along the axis of the solenoid. It is along the axis of the solenoid. Something like this. Something like this. Okay. I'll write magnetic field of the solenoid is along the axis of the solenoid. Along the axis of the solenoid. Okay. How do you find this, guys? Let's suppose current is flowing something like this. Curl your fingers along direction of current. Thumb is pointing something like this. So that's why we say along the axis of the solenoid. Along the axis of the solenoid. At the ends, it will be mu naught Ni, 1 by 2 mu naught Ni. This will be the magnetic field at the center. Similarly, if somebody wants you to make the graph between magnetic field versus distance, guys, and one more thing, this magnetic field which is inside the solenoid, be in mu naught N into I, it is constant. Okay. We say at the ends, magnetic field is mu naught Ni by 2. Guys, at the center of the solenoid, it is constant. And then this is the magnetic field at the ends. This is the ends of the solenoid. At the ends of the solenoid, it will decrease. It will become half. It will become half. Okay, this is the end. This is the magnetic field at the end of the solenoid. End of the solenoid. It becomes half. Here it is B. Here it is B by 2. You can see it is B by 2. It is B by 2. I hope this is clear. I hope this is clear. Now you have the toroid. Okay, first let's talk about this question. This was the question, by the way, this was the question asked previously. A long solenoid of 50 centimeter length having 100 turns carry a current of 2.5 ampere. The magnetic field at the center of the solenoid is, guys, magnetic field of the solenoid is mu naught N into I. Okay, in this case, also we say another formula is mu naught capital N I divided by L. Now B is equal to, we have a solenoid which has the length of 50 centimeters. So L is 50 centimeters. Mu naught. What is the value of mu naught? It is 4 pi into 10 raised power minus 7. So it is 4 pi into 10 raised power minus 7. N, Length of the, sorry, number of turns of the solenoid, that is 100. Okay. I, current in the solenoid, that is 2.5 ampere, divided by length of the solenoid. Length of the solenoid is 50. So 50 into 10 raised power minus 2. Solve it and you will get the answer. This was the question asked in NEET 2020 on the solenoid. Now guys, one more thing. That is toroid. That is toroid. Magnetic field due to a toroid. A toroid can be considered as a ring-shaped solenoid. Guys, this is a solenoid. If I want you guys to basically make it of the circular shape, it will become toroid. So it is, a toroid can be a ring-shaped solenoid, a ring-shaped solenoid, a tube-like structure. Okay, a tube-like structure. It is a tube-like structure. Okay, circular tube-like structure. A ring-shaped solenoid. Now guys, hence it is like an endless solenoid. It does not have the end. It is CC guys, CC. It is something like this. This is the ring-shaped solenoid. Okay. Now in this particular case, if you want to find the magnetic field, what will you say? Sir, whatever is the magnetic field in case of a solenoid, because from the solenoid only we made the toroid. Same will be for the toroid. But the difference is, guys, mu naught Ni. We say mu naught Ni divided by L. In case of the toroid, L means length of the solenoid or this circumference of the toroid. L is the circumference of the toroid. So you can say this toroid will be mu naught Ni divided by, that is 2 pi into R, where R is this radius. Now, here also we define two types of radius. Inner radius, this is R1. Outer radius, this is R2. Guys. If R is more, magnetic field will be less. So you can say in this particular case, maximum magnetic field in case of the solenoid will be mu naught Ni divided by 2 pi into R1. Because here, if radius is less, magnetic field is more. Okay. And my dear friends, when it comes to the minimum magnetic field is mu naught Ni divided by 2 pi R2. So if you take the bigger radius, magnetic field at the outer portion, because it's a inner radius, outer radius. So this will be the minimum magnetic field, this is the maximum magnetic field. Keep this thing in your mind. Okay. I hope this is crystal and clear. Magnetic dipole. Just a second. Guys, give me a minute. I'll come in a minute. I'll get some water. Give me a minute. Guys, we'll take the break at 9. Don't worry, okay? 9. We'll finish this chapter. That's why I'm saying. Okay, because then we have only EMI and AC. Now, guys, take a look. Magnetic dipole. Guys, previously we studied electric dipole. What was electric dipole? You have a negative charge minus Q. You have a positive charge plus Q. Separated by the distance D. This was the electric dipole. But when it comes to the magnetic dipole, in case of magnetic dipole, have you ever heard about or have you ever seen the bar magnet? You go to the market, you buy the bar magnet over there, from there. So that bar magnet would be something like this. It will have south pole, it will have north pole. This south pole has a pole strength that is called minus M. This north pole has a pole strength that is called plus M. This bar magnet is considered to be the magnetic dipole. Like here, minus M plus M. Here it is minus Q plus Q. Magnitude of charge, magnitude of positive charge. This is pole strength of south pole, pole strength of north pole. So the bar magnet in magnetism is considered to be the magnetic dipole. Like you have here dipole moment P, that is Q into D, charge multiplied by distance. Similarly, you have here magnetic dipole moment, that is capital M. And this magnetic dipole moment is pole strength M multiplied by distance between the poles, that is L. This is called magnetic dipole moment. And this magnetic dipole moment is from minus M to plus M. It is from south pole to north pole. Okay. Magnetic monopoles does not exist. Like guys, if you take the charge from here, you place it over here. Individually, minus Q can exist. It can exist. Plus Q can exist. But if you break the magnet, this north pole cannot live separately. It cannot live separately. It cannot exist. What happens if you break it? I'll tell you. Guys, let's suppose if you break the magnet, let's suppose if you have a magnet, this is, I can say south pole, this is north pole. If you break it over here, this, you say, sir, now this south pole will live separately. No, it will generate another north pole from this side. Similarly, this side, if this is north, it will generate another south pole from this side. So it is not possible that magnetic monopoles can exist. Okay, magnetic monopoles does not exist. Now guys, we need to understand that is magnetic field due to a dipole on its axis. Previously, if you remember, we had electric dipole minus Q plus Q. Because of this electric dipole, we talked about the electric field at arbitrary point, axial point, equatorial point. Similarly, here also, you have a magnetic dipole. Okay. And I would mention over here, it is plus M and minus M. This is plus M and this is minus M over here. And this would be plus M. This is minus M. This is plus M because this is a magnetic dipole. So dipole moment is from minus M to plus M. You have to find the magnetic field because of this dipole at an angle theta at r distance, or we say x distance. Let's suppose this is small r, at small r distance. This is called the general point. Guys, if you remember, electric field was, remember, because of the electric dipole, Kp divided by x cube under root of 3 cos square theta plus 1. Compare. Here you have K. It is Coulomb's constant. Here you have constant in magnetism, mu naught by 4 pi. Here you have dipole moment P. Here you have magnetic dipole moment M. Here you have X. Here you have the same X or R, one and the same thing, small r. Cube. Under root of 1 plus 3 cos square theta, 1 plus 3 cos square theta. It is one and the same thing. Guys, on the axis, magnetic field was over there. Twice Kp divided by x cube. Here it is 2 times of this. Here it is K. Here it is mu naught by 4 pi. M by x cube, P by x cube. Similarly, here it is mu naught by 4 pi m by x cube. So because of the magnetic dipole, magnetic field at arbitrary point is this, at axial point is this, at this equatorial point is this. It is exactly like the magnetic field of electric dipole. Now, do you remember we studied if you have the electric field over here. In this electric field, if you place a dipole, minus q plus q, it experiences the torque. Torque is Pe sine theta. Guys, here, if you have magnetic field, in this magnetic field, if you place a magnetic dipole, minus m plus m, we say here also torque will act like electrostatics. And here torque will be m cross b. Over there it was p cross e. Here it is mb sine theta. Pe sine theta was over there. Okay, m is the magnetic dipole moment, b is the magnetic field. Theta is the angle between m and b. Theta is the angle between m and b. Next, you have case 1. Guys, theta is equal to 0 degrees. If theta is 0, magnetic field and magnetic dipole moment, if you are placing the dipole something like this, angle between these two is 0. What will be torque? mb sine theta, sine 0, torque will be 0. If theta is 180, this is magnetic field. Okay, and this magnetic dipole moment is in the backward direction. So magnetic field and dipole moment are opposite to each other. Theta is 180. In this case also, torque will be mb sine of 180. Sine 180 is 0. If theta is 90 degrees, torque will be mb sine 90, something like this. Torque will be mb sine 90, something like this. So this is the maximum torque. We have already discussed this previously. So that's why I'm moving a bit fast over here. Okay. Guys, potential energy of the magnetic dipole, don't you think it is exactly similar? Like previously, I told you if an electric dipole is placed in an electric field, if you rotate it by an angle of theta, we say it will gain potential energy. Potential energy will be stored. That was minus P dot E, or that was minus Pe cos theta, minus Pe cos theta. Similarly, in this particular case, if you have the magnetic field, in this magnetic field, you are placing this magnetic dipole. At an angle theta. Okay. If you are rotating this magnetic dipole by theta, potential energy will be stored in the dipole. And here potential energy in the dipole is minus m dot b. Sir, where does this potential energy come from? Sir, if you rotate the dipole, you have to do the external work done. That external work done is stored in the form of potential energy. And my dear friends, that potential energy will be minus m dot b, or minus mb cos theta. Minus mb cos theta. Okay. Okay. Also, here also we say work done is equal to change in potential energy. Work done is equal to U final minus U initial. I guess we have discussed this in detail previously. No need to go in much detail over here also. Tell me, is this clear? Give me the signal in the chats, guys. Tell me, guys. Now, guys, an important topic here, that is current carrying loop as a magnetic dipole. current carrying loop as a magnetic dipole. See guys, we say a current carrying loop behaves like a magnetic dipole. Current carrying loop means if you have a wire over here, if you have a circular wire over here, circular current carrying loop, in which current I is flowing. I is the current flowing in the loop. Radius of this loop is R, capital R. I say this loop behaves like a magnetic dipole. This loop behaves like a magnetic dipole. Why, sir? Why, sir? Because this current carrying loop produces the magnetic field at the center. Okay? Like if you take a magnetic dipole or a bar magnet over here, this bar magnet also creates magnetic field. Similarly, this will also create magnetic field. So we say in this particular case, this current carrying loop is creating the magnetic field. How do we find the direction of that magnetic field? Curl your fingers along direction of current, thumb is pointing inwards. So I can say, sir, this kind of will make a bar magnet in this particular case and which has a dipole moment, something like this, like in the direction of magnetic field. So from now onwards, guys, if you have a circular current carrying loop, this circular current carrying loop in which current is flowing, it produces the magnetic field at center. So this magnetic field I am showing with the help of bar magnet or magnetic dipole. That is this magnetic dipole. And my dear friends, when it comes to this magnetic dipole, it will have the dipole moment. And that dipole moment is equal to current multiplied by area. Current flowing in the loop, area of the loop, I into A. And direction of magnetic field is along the area vector. Guys, if this is the board, what is the direction of area? Like this, perpendicular to the surface or inwards. So direction of magnetic moment will be also in the same direction. Okay. So from now onwards, you'll remember that a current carrying loop behaves like a magnetic dipole and its dipole moment is current into area. Simply. Next, orbital magnetic moment of an electron. Guys. If I am saying there is an electron which is revolving around the nucleus, charge on an electron is E, its velocity is V, and let's suppose the radius over here is R. Could you please tell me, if an electron moves in a circle, means electron is in motion, charge is moving in orbit, current is being produced. If charge moves in this direction, current is produced in the opposite direction. Now, if current is produced, so it behaves like a current carrying loop. It's like a current is flowing in the loop, behaves like a current carrying loop. It behaves like a current carrying loop. So it will be considered as a magnetic dipole. It will be considered as a magnetic dipole and it will have magnetic moment and will have magnetic moment. Guys, its magnetic moment will be simply EVR divided by 2. E is the charge on an electron, V is the velocity of electron, R is the radius divided by 2. So EVR divided by 2. So from now onwards, you'll remember that if an electron revolves around the nucleus, it also behaves like a magnetic dipole and its dipole moment is EVR divided by 2. One more thing. Angular momentum of a revolving electron If an electron is revolving around the nucleus, its angular momentum is L is equal to mvr. Okay. Now guys, I can say, divide this m with this L. Divide this m with this L. So I can say m divided by L. That is EVR divided by 2. And this, instead of L, I can write MVR. Okay. So this VR and VR cancel. M divided by L is E by 2M. This is called gyromagnetic ratio. Okay, so basically this is the relation between magnetic moment of an electron and angular momentum. If you know the angular momentum, you can find the magnetic moment of that revolving electron. Keep this thing in your mind. Is this clear? Please give me the signal in the chats. Everyone means everyone. Now guys, let's talk about moving coil galvanometer. Let's talk about moving coil galvanometer. Guys, simply I would want you guys to remember one thing. In case of the moving coil galvanometer, we say it is a device which is used to measure the current. It is a device which is used to measure the current. It is a device which is used to measure the current. Okay. Now, my dear friends, listen to me very carefully. Listen to me very carefully. This is how galvanometer exactly looks like. It has this magnetic north pole, south pole. This is a magnet over here. Okay. And my dear friends, this magnetic north and south creates the magnetic field over here. And in this magnet, you have got this coil. This is the coil. This is the coil. Coil placed, rectangular shaped coil of n turns placed in this magnetic field. And there is this spring, this helical spring. It is connected to this coil. And there is this jockey. There is this jockey which is connected to the helical spring. Jockey is connected to the helical spring. And then there is this meter over here. This is how the galvanometer exactly looks like. This is how the galvanometer exactly looks like. Guys. I would want you guys to understand one thing over here. There is only one equation of galvanometer. That is C theta is equal to NIAB. Let me just tell you. In this particular case, let's suppose you want to measure the current with the help of a galvanometer. How does it work actually? You basically send the current in this coil, okay? This coil is placed in the external magnetic field. And in this coil, current is flowing. Tell me guys, very carefully. If you have a coil in which current is flowing, okay? So don't you think it behaves like a magnetic dipole? Yes, sir. Recently you studied. Now, this coil is placed in external magnetic field, means this magnetic dipole is placed in the external magnetic field. Whenever magnetic dipole is placed in the external magnetic field, torque is created. Yes, torque is created. And that torque will be this one. This is the torque created in the coil. What did I say? You have a coil in which current is flowing. You want to measure that current. Okay, you want to measure that current. Now guys, if I am saying this current carrying coil behaves like a magnetic dipole, means it's a dipole. And this dipole is placed in this external magnetic field. When dipole is placed in the external magnetic field, torque will act on that. We studied torque acts on a current on a magnetic dipole. Okay. Like here. I'll show you. If you think I'm lying, let me prove it to you. Torque on a magnetic dipole placed in the external magnetic field. So we say torque will act over here, and that torque is equal to NIAB. Where does this come from? Don't go there. This is the torque. This is the torque in the coil. Torque in the coil. Guys, see, N is the number of turns in the coil. Okay. I is the current in the coil. You can see over here. N is the number of turns in the coil. I is the current. Okay. A is the area. B is the magnetic field. Magnetic field. Now guys, if you send more current in the coil, don't you think that, sir, if current is more, this torque in the coil will be more? Now, if torque in the coil is more, so basically the coil will rotate more, and this jockey is connected to this coil, so this jockey will rotate more. It will show you more reading. Let's suppose if you are sending 10 ampere of current, so it will create less torque, so it will rotate less. If you are sending more current, torque will be more. If torque is more, it will rotate more, it will show you more reading. As simple as that. Now guys, let's suppose you have rotated this because of that torque. Now, while you remove the current, the jockey should get back to the original position. It's not like the speedometer of the car. You are increasing the speed of the car 100 meters per second. Now, if you remove your foot from the accelerator, now that jockey should come back to zero. So for that, we use this helical spring. This helical spring creates the restoring torque. This is restoring torque. Restoring torque. Why do we use this restoring torque? To bring the jockey back. Okay. So this restoring torque is C into theta. C is the helical spring constant. Okay. And theta is how much it has deviated. And this restoring torque should be equal to this torque. Because of this torque, the jockey moves forward, shows the reading. Because of this torque, the jockey comes back to the original position. I hope this is clear. And this is equal to, this is called the equation of galvanometer. This is called the equation of galvanometer. Now guys, listen to me very carefully. There are two things over here in case of galvanometer. First is galvanometer sensitivity. It means how much sensitive the galvanometer is. Guys, if I say a person is very much sensitive, means if you play with that person, if you make a fun of that person, you'll become angry because he is very sensitive. You can't make fun of that person. You can't play with that person. Okay. So means sensitivity of that person is very large. Similarly, even if you send very small currents in the galvanometer, it will measure those currents. Means sensitivity of a galvanometer is very large. Even if very small currents flow, needle will still deflect and shows the reading. That is called the current sensitivity. And guys, this current sensitivity of a galvanometer, it is theta divided by I. Okay, SI is theta by I. That is NAB divided by C. Guys, tell me, if theta is more, guys, if deflection is more, sensitivity is more. If current is more, sensitivity is less. Means if you send more current, it will show less sensitivity. Even if you send less current, it should have the more sensitivity. I hope this is clear. NAB divided by C. So this is the sensitivity. So here, theta divided by this, take this I over here, take this over here. From the equation of the galvanometer, if you want to find the current sensitivity, you say theta divided by this I and take this here. This is NAB divided by C. This is called the current sensitivity. And similarly, voltage sensitivity. Guys, voltage sensitivity of the galvanometer is this. NAB divided by CR, where R is the resistance of the galvanometer. NAB divided by C. Guys. Because galvanometer also measures the voltage. See? NAB divided by C is the current sensitivity. Now, instead of this NAB divided by C, you write SV is equal to SI divided by R. This is the relation between voltage sensitivity and current sensitivity. Okay. So similarly, galvanometer is a device which measures the current. There are two things which are in the galvanometer. One is, sir, that torque due to which jockey deflects and shows the reading. That is this torque, NIAB. Then you have to bring the jockey back to the original position. So for that, we use helical spring. This helical spring creates restoring torque. It creates restoring torque. And this is called the equation of galvanometer. That's it. Then we say current sensitivity. Current sensitivity means how much sensitive galvanometer is. If it is more sensitive, means it can measure very small currents also. So current sensitivity is NAB divided by C. Okay. Current sensitivity is directly proportional number of turns, area, magnetic field. It is inversely proportional to C. Similarly, voltage sensitivity, NAB divided by CR. This is SI divided by R. This. Now you have a question. Current sensitivity of a moving coil galvanometer is 5 division. So SI is given as 5 diV per milliampere. So this is the current. Per milliampere means 10 raised power minus 3 ampere. So take this over here, 10 raised power minus 3 in the numerator will become 5000 division per ampere. And voltage sensitivity of a galvanometer is 20 division per volt. The resistance of the galvanometer is, you saw SV is equal to SI by R. Can I say SV is equal to SI by R? So R is equal to SI by SV. SI is 5000. SV is 20. So that is 250. 250 ohms. 250 ohms. Guys, let's take a break till 9:30. Break till 9:30 p.m. This is the dinner break, and after this we'll finish rest of the 2 chapters. Because then afterwards we have, after this we have, okay, this. And guys, one more thing. Wait, don't go. I have taught you all the topics, even maximum topics, 80% of the magnetism and matter we are done. Magnetic effects of currents already we are done. 80% magnetism and matter also. Now guys, take a look. Now you have some topics, not some topics, one topic, 1 or 2 topics. That is the properties of magnetic materials, okay? Like you say, different magnetic materials, okay? That is, in that case, you have paramagnetic, diamagnetic material, ferromagnetic material. So that is one topic that I would request you, that is completely theoretical, that I would request you to go to the Game of NEET 2.0 magnetism chapter, and from here that portion is starting. And what is the time? From 8 hours and 30 minutes. That portion is starting. I would want you guys to watch that topic from here. Magnetic susceptibility, okay, that is also defined over there. Magnetic susceptibility, ferromagnetic material, diamagnetic material, that comes under one topic only. So that I want you guys to go on to this Game of NEET 2.0 magnetism from 8 hours and 30 minutes onwards. Okay, I would want you guys to watch it. Okay, it will be clear. It is completely theoretical. And my dear friends, let's take a break. Okay. Okay, guys, so we are back, ladies and gentlemen, back to basics. So, I told you there is one topic, one or two topics from the magnetism and matter. Rest 80% magnetism and matter, we are done with that. Now you have types of magnetic materials. I request you to go to the game of NEET 2.0 magnetism marathon. Okay, from this time. So we say 8:30, 8 hour and 30 onwards, you watch this session. So you would be able to understand, because that is completely theoretical. It is just a wastage of time. And it is not possible for you guys to understand in a short duration when it comes to that topic. That's why I request you to go and watch this. And when it comes to this playlist, I have shown you already. It is this one. It is here. This magnetism and matter. Complete magnetism. Now, guys, let's move on to the next chapter. That is chapter 5, Electromagnetic Induction, EMI. Okay. Take a look over here. This is actually chapter 6. Take a look over here. The very first thing that we need to understand in this chapter is magnetic flux. Okay. What does magnetic flux actually mean? We say it is the number of field lines. It is the number of magnetic field lines passing through a surface, passing through the surface perpendicularly. Okay. It is denoted by phi b. Guys, previously we talked about the electric flux. Electric flux is if you have a surface, how many number of electric field lines are crossing the surface? That is electric flux. What is magnetic flux? How many number of magnetic field lines are crossing the surface? That is magnetic flux. Okay. Like, let's suppose, guys, you have placed a magnet over here. We say from the magnet, these are the field lines coming out. Through this surface, how many field lines are crossing? 2. So we say flux here is 2. This is another surface. We say in this surface, how many lines are crossing through the surface? 3. So we say flux is 3. How many number of magnetic field lines cross any surface will be the magnetic flux. Sir, where does these magnetic field lines come from? It may be because of a magnet or because of some machine, something like that. Now guys, take a look exactly over here. The question is, you have got a current carrying loop. And current I is flowing in this current carrying loop. Okay. You are supposed to tell me, what is the flux through this square loop? Guys, we say when it comes to the magnetic flux, always remember, if you want to find this magnetic flux, it is magnetic field into area. Okay, this magnetic flux is B dot A, or you say this magnetic flux is BA cos of theta. Sir, more is the magnetic field, more will be flux. More is the area, more will be flux. So we say this is B dot A, simply BA cos theta. Now guys, if you want to find this magnetic flux over here, what will you say? You'll say, sir, I'll use the formula. That is magnetic flux is equal to magnetic field into area, BA cos theta. Guys, see, you have to find the flux through this area, flux through this square loop. So area of this square loop you can find out, that is L square. Magnetic field, guys, current is flowing through this wire. Because of this loop, magnetic field at the center will be, guys, we say magnetic field due to the loop at center. We have studied that this magnetic field is mu naught I divided by 2R. Magnetic field because of a circular loop at center is mu naught I by 2R. And area of this loop is L square. Now tell me, what is going to be the value of magnetic flux? So we say magnetic flux is magnetic field into area, that is mu naught I divided by 2R, and then we say L square. Simply. And condition here is L is much less than R, because you can consider this as a point, because this magnetic field is exactly at the center. Now guys, see. If you check the direction of this magnetic field, curl your fingers along direction of current, this magnetic field will be outwards. And my dear friends, this outward magnetic field is crossing this loop. That's why we say flux is creating in this loop. Flux is created in this loop. Next, reverse of this. Guys, what is the magnetic flux through this circular loop? If the current in the square loop is flowing I. Guys, again, I say magnetic flux is magnetic field into area. Here, this square loop will create the magnetic field, okay? And that will be inward over here. Can I say magnetic field due to square loop? Guys, if you remember, that is 2 root 2. That is 2 root 2 mu naught I divided by pi into L. This was the magnetic field due to a square loop at its center. Now this magnetic field, because of this square loop, is crossing the circular loop. So we can say this magnetic flux will be, that is this 2 root 2 mu naught I divided by pi into L. L is the length of the side, multiplied by area of this loop, that is pi r square. This pi and pi will cancel, so phi will be 2 root 2 mu naught I into r square divided by L. So this is the flux through the circular loop, and this flux is due to the magnetic field created by this square loop. And by the way guys, this flux is a scalar quantity. Let's talk about the Lenz law. Guys, understand one thing very carefully. Lenz law is very important. I would want you guys to give me 100% attention over here. Let's suppose we have got a ring over here. This is the ring. Okay. And you take a magnet close to this ring. You have a ring, you are taking a magnet. Now bring this magnet close to the ring. We know that because of this magnet, magnetic field lines are coming out. These are the magnetic field lines which are coming out of the magnet. Now guys, if you take this magnet close to the ring, don't you think that more number of field lines will cross through the ring? Yes. As you take the magnet away from the ring, less number of field lines will cross through the ring, because some will leave something like this. We say, guys, when you bring the magnet close to the ring, understand very carefully, magnetic field through the ring will increase, will change. Due to the change in the magnetic field through the ring, through the coil, current starts flowing through the coil, in the coil. When you bring the magnet close to the coil, you observe that current starts flowing in the coil. Due to the change in magnetic field through the coil, current starts flowing in the coil. This is the experiment we are doing. Now the question is, guys, when you take this magnet away from the coil, then also you saw that current is flowing. So basically, while you take it close, while you take it away, current is flowing. While you place it at any particular position, current is not flowing. So whenever magnetic field changes, then only current flows. Now the question is, what should be the direction of that current? See, if the magnetic field through the coil is increasing, if you are taking this magnet close to the coil, means magnetic field is increasing. Then current, I means current, it is not me, it is current. I will oppose the magnetic field, primary magnetic field. The current in the coil will be in such a way, it will oppose the primary magnetic field. Clear? Sir, I couldn't understand this. I know. Wait for some time. If the magnetic field through the coil is decreasing, means if you are taking it away from the coil, then current will support the magnetic field. This current will be in such a way so that it will support the primary magnetic field. Now, what does this support and oppose mean? Guys, see, what does support mean? I will tell you. See, guys, let's suppose if this is the direction of magnetic field, primary magnetic field. I am saying you have to oppose the primary magnetic field. How will you oppose? Apply the secondary magnetic field in opposite direction, that is oppose. If I say this is the primary magnetic field, okay, and it is decreasing, you have to support it. How will you support it? Apply the secondary magnetic field in the same direction. That is the support. Now, what does Lenz's law say? If the primary magnetic field, if this magnetic field through the coil is increasing, the current will be in such a way so that it will oppose it. If the primary magnetic field is decreasing, the current will oppose it. Support it. Guys, see, find the direction of the current. This is the primary magnetic field. Understand this. With the question, you will understand. I say primary magnetic field in this case is increasing. Guys, this is the primary magnetic field. And this primary magnetic field is outwards. Okay, this primary magnetic field is outwards. Understand, with this question you will understand. Now, what should be the direction? Guys, this is the coil, Whenever you place a coil in the changing magnetic field, or if just a second, guys. Now, in this particular case, what I'm trying to say is that if you place a coil in the changing magnetic field, current will flow in the coil. Yes. Now, primary magnetic field is increasing and is outwards. Guys, the secondary magnetic field, sir, where does the secondary magnetic field come? Sir, we say current will flow in this one, okay? Because whenever the magnetic field changes, current will flow. For an instance, let's suppose current in this case is something like this. This is the direction of current, clockwise. Okay. Now, guys, I'm saying current in this case is clockwise. Now, if current is clockwise, don't you think that because of this current, there will be one more magnetic field in this that will be developed? Because, guys, if there is a coil, this coil creates the magnetic field. This current creates the magnetic field. Yes, a current in the coil creates the magnetic field. What is the direction of the magnetic field? Place your thumb along direction of, curl your fingers along direction of current. Thumb is giving you a direction of magnetic field. Cross, this is the magnetic field inwards. This is the magnetic field because of the current. If this is a coil, direction of the current is this. Magnetic field will be outwards. This will be magnetic field outward dot. Now here, in this particular case, guys, if current in this coil is flowing, this current is because of changing magnetic field. Now, for an instance, I say direction of the current is clockwise. Now, due to this current, clockwise current, due to this current, another magnetic field will be developed. That is called secondary magnetic field. What is the direction of the secondary magnetic field? Curl your fingers along direction of current. Thumb is pointing inwards. So this will be inwards. This will be inwards. Okay, this will be inwards. So I can say in this particular case, B secondary will be inwards. See, because of primary magnetic field, primary current is being produced. Because of this current, secondary magnetic field is being produced. Now, secondary magnetic field, guys, current should be in such a way so that it should oppose the increasing magnetic field and it should support the decreasing magnetic field. Now tell me, primary magnetic field is increasing and is outwards. Here, are you supposed to support the primary magnetic field or oppose? We say in this particular case, we have to oppose the primary magnetic field. Why? Because it is increasing. So if primary is outward, secondary should be inward. That is only possible if the direction of the current is clockwise. So direction here is clockwise. That's what I was trying to say. If the primary magnetic field through the coil is increasing, current will oppose the primary magnetic field. How will the current oppose? It will create secondary magnetic field that will actually oppose. One more question. One more question. One more question. See guys, let's suppose question is something like this. You have got this guys, this is primary magnetic field, B primary, and it is, let's suppose, decreasing. Tell me, this is the loop over here. What should be the direction of the current in the loop? If a loop is placed in a changing magnetic field, decreasing magnetic field, current will be produced. Tell me guys. Tell me guys. B primary here is decreasing. And what is the direction? Direction is inwards. If the primary magnetic field is decreasing, we know secondary magnetic field should be also inwards. Why? Because we have to support the decreasing magnetic field. Then my dear friends, see. This is only possible if the direction of the current is clockwise. So if the direction of the current is clockwise, we say then only, curl your fingers along direction of current, thumb is pointing inwards. We say secondary magnetic field will be also inwards. Let's suppose I ask you this one. Guys. Let's suppose this one. This is the magnetic field. This is the magnetic field. In this magnetic field, you are placing a coil. This magnetic field is increasing. Now tell me, here, primary magnetic field is increasing and direction is inwards. Direction is inwards. Secondary magnetic field should be what? Secondary magnetic field in this case should be outwards. Why? Because primary is increasing. You have to oppose the increasing magnetic field outwards. That is only possible, guys. You are saying secondary magnetic field should be outwards. That is only possible if the direction of current is anti-clockwise. So that is only possible if direction of current is AC. This is how we find the direction of current with the help of Lenz's law. Let's talk about this question. Guys, give me the signal in the chat if this is crystalline clear. Give me the signal in the chat is this crystalline clear with the fire emojis. Tell me guys. My throat is actually paining now. Smash the like button if you have not liked the session yet. Take a look. Find the direction of the induced current. Guys, you have a wire over here and in this wire current is increasing. This is the primary current. Guys, see. Because of this current, magnetic field will be produced over here. How? Place your thumb along the direction of current. Curl your fingers. So because of this current, magnetic field will be created over here. Magnetic field will be created over here. And this is primary magnetic field. If this current is increasing, because of this current, this magnetic field will be increasing. Now guys, if primary magnetic field is increasing and is outward, don't you think that this loop is placed in the increasing magnetic field? The secondary magnetic field should be inwards, because Lenz's law says that you are supposed to oppose the primary magnetic field. Okay. You are supposed to oppose the increasing magnetic field. This is only possible if the direction of the current is clockwise. So if the direction of the current is clockwise. So if the direction of the current is clockwise, I can say it will create the secondary magnetic field which is inwards. As simple as that. As simple as that. What about this one, guys? You have got a wire over here, and in this wire, primary current is increasing. There is a loop from the upper side and there is a loop from the lower side. You guys are supposed to tell me what is the direction of the current in the loop A and direction of the current in the loop B. See, because of this current, place your thumb along direction of current. Curl your fingers here. Because of this current, magnetic field here will be inwards. This is primary magnetic field. So I can say in loop A, can I say B primary is inwards? This magnetic field is inwards, and since the current is increasing, so because of this current, so magnetic field will be also increasing. So I would say this is increasing. It is increasing. Now, my dear friends, if primary magnetic field is increasing, Lenz's law says that oppose the increasing magnetic field. I can say B secondary in this case should be outwards. So it should create, here you must create the secondary magnetic field in outward direction, B secondary. That is only possible if the direction of the current is anti-clockwise. Something like this, then only magnetic field will be outwards. So this current is ACW. So current is anti-clockwise. Similarly here, guys, in this case, you have this wire. So in this wire, current is flowing in the downward direction. Curl your fingers along direction of current. So from this side, magnetic field is outwards. This is primary magnetic field. So I can say in loop B, we can say primary magnetic field is outwards. Primary magnetic field is outwards and is increasing. Why? Because this current is increasing. If the current is increasing, I am saying secondary magnetic field here will be. Guys, you have to oppose the increasing magnetic field. So secondary magnetic field should be inwards. So this should be inwards. It is only possible if the direction of current is clockwise. It is only possible if the direction of current in this wire is clockwise. Is this clear? Is this clear? Guys, here you have this magnetic field is constant. B is constant. You guys are supposed to tell me, find the induced current at point A, B, C, D. The loop is moving with a constant velocity inside this magnetic field. Guys, I can say when the loop is outside of the magnetic field, current in that case is 0. Because when no current flows through the loop, when no magnetic field crosses the loop, in that case, no current will be produced. Current is only produced when the magnetic field through the loop changes. Here, magnetic field through this loop does not change actually. No magnetic field is crossing. Guys, I would say at point B. At point B. We say loop is going in the magnetic field. So as it goes in, more number of field lines will cross through the loop. So I can say B primary is increasing. Why? Because it is going in. If B primary is increasing and is inwards, because direction of magnetic field is inwards. No doubt magnetic field is constant, but as much as the loop is going in, we say more number of field lines are crossing. If more number of field lines are crossing, we can say magnetic field is increasing. So if primary magnetic field is increasing, we can say secondary magnetic field should be opposite to this. That should be outwards. So that is only possible if secondary magnetic field should be outwards. That is only possible if the direction of current is anti-clockwise. If the direction of current is anti-clockwise. Okay. What about C? What about C? Guys, when it comes to the at point C, guys, at point C, we say number of field lines is constant. We say magnetic field is constant through the loop. So when magnetic field is constant, current will be 0 because it's placed in the number of field lines inside this is constant. When it comes to the point D, at point D, we say loop is coming out. The more loop comes out, less field lines through the loop will decrease. So magnetic field primary is decreasing. And is inwards. If it is decreasing and inwards, can I say secondary magnetic field should be outwards? Sorry, that should be inwards only. Why? Because we have to support the decreasing magnetic field. That is only possible if the direction of current is clockwise. That is only possible if the direction of current is clockwise. Okay, and here the direction of current is anti-clockwise. Now, there is an important question which has the probability to ask in your NEET exam. That is, find the direction of the current in the coil with respect to the observer. Guys, if observer changes, we say direction of current changes. I'll show you why. See, let's suppose this is the coil. Okay, this is the coil. In this particular case, let's suppose the current is flowing in this direction, anti-clockwise. Current is flowing in the anti-clockwise direction. So with respect to me, it is anti-clockwise. Keep the coil as it is. So current is going towards the board, anti-clockwise. I'll move to this side. Now, with respect to me, it is clockwise. It is clockwise. If I go to that side, it becomes anti-clockwise. If I come to this side, it will become clockwise. So if observer changes his position, we say direction of current changes. Now, guys, I want you to understand over here one thing. What is that? That is, listen carefully, I'll make you understand. Let's suppose if you have a coil over here, this is a coil, okay? Always remember this concept. And there is a magnet which is going away from the coil. And there is a magnet which is going away from the coil. This is the magnet which is going away from the coil. Okay, let's suppose this is South Pole, this is North Pole. Guys, this coil will never want that magnetic field through it should increase. That's why Lenz's law told us, if the magnetic field through the coil is increasing, the coil will try to oppose the primary magnetic field. If the magnetic field through the coil is decreasing, the coil will try to support that magnetic field. The coil never wants that magnetic field through it should either increase or decrease. It wants the magnetic field to be constant. Now, if the magnet goes away, we say this coil, so if the magnet goes away, so magnetic field through the coil is decreasing. So what this coil will do, this coil will create an imaginary bar magnet. It will create an imaginary magnetic field. Okay, it will create an inside magnet, secondary magnetic field. That imaginary bar magnet will attract this magnet. Because this magnet is going away, it is decreasing the magnetic field through the coil. But this coil does not want the magnetic field should decrease. So it will create a bar magnet which should have north pole from this side, south pole from this side. Then only north will attract south. Okay. Another case. If you have this coil, and you have a magnet over here, okay, let's suppose this is south, this is north. This magnet is going towards the coil. In this case, magnetic field through the coil is increasing. Coil never wants the magnetic field through it should increase. It will again create the imaginary bar magnet. But right now, the south will be from this side, north will be from this side. Why? Because now this bar magnet will repel this increasing magnetic field. So always remember, if a magnet goes away from the coil, this will create an imaginary bar magnet which will try to attract the primary magnet. If the magnet is going towards the coil, this will again create an imaginary bar magnet which will try to repel the coil. That's why we say coil repels the increasing magnetic field, coil supports the decreasing magnetic field. Now come over here. Guys. Direction of current in coil 1, direction of current in coil 2. If I say this is the coil over here, this magnet is going away from the coil. Can I say this will create an imaginary bar magnet? Yes. And north pole will be here, south pole will be here. Then only north will attract south. Now this magnet is going towards the coil. This coil will create an imaginary bar magnet. And this north will be here, south will be here. Now this north will repel this north. Okay. Now see, guys, remember this statement. If the observer sees north pole in the coil, here is the observer. Observer is directly facing the north pole. Observer is directly facing the, south pole. North pole is from another side. If the observer sees south pole in the coil, then current is clockwise. Okay. If the observer sees north pole in the coil, like this observer is directly facing north pole of this coil, south pole is from another side, then current will be anti-clockwise. Now tell me, in this coil, observer is facing south, so current in the coil is clockwise. So I can say this is the direction of current. Current is clockwise. Observer is facing north pole. Current in this coil is anti-clockwise. Very important concept. Let me give you one more question on this. Let's suppose you have a coil. Observer is here. This is the magnet, north, this is south. It is going towards this velocity v. Now tell me, What is the direction of the coil here in this? What is the direction of the current in this coil and in this coil? Guys, this magnet is moving towards this coil, so it will create an imaginary bar magnet. Here it will be north, here it will be south. No, it will repel this. This magnet is going away from the coil. It will also create an imaginary bar magnet. This will be north, this will be south. This north will attract this south. Now tell me, this observer in this case is facing what? I would say north pole. So in this case, current is anti-clockwise. This observer in this case is facing north, so current in this case is anti-clockwise. Okay, let's suppose if I change the position, if I place the observer over here, what will be the direction in that case? Guys, this observer is facing north, current will be anti-clockwise. This observer is right now facing south, current in this case is clockwise. Okay. Again, if I change the position of the observer, let's suppose I'll place over here. Now tell me, this observer is facing south, current in this case is clockwise. This observer is facing north, current in this case is anti-clockwise. I hope now it becomes easy. It has become easy for you to figure out how to solve this type of question, these types of questions. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Guys, it states that the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through the coil. Okay. Guys, let me make you understand this Faraday's law. Guys. Let's suppose I have got a coil. Again, I'll take the same example. Let's suppose I have got a coil over here. And in this coil, you have a magnet in this case. You have a magnet. Okay. Guys, if you are taking this magnet close to the coil, away from the coil. You are bringing this magnet close to the coil, away from the coil. You know that because of that current will be produced. And how to find the direction of that current? Because of the Lenz's law, we have understood that properly. Now see, this is the current, this is the current. Magnetic field is changing through the coil, current is being produced. Now, if there is a current in the coil, guys, understand very carefully. If there is a current in the coil, we say there will be potential difference because Ohm's law says that potential difference is directly proportional to current. If there is potential difference, there is current. If there is current, there is potential difference. Okay? Because current always flow when there is potential difference. We say here current is produced due to change in flux. Flux or field, one and the same thing. So, potential difference slash EMF will be there. What I'm trying to say, guys, when field through the coil changes, okay, due to this flux changes, okay, due to this flux changes, when flux through the coil changes, we say current is produced. Okay. My dear friends, when there is current, we say there will be EMF. EMF is present. Because it is not possible current can flow without EMF, without potential difference. So because we say current always flow from higher potential to lower potential. Now in this particular case, can I say due to the change in flux, EMF will be produced? So, due to the change in flux, EMF is produced. Yes. So can I write it something like this? Sir, change in flux will be d phi by dt. Because of this change in flux, EMF will be produced, and put the negative sign. Negative sign is because of the Lenz's law. Because Lenz say that if the primary magnetic field is increasing, the current will be in such a way so that it will oppose it. So we say d phi due to the change in flux or change in magnetic field, current is produced or EMF is produced, one and the same thing. EMF is equal to d phi by dt. This is Faraday's law. That's mentioned in this line. The magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through the circuit. More flux through the circuit changes, more EMF will be produced. Now here, this is the instantaneous EMF, d phi by dt. If we talk about the average, that will be delta phi by delta t. Guys, what is instantaneous? Let's suppose this is a coil. You are changing the magnetic field through the coil from 9 a.m. to 1 p.m. I'm saying, sir, from 9 a.m. to 1 p.m., what was the EMF which was induced? What was the EMF which was produced? That is average EMF. Total. Sir, when the time was exactly at 11:30, at that time, what was the EMF which was produced? That is instantaneous EMF. EMF induced at any particular instant. And this is the EMF induced in a given time interval. Delta phi by delta t. Now guys, tell me one thing. If there is EMF, there will be current. Guys, we say current is I is equal to V by R, potential difference EMF divided by resistance. Now can I say average EMF will be EMF divided by R? And instead of EMF, I'll write delta phi by delta t, because EMF is actually equal to delta phi by delta t. Okay. So you will write over here delta phi by delta t and divide by R. So this is the average EMF. When it comes to the instantaneous EMF, you will say this is d phi by dt and this is R d phi by dt. Okay. Yes. And guys, we say this is the current, that is, it is EMF by R, and here you will write d phi by dt and this R. And then, my dear friends, if current is flowing in a coil, guys, let's suppose you are saying you have a coil over here. In this coil, you are saying current is produced. Okay. Sir, how current is produced? Because of changing magnetic field. And if current is produced, what is current? Current itself is the flow of charge. When charge flows, current will flow. When charge flows, current will flow. So we say if current flows, in a coil, charge is flowing. That is, charge is flowing. And charge flow will be delta Q is equal to delta phi divided by R. Because how do you find it? I'll tell you. Guys, see. Since you are saying current is equal to EMF divided by R, V by R, you are saying current is equal to EMF is, sir, delta phi divided by delta T and this R. Now this current is charge upon time, delta Q by delta T. I have told you many times, charge upon time is equal to, this is delta phi divided by R delta T. Delta T will cancel. So total charge flown is equal to delta phi divided by R. Is this clear? Is this clear? Tell me, guys. How much time? It is 10:16. We'll get done at 11. We'll get done at 11. Now, guys, let's move on to this one. You have radius of a circular loop placed in a perpendicular uniform magnetic field is increasing at a rate of R0 meter per second. Guys, you have got a loop, circular loop. This circular loop is placed in a uniform magnetic field. It is placed in a constant magnetic field. But the radius of this loop is increasing. We say R is increasing. Okay. If radius is increasing means loop is getting bigger. So we say more field lines will cross through the loop. So means magnetic field through the loop will increase. And it is saying that radius is increasing at the rate of dr by dt. This is given as R0 meter per second. Every second, how much is the increase in radius R0 meter? Let's suppose if I say R0 is 1 meter. Every second 1 meter radius is increasing. Every second it will become bigger, 1 meter, 1 meter, 1 meter. Okay. If at any instant radius of the loop is R, then EMF induced in the loop will be. Guys, we have to find EMF. To find EMF. Can I say, sir, this EMF will be simply, that is minus d phi by dt? Yes. Guys, when it comes to the EMF, I can say it is minus d by dt of phi. Phi is magnetic field into area. Phi is magnetic field into area. Phi is magnetic field into area. Since magnetic field is constant over here, take this magnetic field out. So this is minus B. Then we say area. Area of the loop I can write pi r square. So I can write d by dt of pi r square. Even I can take pi also out. Minus B pi dr square divided by dt. Guys, I cannot differentiate r with respect to t. So multiply with dr and divide with dr. So interchange this and this. If you interchange this and this, you will be writing over here. This EMF is equal to minus B pi dr square by dr square divided by dr multiplied by dr by dt. Okay. Guys, tell me one thing. Dr square by dr. So differentiation of r square with respect to r. So this will be minus B pi and this is 2r. Dr by dt. Guys, dr by dt is, I guess, given as R0 meter per second. So you can put over here. So this will be R0. So this will be the EMF induced at that instant. This will be the EMF induced. Okay, let's talk about this one. A conducting ring of radius r is placed perpendicularly inside a time-varying magnetic field. You have got a ring which has a radius r. It is placed in a changing magnetic field, time-varying magnetic field. B is equal to B naught plus alpha t. Okay. Where B naught and alpha are positive constants, EMF induced in the ring will be. You have to find the EMF induced. Guys, I can say EMF is simply minus d phi by dt. I can say this EMF is equal, when flux changes, EMF is produced. And here magnetic field is changing, so EMF is produced. So you can say minus d by dt of magnetic field into area. So you can say EMF in this case will be minus, we can say d by dt of magnetic field here will be B naught plus alpha t area in this case will be pi into r square. Pi into r square. So EMF in this case will be is equal to, that is minus, guys, what can you take constant? This area is constant, okay, take this out. So it will be minus pi r square. Now differentiation of this, guys, differentiation of B naught is constant, differentiation of constant is 0. Then you say differentiation of alpha t. For differentiation of alpha t, you can directly write over here alpha. Sorry, yes, alpha, because we are differentiating with respect to t. So it will be alpha. So it will be simply minus alpha pi r square. Minus alpha pi r square. Motional EMF. Motional electromotive force. EMF. Guys, give me the signal in the chats. Is this clear? Everyone means everyone. Tell me, is it clear? Take a look, guys. Motional electromotive force. See, let's suppose you have a magnetic field over here, inward magnetic field, and in this inward magnetic field, you are placing a rod, and in this magnetic field, you are placing a rod. Okay, guys, directly remember, I would want you guys, this rod is moving with a velocity v. This rod is moving with a velocity v, and length of the rod is L. Length of the rod is L. We say whenever a rod moves in a magnetic field, okay, and EMF is induced. EMF means potential difference induced in the rod, and EMF is induced in the rod, called motional EMF. Why? Because it is due to the motion of the rod. That's why we call motional EMF. And that motional EMF is equal to BVL. B is the magnetic field, V is the velocity, L is the length of the rod. That motional EMF is equal to BVL. Okay. Now, my dear friends, you have three cases. Direct remember, if, now, see. I'll write over here. If any of the three, that is B, V, and L, if any of the three, B, V, and L, are parallel, if any of the three, B, V, and L, are parallel to each other, then EMF is 0. Okay? My dear friends, if any of the three are parallel to each other, like if I say velocity and magnetic field are parallel, in that case EMF will be 0. Like here. Guys, the rod is moving in the forward direction, velocity and magnetic field are parallel, in that case EMF is 0. Okay? Here in this case, magnetic field is inward, rod is placed something like this and moving forward. So velocity is in x-axis, length is also in x. In this case also EMF is 0. Next, case 3. When velocity and length are parallel. Guys, this is velocity in the upward direction. Okay. When magnetic field and length are parallel. See, this is the magnetic field. Rod is placed something like this. These two are parallel. Here also EMF is 0. So I can say all the three must be mutually perpendicular. All the three must be mutually perpendicular. Please don't ask me why, because it will take a lot of time to make you understand why EMF will come out to be 0 if the two are parallel. Like here in this case, magnetic field is inward in the z-axis. Velocity is forward in the x-axis. Length is in the y-axis. All the three are mutually perpendicular. That's why we say it is BLV. If any of the two are parallel to each other, then EMF in that case will be 0. The first question you have on this topic, that is this. That is this. You have a wire over here, and then you have a rod. This rod is moving with a velocity v. Okay, and this rod is placed at a distance a from this wire. You are supposed to tell me length of the rod is L. What is the EMF induced this? Guys. You see here in this case, if we talk about, because of this wire, magnetic field here will be, place your thumb along direction of current, curl your fingers, magnetic field is inwards. So magnetic field produced because of the current carrying wire is inwards. In that inward magnetic field, this rod is moving with a velocity v, but velocity and length are parallel. We say here v and L are parallel. So in this case, EMF will be equal to 0. In this case, EMF will be equal to 0. Next, when velocity and length are parallel. Okay, here velocity and length are parallel. Rod is moving in the upward direction. Length in this case same, so EMF in this particular case is 0. In the previous one, what was parallel? Velocity and length. Here, no, here velocity and length is not parallel. Velocity is in the x-axis, length is y-axis, magnetic field z-axis. In this case, when it comes to the EMF will be simply, that is, what is the, guys, that is BLV. That is BLV. Take a look, guys. Here, velocity is in the x-axis, length is y-axis, this is z-axis. In this case, what is the magnetic field due to this wire at a distance? Guys, we say magnetic field due to wire at a distance is mu naught I divided by, what is the magnetic field because of an infinitely long wire? Mu naught I divided by 4 pi r. And instead of r, I can write a. Because this is r. Magnetic field because of an infinitely long. This wire is infinitely long. At a distance will be mu naught I by 4 pi a. So you can say this EMF in this case will be simply mu naught I divided by 4 pi a v into L. This is the correct answer. Okay. This is the correct answer. Tell me in this case, okay, here EMF is 0. Why? Because length and velocity are, length is in the y-axis, velocity in the y-axis, length and velocity are parallel. Okay, if you have a structure something like this, guys, what do you do in this particular case? What do you do in this particular case? Guys, see. I can say in this particular case, whenever you have a structure something like this, always consider the effective length. Always consider the effective length. Okay, guys, if this is L, this is total is 120, this will be 60. This is also how much? That is 60. If this length is L, this length is also L. Which component is this? L cos 60. Which component of length is this? This is L sine of 60. This is L. This is L cos 60. Which component of L is this? This is L sine of 60. Now, guys, what is the effective length? Join one end with the another end. In this case, always remember effective length is 2L sine 60. Because this plus this is 2L sine 60. What will be the motional EMF in this case? So in this case, EMF is equal to BVL effective. So I can say, what is the magnetic field? B, that is given. Magnetic field is B. Velocity is V. L effective, that is 2L sine 60. Sine 60 is √3/2. So this is BV2L. And this will be √3/2. 2 and 2 will cancel. So it is √3BVL. So whenever you have a structure which is not straight, in that case, you guys are supposed to take the effective length. You guys are supposed to take the effective length. Okay. Yo. Let's suppose if you get a question something like this, guys. In this particular case, let's suppose the question is, this radius is R, this radius is 2R. Okay, and this structure is moving with a velocity V. You guys are supposed to tell me what will be the motional EMF in this particular case. What will be the motional EMF in this particular case? Guys, in this case, I can say when it comes to the motional EMF, guys, see, this structure is made up of two parts. This outer part, okay, this inner part. I'll make it. Guys, this outer part, this inner part, this inner part. This will also create EMF. This will also create EMF. Could you please tell me what is the effective length in this particular case? Effective length will be, guys, this length, that is 2R plus 2R, 4R. L effective is 4R. What is the effective length of this? This is also effective length. Here also it will be 4R. What is EMF induced in this part? EMF induced in this part will be BV4R. Because BVL effective. Here also EMF induced will be, that is BVL effective. So that is BV4R, BV4R. BV4R, BV4R. Okay. Let's suppose if somebody asks you this, you have got a square. Okay. This square in this particular case is moving with the velocity V. Okay. And current is flowing in this case I. You guys are supposed to tell me what is the EMF. Guys. Let's suppose this is A, B, C, D. In this case, can I say EMF in CD and AB? In CD and AB is 0. EMF in CD and AB is 0. Why? Because length and velocity are parallel. L and V are parallel. velocity and length are parallel. Okay. किसमें direction? In which one you are saying? QA writes. QA writes. किसमें बोल रहे हो? In which question you are saying QA writes? Now guys, in this particular case, okay, let me say over here, when it comes to this and this, we say EMF is 0. Now EMF in this and this, let's suppose length is L, length is L. So I can say EMF in AD. Guys, that will be simply, that is BLV EMF. Okay. And when it comes to the EMF in BC, that will be also BLV. Simply. Okay. Let's talk about self-induction. Let's talk about self-induction. Okay, let's talk about self-induction. Guys, understand one thing very carefully. Let's suppose you have got a coil over here. This is the coil that you are having. Okay. Okay, this is a coil, or you can also call it the solenoid. Okay, solenoid, or we say coil of N turns. And in this coil, we say current is flowing. Okay. We say whenever the current flows in a solenoid, it produces the magnetic field. It produces the magnetic field. It produces the magnetic field. Okay. Now, guys, I can write over here. Due to the current, or I'll directly say, sir, because of the current, we say magnetic field is produced inside. Okay, because of the current, magnetic field is produced. And this magnetic field crosses the area of the coil. It crosses the area of the coil. It is along the axis. We say flux is produced. Flux is produced. Okay. Now, can I say more is the current, more field will be produced. More will be the flux. So I can directly say, my dear friends, flux is directly proportional to the current. More current you send through the coil, it will create more magnetic field. More magnetic field will cross through the coil. More flux will be produced. More flux will be produced. Now, my dear friends, if I replace this with a constant of proportionality, so I'll use the constant as L, where L is called, I say self-inductance, where L is called self-inductance. Okay. Where L is called self-inductance. Now guys, my dear friends, this self-inductance is equal to mu naught N square A into L. The value of this self-inductance is further equal to mu naught N square A into L. What is N? N means number of turns per unit length. How many number of turns are there in a unit length? Okay. We say A. A means area of cross section of the coil. Then L. L means length of the coil. L means length of the coil. L means length of the coil. Okay. Now guys, let's suppose if the current I is changing, if you send a increasing current in the coil, which is increasing, can I say because of this increasing current, can I say because of this increasing current, the magnetic field which you produce will be also increasing? The magnetic field which you produce will be also increasing. If current is changing, magnetic field will be also changing, increasing, whatever you say. Okay. We say due to which flux will also change. If you increase current, magnetic field will increase, flux will increase. Now guys, from this equation, how do you write the change in current? Sir, that is di by dt. Because of change in current, flux will change. How do you write change in flux? d phi by dt. So because of di by dt, flux will change. That is d phi by dt. Now, my dear friends, what is d phi by dt? We say Faraday's law says that EMF is equal to d phi by dt minus d phi by dt. So instead of this d phi by dt, I'll write EMF. So EMF is equal to L di by dt. So minus is because this minus. So this is what we call the production. This is what we call the EMF induced in the coil. This is what we call the EMF induced in the coil. Okay. Now tell me guys, because of the change in current, EMF is being induced in the coil. This production of EMF is what we call the self-induction. I'll mention over here. This production of EMF is called self-induction. This production of EMF is called self-induction. Sir, what is this self-induction? Self-induction simply means if this is a coil, guys, in this coil you are sending the current. In the same coil, magnetic field is being produced. In the same coil, flux is being produced. In the same coil, EMF is being induced. So we say EMF is L di by dt. That's why we call it self-induction. Now, if the concept would have been something like this, if you have a coil, if you have another coil, we say current in this coil is changing. Current in this coil is changing. Okay. Now, because of this current, magnetic field would be produced over here. Now, this magnetic field changes. So, because of this magnetic field, flux will change. Now, if this flux changes, EMF will be induced in this coil. Current was flowing in one coil. EMF is induced in another coil. This is called mutual induction. But when it comes to the self-induction, we say current flows in the same coil. We say magnetic field is induced in the same coil. We say EMF is induced in the same coil. Okay. We say EMF is induced in the same. That's why we call it the self-induction. Okay. The current passing through a coil of 5 Henry is decreasing at the rate of 2 ampere per second. So di divided by dt in this particular case is given as 2 ampere per second. Okay, 2 ampere per second. Current in a coil is decreasing at the rate. Let's suppose this is the coil. In this coil, current is decreasing at the rate of 2 ampere per second. And inductance L is given as 5 Henry. You have to find EMF developed in the coil. Guys, simply EMF is equal to minus L di by dt. And guys, we say minus L, value of L is 5. And di by dt. Di by dt is minus 2 ampere per second. Why? Because current is decreasing. So minus 2 ampere per second. Okay. 5 into 2 is 10. So that is 10 volts. EMF induced will be 10 volts. There was a question asked in NEET 2016. Okay, this one, give it a try. What is the answer of this question? Tell me. Tell me, guys. A long solenoid has 1000 turns. There is a solenoid, it has got 1000 turns. Okay. When a current 4 ampere flows through it, the magnetic flux linked with each turn is 4 in 10 raised power minus 3 Weber. Okay. Guys, flux through one turn. There is a solenoid. Flux through one turn is given as 4 into 10 raised power minus 3. Now, how many turns are there? 4000. So, I can say flux through 4000 turns. It will be simply 4000 multiplied by this. Okay. It will be simply, sorry, 1000. 1000 into multiplied by this. When a current of 4 ampere flows through it, okay, the self-inductance will be, guys, we say flux will be L into I. Flux will be L into I. And in this particular case, flux through each turn is this. Flux through 1000 turns will be how much? 1000 multiplied by 4 into 10 raised power minus 3 is equal to L. Current flowing in this will be 4 ampere. Guys, it says that we have a solenoid which has got number of turns as 1000. It says flux through each turn is 4 in 10 raised power minus 3. How much will be the flux through all the turns? 1000 into 4 in 10 raised power minus 3. Okay. So, my dear friends, is equal to this. Now, 10 raised power plus 3, 10 raised power minus 3. 4, 4. L is equal to 100. L is equal to 100. We are supposed to find the self-inductance in this case. Mutual inductance. Let's talk about the concept of mutual inductance. Guys, see. Let's suppose you have got a coil over here. You have got a coil over here. And there is one more coil over here. The radius of this coil is R1. The radius of this coil is R2. Okay. Such that the distance between the two coils is X. And X is much, much greater than R1 and R2. X is much, much greater than R1 and R2. Okay. Now, my dear friends, in this particular case, what I'm trying to say is that, sir, if the current is flowing in this coil as I, because of this coil, magnetic field will be produced over here. Because of this coil, magnetic field will be produced over here. We have previously studied. A coil creates the magnetic field near it, around it. And we have studied how much is the value. Now, if because of this coil, magnetic field is present over here, that magnetic field will actually cross the second coil. That magnetic field will actually cross the second coil. So, can I say, flux will be produced through the second coil? Yes. So, flux through the second coil is proportional to the current in the first coil. If more current flows through the first coil, more magnetic field will be produced on the axis. More magnetic field will cross this coil. Okay. Then more flux will be produced through this coil. Then, my dear friends, I say flux in the second coil is directly proportional to the current in first coil. Replacing the proportionality with a constant, we say M into I, where M is called mutual inductance. where M is called mutual inductance. Mutual inductance. And value of this mutual inductance is mu naught. R1 square, R2 square. R1 is the radius of this coil. R2 is the radius of this coil. Pi divided by 2x cube. X is the distance or the separation between the coils. This is the value of M. Now guys, if I say, if I changes, if current changes, so flux changes. Guys, if I changes, flux changes. If flux changes, then EMF is induced. Okay, because we know EMF is d phi by dt minus d phi divided by dt. Now guys, how do you write change in current? How do you write this change in current? I'll write over here. Sir, this is di divided by dt. Sir, mutual inductance is constant, is equal. Because of change in current, flux will also change, d phi by dt. Now guys, we know d phi by dt will be actually equal to, that is EMF, because EMF is d phi by dt. So EMF is equal to mdi by dt. This is called the mutual induction. This production of induction, I'll write over here. This production of EMF in another coil is called mutual induction. This production of EMF in another coil is called mutual induction. Why? Because current is changing in one coil, EMF is flowing in another. EMF is induced in another coil. That's why we call it the concept of mutual induction. Is this clear? Okay. Guys, do this question on your own. Decrease of current in the primary coil is 2 ampere to 0. So means Ti is given as 2 ampere because 2 minus 0 is 2. And time in this case is given as dt is given as 0.01 seconds in 0.01 seconds. EMF in this case is given as 1000 volts. Okay. EMF in this case is given as 1000 volts. You guys are supposed to find the value of M. Simple. M is equal to, EMF is equal to mdi by dt. Okay. Okay. What else do we have over here? Guys, you say this self-induct, this is by the way length, okay, this is length of the coil, small l. Always remember when it comes to the number of turns per unit length, it means total number of turns. It is total number of turns divided by total length. This is important point. Total length. Total number of turns divided by total length. So this N you can say capital N divided by L. Now put it in the equation first, call this first. Put in first. If you put this in equation first, you'll get L is equal to mu naught. Instead of N, you'll get N square divided by L square. N square divided by L square. Because instead of N, you will get N square by L square. A into this L. Okay. This and this will cancel. So L will be mu naught N square A divided by L. Okay. This is the length. This is also the value of self-inductance. This is also the value of self-inductance. Okay. Okay, this is also the value of self-inductance. Okay. One more question I'll just give you in this case. Let me see who can do this particular question. Guys, let's suppose you have a wire over here. This is the infinitely long wire. In this infinitely long wire, current is flowing. Okay. Now there is rod placed over here. There is a rod placed over here. Okay. And this rod is at a distance from the wire. It is at a distance from the wire. Length of the rod is L. Okay. It is moving in the upward direction with the velocity V. You guys are supposed to tell me, find the EMF induced in the rod. Find the EMF induced in the rod. Find the EMF induced in the rod. Tell me, guys. Guys, tell me, in this particular case, guys, here magnetic field at different points will be variable. This is what I can give, what I'll give you as homework. I'll just give you the idea in this particular case. Magnetic field at different points will be variable. Because of this infinite wire, magnetic field at a distance will be something, at this something. So what you do is that you consider a small element over here of dx length, okay, which is at x distance from the wire. Then consider the magnetic field at this point, that will be constant at a single point. Then you find the EMF induced in this, that will be dE, okay. Then you integrate to find the total EMF. This will be the question that I am giving you as homework. Okay, guys, we finished till electromagnetic induction. I know next chapter, that is AC, the 7th chapter. It is 7th actually, not the 6th, it is 7th. 6 we have already completed. So this we will teach, this we will learn in the next marathon. So my dear friends, with this we are done and dusted. So I'm very tired. I know you guys are also very tired from your end. Okay. Take care, bye-bye. And guys, one more thing I forgot to tell you, that is, I would want you guys to tell me in the chats, not the chats, comments. When I end the live stream, do let me know in the